Hope you have coffee or tea or beer, depending on your time zone. So the first speaker today is Xin Wang from Baidu. And due to technical difficulties, he can say hi now, but then we'll have a recorded talk. So if you have questions, you can ask them on the Q&A, or you can ask them on Slack channel, or if you're watching this from the future, you can write an email to the speaker. Okay. And if there's something very pressing, then let us know in the question, because then we could, in principle, stop the video and answer live, but most questions will be answered at the end. Okay. And I'll post a link to the Slack channel now in a second. Okay. So whenever Xin and the technical support are ready, I guess we can start the talk.
Okay. Good morning, everyone. Thanks for coming to my virtual talk. And I would like to thank the organizers for organizing this very nice virtual conference. And also I want to thank the committee for giving me the chance to deliver this invited talk on quantum resource theories of quantum channels. And in this talk, I will mainly introduce my results on this topic from some selected results from my works with my collaborators. Okay, so I will first give you, an overview of this talk. I will first show you a brief intro of quantum resource theories, and then give you motivations from, quantum states to quantum channels, and then introduce you the main focus of our this talk. That is, what is the power and the cost of a quantum channel under different resource perspectives, and also under different protocols. Different settings of protocols. And then I will show you a very interesting application of quantum resource theory to the problem of quantum channel distinguishability. And finally, I will give you a summary and outlook. Okay, so first, what are resources? There are many kinds of resources. For example, information is a resource in the sense that if you know information of something, then you may have the ability to, have a higher success probability to make a right decision. And energy, and sometimes also resource, because you can use energy to drive machines. And in the quantum world, the most well-known resources are entanglement and coherence. And moreover, in this talk, our main focus is, consider quantum channel as a resource. And resources can be converted under certain conditions, and these conditions usually come from the physical constraints of experiments, or sometimes simply from the laws of physics. And to better understand this conversion, we need a framework and a developed kit to study these quantum resources. And the main focus of this talk, is to understand this interaction between quantum resources and quantum channels. First, what is the resource cost to implement a quantum channel, and the second, what is the power of quantum channels to generate quantum resources. And we want to know the answer of these questions. Okay, so first, what are quantum resource theories? And here, quantum resource theory models what we can physically accomplish given constraints on physical operations. And I will refer to this review paper by Chitambo and Gore. You can see the formal definitions and many examples, as well as the history and the tools in this review paper on quantum resource theories. And from my point of view, I think quantum resource theory offers systematic and powerful framework for us to study the power and the limits of quantum resources. And there are many very good examples. For example, there are resource theories for static resources like entanglement, coherence, magic, and so on, and also for dynamic resources like communication. And in the framework of quantum resource theories, there are two important elements. One is free states, and another is free operations. And the golden rule in quantum resource theory is that the free operations, always maps free states to free states. And here I also have to say, in quantum resource theory, we usually partition quantum states to two parties. One is the free states, another is the remaining is the resource states. And in quantum resource theory, we are interested in, the detection and the quantification of the resource states, as well as, the manipulation and application of the resource states under the free operations. And we have many resource theoretic tasks. As a warm-up example, I will introduce the entanglement theory. So entanglement is a property of a composite physical system that cannot be generated by local operations and classical communication. And in the resource theory of entanglement, the free states are separable states, and the free operations are LCC operations. And in this resource theory, the golden units are the maximally entangled states. And moreover, we usually consider the Bell states as the currency in this entanglement theory. And in this theory, we're interested in the transformation between resource states. And as you can see here, for example, there are two very fundamental tasks. One is entanglement distillation, aims at distill Bell states from given states, and another is dilution, using these Bell states to prepare your target quantum states. And the corresponding rates for distillation and dilution are called distillable entanglement and entanglement cost, respectively. Okay. And there are more examples of static resource theories. For example, recently very popular resource theories for magic and also coherence. And for magic, the free states are simply stabilizer states, and the free operations are stabilizer operations. And in this resource theory, we are interested in magic state distillation. And you can see the analog of coherence here. Okay. And from quantum states to quantum channels, I will give you the motivations. Resource theory actually, naturally goes to higher order, but with very fundamental motivations. First, quantum channels are resources. You can consider quantum channel theory as an example, and they can be used. Quantum channels can be used to transform classical, quantum, and also private information from one side to another. And also, quantum channels can represent dynamical resources in the sense that it can be used to generate quantum resources. And also, the quantum resource theory of quantum channels have a more complicated but also fruitful structure. I'll show you a partial list of the recent progress on the resource theory of quantum channels here. And in this talk, I will mainly mention some selective results from these 4 papers. And now, before showing you the results on resource theory of quantum channels, I will first introduce what is a quantum channel. Quantum channel, has different names in different communities. For example, it is also called quantum process, and also called noisy quantum circuits, and also quantum operations. And for all of this, we just call it quantum channel in this talk. And a quantum channel is simply completely positive and trace preserving linear map from one side to another. This is its mathematical definition. And it has many useful equivalent representations. First is this Troy cross representation. As you can see here is the sum of operators, and this EK is called the Troy cross operator of the channel, and it has to satisfy some conditions. And the second representation is this Stinger spring representation. That is, you can understand the whole evaluation as an isometry from Alice to the Bob and the environment. And if you trace out the environment, you will get the channel from Alice to Bob. And The third very useful representation is this Troy-Yamikowski representation. That is, you apply identity map tensor the channel to normalized maximally entangled states, and you obtain this Troy operator of the channel. This Troy operator have very nice properties because, and also gives us the semi-definite conditions to characterize a quantum channel. And then what is the role of quantum channel in quantum resource series? So I think first, quantum channels, some of them are just the free operations. And also the quantum channel itself is a kind of quantum resource, and it also leads to very fundamental questions about the fundamental cost and also the resource generating power of these quantum channels. I will first show you the first question: what is the the resource cost to realize a quantum channel? A good example to start with is quantum teleportation, introduced by Bannink et al. In 1993. In this protocol, one needs 2 classical bits and 1 e-bit to realize a noiseless qubit channel. And as you can see here, you can imagine this F as the protocol, and this protocol will consumes 1 e-bit to simulate a channel from Alice to Bob, and the goal of quantum teleportation is to simulate identity qubit map, such that Alice can send quantum states to Bob without any noise. And in this model of quantum teleportation, there is a trade-off. For example, the LCC protocol will consume classical bits for communication, and also it will consume shared. The protocol will consume the shared entanglement between Alice and Bob. And then it raises 2 questions. When classical communication is free, what is the entanglement cost? The second question is, when entanglement is free, what is the communication cost? And we can consider this as more higher level. That is also in this entanglement theory of quantum channels. If we want to realize quantum dynamical resource, under the free operations of LCC, for example, we will need quantum static resource to implement some quantum dynamical resource. And on the other hand, if we can use any local operations and shared entanglement, then we need quantum dynamical resource to realize another quantum dynamical resource. And so we can now move on to consider these 2 questions. First, what is the static resource cost under free operations? And the second, what is the dynamical resource cost under free operations? The most famous example here is the quantum channel theory. And also, to understand the resource cost, you also have to consider different regime of protocols. And here I want to introduce the most general protocols: adaptive protocols and parallel protocols. And here adaptive sometimes also called sequential. So for resource theory of quantum channels, we are interested in both parallel and adaptive regimes. And for the parallel simulation, the goal is to simulate this channel parallelly, and for the adaptive strategy, the goal is to reuse the resource state and to simulate the channel in this adaptive way. The main idea behind the sequential channel simulation, is to simulate the channel in a way such that m-uses of the channel can be caught in an arbitrary order, and in particular on demand when they are needed. Okay, and also I want to say sequential channel simulation is stronger than parallel simulation, which means it will have higher resource cost, and this also considered in discrimination, the topic of channel discrimination. And now I will show you our results on this resource theory of entanglement for quantum channels. Okay, so let me record problem again. What is the in-time cost of a quantum channel? Briët et al. First introduced this question about the in-time cost of a quantum channel when classical communication is free. And they define this as the minimum rate at which entanglement is needed to simulate many copies of quantum channel in presence of free communication. Here is the definition of of this in-time cost, and they show that this in-time cost of quantum channel is given by the regularization of this in-time information of the channel. And in our work, in my work with Mark Wilde, we consider the exact in-time cost of a quantum channel. And first, we define this one-shot exact in-time cost, which is the number of in-time bits that are required to simulate a quantum channel n exactly or perfectly using some free operations from the omega set. And then we define the exact parallel in-time cost, which just to simulate the channels in this parallel way. And then this exact parallel in-time cost is given by this regularization of the one-shot exact in-time cost. And when LCC is free, this problem is extremely difficult. Even for the state version, it is unsolved. And with us, consider a larger set of free operations called PPT operations. Which these PPT operations are the most common set of quantum operations beyond LCC. And its definition is given here, and you can search PPT operations for more details. And here we consider this operation because it is also widely studied in time theory and also can provide us many insights to understand the structure and the properties of and also limitations of quantum entanglement. Okay, when PPT operations are free, we are able to obtain this characterization of the one-shot exact in-time cost. And as you can see here, it is characterized by a linear optimization problem. And now the question is, what is the asymptotic, rate? What is the exact parallel in-time cost defined here, and how to solve this regularization problem? This is quite, challenging, because even for the one shot, we do not have enough good understanding, and now we have to solve this regularization, this asymptotic limit. And in our work, we found a very elegant way to solve the problem. And our starting point is to introduce this kappa entanglement of a quantum channel. So we first define this kappa entanglement as this semi-definite program based on the trigonometrics of the channel, and also making use of partial transpose and also the spectral norm. And then we found that this kappa entanglement of a channel can be used to bound this the one-shot exact in-time cost just up to some constant factors in the log, and we call this SDP sandwiched approximation. And then we also use the duality theory of semi-definite programming to show that the kappa entanglement of quantum channel is additive under tensor product. And combine these two properties, we are able to further estimate the asymptotic rate. So first, we can use the upper bound here to upper bound the exact parallel in-time cost. And then we can use the additivity of kappa entanglement to move m before the this e kappa. And finally, notice that this constant factor will not have any effects in the regularization, and we obtain this equality. So that is, we obtain this equality. The asymptotic rate is smaller than or equal to the kappa entanglement of the channel. And on the other hand, we can use similar idea to establish the reverse direction and obtain the result that for any quantum channel, the exact parallel income cost is equal to the kappa entanglement of the channel. Okay, so this is one of our main results. That for the one-shot case, it is not hard to estimate. However, if we consider asymptotics, things becomes more elegant, and we have this single letter SDP for for the exact parallel in time cost. Okay, as we already solved the parallel case, we move on to the sequential case, and I will record the product sequential, the definition of the sequential protocol in this figure. And here, for the sequential case, we also prove that the exact in-time cost is equal to the kappa entanglement of the channel. And the technique is also, the idea of techniques is similar. Here, however, we consider, n uses of the channel, and we try to estimate its, in-time cost. And we are able to use kappa entanglement to establish this sandwiched approximation, both lower bounds and upper bounds. However, both lower and upper bounds will, converge to kappa entanglement in the asymptotic limits, and which allows us to establish these main results. For the lower bound, it's simply from the, some operational reasons that the sequential simulation cost is larger than the parallel simulation cost. And on the other hand, for the upper bound, we consider the protocol that forces the resource after every round to be maximally entangled. And then we reuse this state. And these results are quite surprising because they tell us the sequential and parallel protocols have the same power in this, in-time cost of quantum channels. And we also implement the SDPs to estimate, the exact in-time cost of fundamental quantum channels and obtain, some both of these, analytical results. And we refer to the paper for more details. And this result also leads to many thoughts on channel resource measures. And first, we also show that the exact in-time cost of a quantum channel is equal to the maximum kappa entanglement generated by the channel. And also, actually here, I want to say it equals to the maximum kappa entanglement that can be amortized using the channel. And here, amortized means for a state rho, we first calculate its entanglement, and then we apply the channel and calculate the entanglement again, because the channel can sometimes, increase the entanglement, and then we maximize over this amortization, and turns out it's just equal to the kappa entanglement of the channel. And this interesting or surprising property supports one way of introducing channel resource measures. That is the amortized, amortized resource of a quantum channel. And this was introduced by Sikora and Wilde in 2018, formally this way. And our results from this also good examples of static resource cost of quantum channels under both parallel and adaptive protocols. And actually, similar ideas also work for the resource theory of quantum coherence. Diaz et al. This is a paper I collaborated with Diaz et al. And we show that the one-shot coherence simulation cost under the free operations called MIO, is characterized by the actually the max channel divergence. That is the one-shot coherence cost to simulate a quantum channel is equal to the the minimization of some channel divergences, the so-called smooth max divergence. And this finding actually supports another way of introducing channel resource measures based on the channel divergences introduced in these papers. and a general definition is given here. And as you can see, there currently we have two kinds of channel resource measures, and in the later part of this talk, I will show you some connections between these two resource measures. Okay, and we already learned some, information about the static resource cost. Now we will move on to the dynamic resource cost of quantum channels. Okay, so for the dynamic resource cost, it's about using quantum channels to simulate quantum channels under certain free operations. In general, there are free quantum channels and also free super channels. Here, as you can see, super channels are bipartite quantum channels that send quantum channels to channels, even when tensored with some identity map. And the question here is, what are the minimum dynamical resources that are required to realize a specific quantum channel? And again, we can use quantum teleportation as an example. And the question here is, when shared in time with free, what is the required classical bit to simulate your target channel? In quantum teleportation, target channel is noiseless qubit channel, and actually it can be other quantum channel. Okay, and here to better understand the dynamic resource cost of quantum channel, here we can introduce some mathematical metrics to better understand the problem. Here we introduce the minimum error of simulation from one channel to another under certain free operations in this way. We just minimize over the diamond norm between the here this composite between pi and n is just the effective channel after you apply the free super channel. The diamond norm, we minimize the diamond norm between this effective channel and your target channel m. And this is the minimum error of simulation. And based on this minimum error of simulation, we are able to introduce this channel simulation rate from one channel to another. And here, in particular, this rate is defined by n divided m, such that n uses of the first channel can simulate m uses of the second channel under the omega free operations up to some error tolerance. And this dynamical resource transformation is very powerful framework because it allows us to understand both channel capacity and the simulation cost. If we want to use noisy channel to simulate noiseless channel, then the cost, is indeed related to the quantum capacity. And the way, as you can see here, is you can use the channel simulation rate to represent the quantum capacity of a quantum channel under omega free operations. And for the reverse task, we're interested in the optimal rate to simulate a quantum channel n via the identity channel. And here the simulation cost of a quantum channel. Here the simulation cost is defined as the number of noiseless qubit channels to simulate a quantum channel in a asymptotic region. And here for short, we just call the simulation cost of quantum channel. And by operational reasons, we have this chain of inequalities. The first inequality here, E represents the intermediate codes, while NS represents the non-signaling assisted codes. The first inequality is due to the reason that intermediate codes is weaker than non-signaling assisted codes. And the third inequality is the similar reason, and the middle inequality is also the operational reasons that the capacity is always smaller than the cost. Okay, and in our work, in this archive paper, we've mainly focused on the simulation cost of a quantum channel, or the communication cost of a quantum channel under non-signaling assisted codes. And we first introduce max information of quantum channel, and this, is motivated by the resource theory perspectives. First, the free dynamic resources are constant channels because in this setting, we don't want the channel to, the free channel to communicate, and all these constant channels are free resources because they cannot send any information. And also the free superchannels are local operations with shared entanglement or non-signaling correlations. And motivated by many examples in the resource theory of quantum states, we define the following resource measures in this way of channel divergence. We first consider this max divergence between two channels, and then we introduce this max information of a quantum channel as the minimize this d max between channels over all the constant channels. And also we define its smooth version by considering this diameter smooth of the channel. And all the above is also compatible with other channel divergences. And the main results of our work is to, we first show that the one-shot simulation cost under non-signaling codes is equal to the smoothed max information of a quantum channel. And furthermore, we show that the channel smooth max information has a very nice asymptotic equipartition property, which we call it AEP. That is, it's asymptotic will converge to the mutual information of a quantum channel. And the main techniques to obtain these results involves post-selection techniques and partial smooth bound and many other result techniques. But the final result is very elegant. And we have both operational meanings of this smoothed max channel, smoothed max information of the channel, and also for its asymptotics. Okay, and then I will show you another example of dynamic cost called gate synthesis. And the problem is also simple but very important. Consider the magic states and magic channels are very necessary resources to achieve universal quantum computing. And also in fault-tolerant quantum computing, the stabilizer operations are very cheap, and we consider this as free operations. And now the question is, if we want to implement a target quantum operation, and the free operations are stabilized operations, now the question is, what is the minimum number of these magical resources that are required to implement your target operation? And to understand this problem, we introduced the resource theory of magic for quantum channels, and also we refer to another paper by Stilck and Cambyse for the magic of multi-qubit operations. And the message here is that resource measures like channel divergence and also from other techniques can help us estimate the magic cost of both noisy or noiseless quantum circuits. For example, in our paper, we can show that for any included quantum channel N, the number of channels E required to implement the channel N is bounded by this quantity, which involves these two channel resource measures. One is called mana of a channel, another is uses the channel divergence as a channel resource measure. And I will point to this paper for more details due to the time limit. And okay, now I already show you the very good examples of the static and the dynamic resource cost of quantum channels. Next, I will show you a very interesting application of resource theory to the quantum channel discrimination problem. And here, I will first, try to give you some motivation of quantifying distinguishability. Here, distinguishability is actually a resource in the sense that it limits the amount of effort needed to make decisions. And also, I want to say it can be considered as a resource that can be quantified and also interconverted. And in our work, we introduce the fundamental unit called bit of asymmetric distinguishability as these state boxes. Here was pi is the maximum mixed state, and we also introduce log m bits of asymmetric distinguishability as the following qubit state box, where pi m is defined in this way. And our motivation is that if for the state box, if m is larger than if m, for example, if m goes to infinity, then the state box can be perfectly distinguished because these two states are orthogonal. Okay. And actually, I will point out to the paper for more reasons of defining this these bits of distinguishability. And here, I will show you the resource theory of asymmetric distinguishability for quantum channels. And here, the basic object to manipulate is a channel box consisting two channels. And also, the free operations here are all super channels, which accepts, which maps quantum channels to quantum channels. And here, we consider, the motivation is that distinguishability of channels is also fundamental and resourceful. And the task, is to distill the distinguishability, to dilute the distinguishability, and also consider channel box transformations. And here, the current box is this replaced channel of, the state box I just introduced in the previous slide. I mean, if you can get larger m, this where means the two channels can be better distinguished. And also an important point in our work is again about parallel and sequential strategies. Okay, and the left is the parallel and the right is the sequential. And also we want to understand the the differences or the between discrimination under parallel and sequential strategies. And in our work, we utilize many tools in quantum resource theory and also channel divergences. And actually, in our work, we show that the asymptotic parallel distillable distinguishability is actually given by this regularized channel relative entropy. And this is the formal definition of the channel relative entropy. And this is for the parallel setting. Okay, so then you may wonder what is the result for the sequential. And surprisingly, we also we are able to solve it. And we found that the asymptotic sequential distillable distinguishability is equal to the amortized channel relative entropy. And here, dA is the amortized channel relative entropy defined in this way. It's just the relative entropy you can amortize by applying these two channels and m. Okay, and then we are able to provide operational meaning for this amortized channel relative entropy introduced by Briët et al. And also this can be considered as a solution to the Stilck's lemma for quantum channels in the sequential setting. It's very nice because under the sequential setting we have the single letter formula for the for the asymptotic distillable distinguishability. Okay, and then natural question is whether the sequential distillable distinguishability can be larger than the parallel distillable distinguishability. And here also we have the quantity for both particles, and we just want to know whether they are same or not. or which one is larger. And because the non-adaptive or sequential strategies are special case of the, the adaptive or sequential. Here, because the non-adaptive or these parallel strategies are special case of adaptive strategies. We have that the regularized channel relative entropy is always smaller than or equal to the amortized channel relative entropy. And the question is whether these inequalities are strict or not. And quite surprisingly, Fang et al. Introduced a chain rule of relative entropy in this way. And this directly leads to a negative answer to the above question. And this is the chain rule of relative entropy in their paper. And by some direct, calculation, you will obtain this inequality. That is, the regularized channel relative entropy equals to the amortized channel relative entropy, which means sequential and parallel protocols have the same power in this asymmetric channel discrimination task. Okay, so now I will wrap up the results in this talk. And the main message I want to deliver is that quantum resource theory of quantum channels provides us a powerful framework to understand the fundamental quantum resource cost and power of quantum channels. It provides us operational and quantitative insights into various quantum information process tasks. And it also has very fruitful structure. For example, for resource manipulation, there are two types, like resource cost and resource generation. And also for the regime or strategy, there are also two types, parallel protocols and also sequential protocols. And also for the resource type, there are also two types. One is, the static resource and also the dynamic resource. And it's a very fruitful structure, and many problems actually remain open. Okay, and also our results motivate different types of quantum resource measures for quantum channels. For example, the amortized channel measure, and also the channel divergence measure. And actually, quite surprisingly, they can be connected in the resource theory of asymmetric distinguishability. And also, the quantum resource theory of quantum channels will have applications to many other fields, such as quantum channel discrimination. And in the future, it will be interesting to develop, to have further understanding of quantum resource theories of quantum channels. For example, it will be interesting to solve the sequential in-time assisted simulation cost of quantum channels. This, is related to the quantum reverse channel theorem under the sequential regime. And also, we are interested in the in-time cost for quantum channels under the sequential regime. And maybe we need more tools for study, dynamic resource sequential regime, and also more theories for the channel divergences. And the final question is, again, the power between the difference of the power between parallel and the sequential protocols. The reason is that, as you can see from my talk, the results, these two strategies have the same power in exacting time cost of a quantum channel as well as asymmetric distinguishability. And the question is, can we find a case where the sequential protocol has, advantages of the parallel protocol? Okay, that's the question. And that's all. Thank you for your attention. And I also would like to thank my collaborators, Roberta, Kunfang, Yuan Su, Marco Tomamicio, and Mark Wilde. Okay, that's all. Thank you.
Okay, thank you, Xin Wang, for a very, very comprehensive and clear talk. It was a very nice overview of quantum resource theories and new results for channels. So I just talked to Xin Wang, and the audio is not good enough to answer questions live. So we're going to move the whole discussion to Slack. Okay, so during the next 5 minutes, we can answer and ask questions on Slack in the channel. And in 5 minutes, at 50 past the hour, we start with the new talk. So in the meantime, Srijita, if you can start sharing your screen, then yeah, this will make things easier. And for everyone else, see you in 5 minutes.
Is that working?
Yeah, that's perfect. Yes. Yeah, we now just wait a little bit. There's some background noise on your side, but maybe this stops when you start talking.
I think it's the air conditioner.
Okay, never mind. Okay, welcome back, everyone. So next up, we have a cryptography talk. Srijita Kundu from CKT Singapore, and it will be about device-independent XOR oblivious transfer. And again, you can ask questions here or on the Slack channel, which I'll post on the chat. Okay. Go ahead.
Okay. Hi everyone. Thanks to the organizers for letting me speak at this lovely conference. So I'll be talking about joint work with my colleagues Jamie from Perimeter Institute and Ernest from KT Zurich. And the talk is on device-independent XOR oblivious transfer. So in this work, we'll be focusing on the two-party cryptographic setting, where we have two parties, Alice and Bob. They want to do some kind of primitive or a simple cryptographic task, and they don't trust each other. Typical two-party cryptographic protocol will look like this. Alice and Bob may have some inputs that they'll enter into a communication protocol, and at the end of the protocol, they will get some outputs. The goal is going to be to design protocols that minimize cheating, where cheating is going to be defined depending on the task at hand. Examples of two-party cryptographic tasks include coin flipping, bit commitment, and oblivious transfer. All of these are primitives in the sense that they can be used to do more complex tasks, such as, for example, secure two-party computation. The task XOR oblivious transfer that we'll be considering is a variant of a more well-known cryptographic primitive called oblivious transfer. So we'll see what that is first. So there are a number of variants of oblivious transfer you can consider. The variant we'll consider here will have no inputs. So Alice and Bob will do an oblivious transfer protocol. And at the end of the protocol, Alice will output 2 bits, x0 and x1. And Bob will output 2 bits, B and XB. The first of Bob's bits is going to be interpreted as an index. And his second bit is going to be equal to one of Alice's output bits, depending on the index. And ideally, we want an oblivious transfer or OT protocol to have two properties, completeness and soundness. For completeness, we want the output bits x0, x1, and xp to be uniformly random. And we also want that the protocol does not abort if both parties are honest. In general, protocols can abort. For soundness, we'll consider two different scenarios. One is when Alice is honest and Bob is dishonest or cheating. And the other is when Bob is honest and Alice wants to cheat. So when Bob wants to cheat, he wants to learn both bits, x0 and x1. Remember, he's supposed to output only one of them. And when Alice wants to cheat, she wants to learn Bob's index bit B, which she's not normally supposed to learn. So for soundness, we want that Alice should not be able to learn B and Bob should not be able to learn both x0 and x1. The cheating probabilities for oblivious transfer, which we'll denote by POTA and POTB, are going to be the probabilities that Alice can learn B and Bob can learn both x0 and x1. So our task XOR oblivious transfer is a slight variant of this, as I mentioned, where there are no inputs as before. And in this case, Alice outputs 3 bits, x0, x1, and x2. But his her third bit, x2, is in fact just the XOR of the first 2 bits. And Bob outputs a trit and a bit. Bob's trit is an index as before. And depending on his index, he learns one of Alice's 3 bits. As before, we want completeness and soundness. We want that x0 and x1 should be uniform bits and B should be a uniform trit. And the abort condition is going to be the same. And we also want that, as before, that Alice does not learn B and Bob does not learn both x0 and x1. The cheating probabilities for this protocol are going to be denoted by PXOTA and PXOTB, which are the probabilities that Alice learns B and Bob learns both x0 and x1. I'll elaborate on the cheating probabilities a bit more when I get to the actual protocol. So why are we considering this weird variant of oblivious transfer? First of all, because it's a generalization of oblivious transfer. And oblivious transfer is a very powerful cryptographic primitive. It is universal for secure computation, as was shown by Killian in 88. If you can do oblivious transfer, you can do other cryptographic primitives such as bit commitment and coin flipping. And in fact, we show that if you have a perfectly secure XOT protocol, then you can have a perfectly secure OT protocol. This means that if you have an XOT protocol which has the ideal cheating probabilities for Alice and Bob, then you can use that to give a protocol for OT that has the ideal cheating probabilities for Alice and Bob as well. Another reason is that we are studying device-independent protocols, and device-independent protocols are generally constructed from non-local games. And we were looking at this non-local game, which is Magic Square. And as it happens, the structure of the Magic Square game is very similar to the structure of XOT. So why do I say that? So let us first look at the Magic Square game a bit. In the Magic Square game, you have a 3x3 grid. Alice gets as her input a row of this 3x3 grid, which will be denoted by A, and Bob gets as his input B a column of this 3x3 grid. Both of these are with uniform probability. Alice is required to output x0, x1, and x2, which fills her row, and Bob is required to output y0, y1, and y2, which fills his row of the 3x3 grid. And the win condition of the Magic Square game is that Alice's bits should be such that they XOR to 0, Bob's bits should be such that they XOR to 1. And in the square where Alice's row and Bob's column overlap, their output bits should be equal. That is, XP should be equal to YA. The quantum strategy for the Magic Square game is just that Alice and Bob share two EPR pairs, and they perform measurements which are where the 0 and 1 measurement outcomes are the plus minus 1 eigenstates of the Hermitian operators shown here on the rows and columns here. The trick is that along a row, the Hermitian operators commute and they multiply to identity, and along a column, they also commute and multiply to minus identity. The quantum winning probability of the Magic Square game with this strategy is perfect. You can win with probability 1, whereas the classical winning probability is only 8 by 9. So how are we going to give an XOT protocol from the Magic Square game? Let us first consider the device dependent case, and let us do the most obvious thing. Alice and Bob share the Magic Square state. Alice and Bob then pick inputs A and B on their own sides privately with uniform probability, at least ideally, and they do the corresponding Magic Square measurements. So then Alice will get output X and Bob will get output Y. Now Alice can send her input A to Bob and output X now. This means that Bob in fact knows XP, because recall that the Magic Square winning condition is that YB is equal, YA is equal to XP ideally. And now Bob knows both Y, which was his output, and A, which Alice sent him. So he can output YA is equal to XP. So yeah, Alice is going to output X and Bob is going to output B and YA. The completeness condition is satisfied here because the Magic Square game has this property that X is going to be uniformly random among all 3 bits which XOR to 0, and Bob chooses his trit be uniformly at random anyway, so he can always make it random. And right now there is no abort in the protocol anyway. So there is this good protocol is good and bad. The good thing about this protocol is that Alice cannot cheat at all because Alice does not receive anything from Bob, and just via signaling she cannot learn Bob's input. The problem is that Bob can cheat perfectly, however. His cheating strategy to cheat perfectly is he doesn't measure Y beforehand like he's supposed to. He waits till he receives A from Alice, and then he performs the exact same measurement as Alice. The property of EPR pairs ensures that if he does this, then he can get the exact same output as Alice. Hence, he knows X. So we obviously don't want Bob to cheat perfectly, so we're going to modify this protocol of it. The workaround we're going to use is we're going to force Bob to send Y to Alice before receiving A from her. Now, why is this good? This is good because if Bob uses the cheating strategy that I described earlier, where he does not measure Y beforehand and sends some random Y or a fixed y, doesn't matter, to Alice. Alice can detect that Bob has done this and abort. How does this happen? So Bob's output condition is that y must contain at least 1, 1, because y0, y1, and y2 XOR to 1. But Alice's outputs XOR to 0. So Alice's output can sometimes be 0, 0, 0. Now the Maxwell condition is such that xb should be equal to ya. Now if x is equal to 0, 0, 0, and Bob has sent y such that ya is equal to 1, then Alice knows that Bob must have cheated, because if he had actually used the magic square measurement, then this would not have happened. And x is equal to 0, 0, 0 and y equal to 1 with probability 1/12. So Alice can detect cheating with probability 1/12. This means that Bob can still cheat with probability 11/12, which is like 91.66%. But that's better than being able to cheat perfectly, which he was able to do before. Now the bad thing is that now we are making Bob send something to Alice, his output y, and Alice can try to learn B from y. But fortunately for us, Alice can't learn B perfectly. So here's what the final protocol is going to look like. Alice and Bob share the magic square state ideally. Bob does a measurement, or he does not do a measurement if he's dishonest, and sends y to Alice, and then Alice sends her intended input A to Bob. After that, she does a test to get does her measurement to get her output X, and she does the test mentioned earlier to check if X, Y, and A are consistent. If the test accepts, then she outputs X, and if the test rejects, then she aborts the protocol. Bob, as usual, outputs B and YA as he did before. Now, since this protocol can abort, we are going to need to incorporate the abort condition in the cheating probability definitions. Alice's cheating probability P XOTA is going to be the probability that Alice learns B and the protocol doesn't abort. And Bob's cheating probability P XOTB is going to be the probability that Bob learns X0, X1 and the protocol doesn't abort. Including the protocol doesn't abort in Alice's cheating probability is a bit superfluous, because I mean, right now in this protocol, Bob cannot abort anyway, but we are doing it anyway because for future compatibility. So we prove upper bounds on the cheating probabilities of this protocol. The cheating probability is upper bounded in two different scenarios. One is when Alice and Bob, well, the honest party trusts the state that is shared in the protocol, but not the measurement that the dishonest party performs. The second is when they trust neither the state nor the measurement. In both cases, however, the honest party always trusts their own measurement because this is still a device-dependent setting. So in the trusted state setting, Bob's cheating probability is 93.62%, which is greater than the cheating probability 91.66% that we saw earlier. That's because Bob can use a slightly different but less obvious strategy to cheat. The untrusted state cheating probability is higher than the trusted state cheating probability in both cases, because it gives more freedom to the cheating party. And also Alice's cheating probability is lower than Bob's cheating probability in both cases, because Alice is supposed to learn one of three things, so her cheating probability should ideally be 1/3, whereas Bob's cheating probability should ideally be 1/2. The way these bounds are obtained is by expressing the optimal cheating probabilities as semi-definite programs and solving the semi-definite programs numerically. So, for example, in the trusted state cheating Alice scenario, the cheating probability is just the result of a state discrimination problem, for which NSDP is well known. Okay, so how do we make this protocol device independent? Before I do that, let me clarify our device independent setting a bit. We are going to make these assumptions. So we're going to model the party states and measurements as black boxes. The parties should be able to send their black boxes to each other, which is something we'll make use of. Because the setting is device independent, we're going to assume that the cheating party can tamper however they want with the honest party's protocol before the protocol starts. So they can control the honest party's measurement as well. But crucially, they can only do this before the protocol. They can't do anything further after the protocol starts. which is a property that will help us. And we need two further assumptions, which is that the honest party's box can't just broadcast its input or output. If they could do that, then no cryptography would be possible, basically. So this assumption is always needed. And one further assumption is that the measurements implemented by the two boxes are in tensor product with each other. This is not super crucial. You can generally use a weaker assumption, like the measurements simply commute, but this is a common enough assumption, and so this is the one we'll be using. Okay, so note that the assumption 3 that we've used implies perfect cheating if we use the device dependent protocol as is. Because, for example, Alice can cheat perfectly like this. She sets up Bob's box in such a way that his output Y encodes his input B in some way. And since Bob sends his output Y to Alice, Alice can learn his input B perfectly from there. But the thing that will save us is this property of self-testing of the magic square game, which can help certify the honest party's measurement. So by the self-testing or rigidity property of magic square, I mean something like this. So this is a lemma that follows basically from the work of Wu et al. And Kudrin et al., but we had to do some extra work to get exactly what we needed. Suppose Alice and Bob have some unknown state and measurements with which they achieve magic square winning probability of 1 minus epsilon. Then up to local isometries, their measurements applied on their state are close to the ideal measurements applied on the ideal states. Where by close I mean we go of epsilon to the 1/4 close. The constants in this lemma in the big O can actually be tracked, but we haven't bothered to do so because they're quite large and it wouldn't make a lot of difference anyway. Okay, so let's see how this self-testing helps us. So suppose, let's consider the case where Alice is honest and Bob is dishonest. And suppose that Alice can do two different subprotocols with Bob. So suppose she can choose to do the device-dependent protocol with Bob. As I said before, Bob can set up Alice's box in such a way when Alice does this, such that he cheats perfectly. So Bob's cheating probability in this case, which we'll denote by P prod B, is could potentially be 1. Now suppose Alice could also do something else. She could ask Bob to send her his box. And once Bob sends her his box, she can privately self-test magic square on both boxes on her side. So she just checks if the output of the boxes satisfies the magic square winning condition. And if it does, then she does a trivial protocol, and if it doesn't, then she aborts. The trivial protocol is just Alice chooses a fresh x0, x1 on her side and sends both to Alice, and then she outputs both x0, x1, and Bob outputs B and xb. But since Bob gets both from her, he can learn both of the bits perfectly. So the probability that Bob can cheat in this scenario is just the probability that Bob can pass Alice's test. And in fact, Bob can set up Alice's box so that he can pass the test with probability 1, because he can just have both the boxes implement the magic square state and measurements, which will always pass the test. So Bob's cheating probability in this case is also with 1, and we'll denote this by P test P. Okay, but suppose suppose Alice could randomly choose to do any one of these two subprotocols. She could either perform the device-dependent protocol with Bob, or she could ask Bob to send her his box and perform the self-test. Then Bob can't actually cheat in both of these things with probability 1, because Bob needs to because Bob can't tamper with Alice's box before the protocol starts, and the way he needs to set up Alice's box to cheat in both cases, they're not compatible. So even though Bob can achieve P protocol B equal to 1 and P test P equal to 1, he can't do both at the same time. He could have two different boxes on his side, which he would use in the two different cases. But because Alice's box has to be the same for both cases, this is not possible. Thus, if Alice uses a probabilistic mixture of these two subprotocols, that means that Bob's overall cheating probability is less than 1. So this is what our final device-independent protocol is going to look like. So first we'll let Alice decide whether she's going to test or not test. Then we'll let Bob decide whether he's going to test or not test. If neither party decides to test, then both of them perform the previous device-dependent protocol as usual. If Alice decides to test, as we saw earlier, Bob sends her his box, and then Alice self-tests Mary Square privately on her side. If the self-test accepts, then she performs a trivial protocol, which allows Bob to cheat perfectly. If the test rejects, then she aborts. And if Bob decides to test, then Alice sends him her box, and he tests Mary Square privately. If the Mary Square test accepts, then he does a different trivial protocol on his side, which will let Alice cheat perfectly. Otherwise, he rejects. The cheating probability of this device-independent protocol, they're going to be expressed like this. Alice's cheating probability is QB times P tested plus 1 minus QB times P prote, where QB is the probability with which Bob decides to test or not. Bob decides to test, and Bob's cheating probability is QA times P tested plus 1 minus QA times P prod. Sorry, there's a typo. QA times P test P and 1 minus QA times P prod B, where QA is the probability with which Alice decides to test or not. So we upper bound these cheating probabilities in two different ways. First is the analytical approach, where we use the rigidity property of Mary Square. So by the rigidity property of Mary Square, if Alice's probability of passing the test is at least 1 minus epsilon, that means that Bob's measurement applied to the shell state is order epsilon to the 1/4, close to the ideal measurement performed on the ideal state. So this means we're back to the trusted state device dependence situation, and Alice's probability of cheating should be order epsilon to the 1/4, close to her cheating probability in the trusted state device dependence scenario, which was 0.8333. However, as I said before, because the constants in this big O notation are not very big, these bounds become kind of useless for epsilon bigger than 10 to the minus 4. So we at most get cheating probabilities which are like 1 minus 10 to the minus 4 or something. So we also adopt a different approach, which is numerical approach. So we can express the cheating probabilities as optimization problems, which can be solved by the NP hierarchy of SDPs. So our code for this is online. In fact, anybody can check it out. There is a slight caveat in that our protocols have sequential measurements, which the NP hierarchy normally does not handle. We need to do some tricks to deal with that. The NPA optimization is done with numerical values of QA and QB. And after optimizing for the values of QA and QB as well, we get the cheating probabilities to be like this. Alice's cheating probability is 0.9644 and Bob's cheating probability is 0.9920. Bob's cheating probability is still pretty close to 1 here, but it's much better than the bounds we got using the analytical approach. Okay, so to conclude, we've in this work given a new device-independent protocol for XOR oblivious transfer. There weren't any device-independent protocols known for XOR oblivious transfer or even oblivious transfer before. We've bounded the cheating probabilities of this protocol in two different ways. First, we've bounded the device-dependent cheating probabilities using SDPs and the rigidity of magic square. And secondly, we've bounded the cheating probabilities using the NPA hierarchy numerically, but the bounds are still kind of close to 1. So one obvious future direction to work on is to try and get better cheating probabilities. One way we could potentially do that is to consider statistical protocols with many rounds of self-testing instead of the single shot self-test that we used. This sort of approach was used by Aharon et al. In their work on device-independent bit commitment based on the SH game. Another approach would be potentially to use the magic square game for other cryptographic tasks. And finally, we could try to make a composably secure device-independent XOT or OT protocol. Composably secure means that if you use the protocol as a subprotocol for a bigger task, then the bigger task is also secure. This is generally quite hard, and I'm not aware of any work having been done for OT in a composably secure setting, but it could be an interesting and important direction to pursue. Okay, I'm done.
Okay, thank you very much, Srijita, for your talk. Are there questions that I can see? So do you know for this optimal cheating probabilities, what was the ratio between for both parties? Like how many times did they test versus run? You know what I mean? Like if you go back to your diagram where we had the whole protocol.
Oh,
Yeah.
I mean, they either test or run the, as in they don't do both. As they,
yes, but you optimize over the probability of this coin that they flip, right?
Oh yeah. So I think our optimal QA and QB were both 0.6.
Okay, so it's fairly balanced. Okay, that's surprising somehow. Yeah. Okay. Are there more questions? If there are not more questions for now, then I direct everyone, including Srijita, to the Slack channel, and we can continue the discussion there over the rest of the day. And in the meantime, we have now a coffee break, so we'll see you again in half an hour at 45 past the time. Okay. Thank you. Thanks, Srijita. Thanks to everyone this morning.
Okay, good morning, everyone, and welcome for this second morning session of this last day of TQC 2020. So we're going to have 3 talks in this information theory session. The first one will be given by Farrokh Labib on the paper Quasirandom quantum channels. So this paper actually got the Outstanding Paper Award from the conference track. So before letting the room to Farrokh, I will pass it over to Andres Ambinis, who will kind of virtually give this award to this the authors of this work.
Hello, everyone. Here is the outstanding award paper Plague. The program committee selected as a TQC outstanding paper Bannink, Briët, Farrokh, Labib, and Hans Maassen, Quasirandom quantum channels. Congratulations, and we will mail this award certificate to the authors after the conference.
Okay, so congratulations once again to the authors. And well, Farrokh, the room is yours, so please go ahead.
Okay, thanks. Let me share the screen first. Is this, yeah, okay.
Yeah, looks perfect.
First of all, thanks for joining to this talk. And I'm honored to receive the, or we are honored to receive the Outstanding Paper Award. Thanks. So this talk is based on our paper Quasirandom quantum channels, joint work with Bannink, Briët, he's my supervisor, and Hans Maassen. Let's see. Okay, so our paper or our work was inspired or motivated by the work of seminal work of Chang, Graham, and Wilson in '89. They showed that for quasi-random graphs, that the number of seemingly unrelated properties of graphs are equivalent for dense graphs. Here, dense graphs are, so by a dense graph, I really mean a sequence of graphs on, say, n vertices, and n goes from, n is in natural numbers. And we want that a graph, so such sequence is dense if the number of edges is always omega n. So it contains omega n squared. So it has at least a positive fraction of the total number of edges. So that's what we mean by a dense graph. And they showed equivalence for a lot of properties, 7 to be precise, but we will be only focusing on 2 such properties, spectral expansion and uniformity. Let me define what is this? What is spectral expansion and uniformity? So, so G is a graph on vertex at V and edge at E. We want it to be deregular on n vertices. And then we order the eigenvalues of the normalized adjacency matrix by their absolute value. They're all real, by the way. And then we say that a graph is a lambda expander if this second largest eigenvalue in absolute value is at most lambda. So again, for what we really mean is actually you look at a sequence of graphs on n vertices, and you want for this whole sequence that the second largest eigenvalue is at most a constant, say bounded away from 1. And I should also note that random graphs, so say Airy's random graphs for which you for which the vertex set is n, and you pick you choose for 2 vertices for there to be an edge with probability 1/2, say. For such graphs, they are with high probability lambda expanders. And then uniformity, this is a little bit more of a combinatorial property. So again, G is a graph, and we say it's epsilon uniform if for subsets S and T, for all subsets S and T of the vertex set, that the number of edges here minus the edge density, which is d divided by n, times the total size of S and T, is at most epsilon times d times n. So this quantity here, d divided by n, which is the edge density, times S times T, is a quantity that is the number of edges, what you would really expect from a random graph if you chose the edges between S and T to be with probability d divided by n. And so this measures how much you deviate from this random graph. And random graphs are with high probability epsilon uniform. So Chung, Graham, and Wilson showed that for dense graphs, so for sequences of graphs for which the number of edges is omega n squared, so a positive fraction of n squared of the total number of edges, we have the equivalence that lambda is small, so its second largest eigenvalue is small, if and only if the epsilon is small, the uniformity is small. And one implication that the spectral expansion is small implies epsilon small follows from the so-called expander mixing lemma, and this is the easy part of the equivalence, and it simply states that epsilon is at most lambda. Then Chung Graham asked later about the equivalence for these two properties, spectral expansion and, or actually for all of them, but we will focus on these two. Does this equivalence hold for sparse graphs as well? The answer is no. In general, Krivelevich and Sudakov showed a non-regular counterexample of this. They showed that they construct a sequence of graphs which have small O of n squared edges, such that it is epsilon uniform. The uniformity goes to 0, but the second eigenvalue stays above a constant. But later, Kohayakawa, Rodel, and Schacht in 2016 showed that for Cayley graphs over abelian groups, the equivalence does hold. And then finally, in 2017, Conlon and Zhao resolved the problem by showing that the equivalence is true for vertex transitive graphs. Here, vertex transitive graphs are graphs with a lot of symmetry. And so mathematically, it says that the automorphism group of the graph acts transitively on the set of vertices. And Cayley graphs over any group are vertex transitive, but there are vertex transitive graphs that are not Cayley graphs. So this result is really more general. For example, the Peterson graph is vertex transitive, but not a Cayley graph. And they showed necessity by giving an example of graphs that are not vertex transitive, for which the equivalence does not hold. So let me state this theorem. So if G is a vertex transitive graph, so its automorphism group acts transitively on the edge on the set of vertices, then epsilon is at most lambda. This is the expanded mixing lemma, by the way. This is this holds for any graph, so this is the easy part. And then the non-trivial part is really this second inequality. Lambda is at most 4 times this mysterious constant times epsilon, uniformity. Kg is the Grothendieck's constant, which appears in the Grothendieck's inequality, which is a famous result in functional analysis. It's quite surprising that this appears here. It's known to be between 1.67 and 1.7822. And we also show in our paper that this inequality is in fact optimal. So our work in this story is to draw a parallel line in the context of quantum information theory, where quantum channels or superoperators in general will replace the role of graphs. So we will see the definitions for spectral expansion, uniformity, and vertex transitivity, but for quantum channels. So let's go to it. But maybe first some motivations for expanders. So expander graphs have many applications in computer science. It's related to the convergence rate of Markov chains and plays a key role in Monte Carlo algorithms. And one key property of expander graphs is that when you run a random walk on the graph, it very quickly converges to its limit distribution. This is something that's used. Construction of good error correcting codes, and some other application in the theory of games. You can show that for certain multiplayer games called expander games, you can show parallel repetition theorems, which is very interesting. And some motivations for spectral expansion for quantum channels. So this has already been defined quite recently compared to expander graphs by Hastings and independently by Ben Arroyo, Schwartz, and Tashma. And it already found applications through randomness reduction in sampling from harm measure. And in cryptography, Cambyse and Sumeet used quantum expander implicitly to construct short quantum momentum paths. So far the motivations. Let me state our results. We show that for irreducibly covariant quantum channels, expansion and uniformity are equivalent. I haven't defined yet what are irreducible covariant, expansion, and uniformity, but this should be really seen as the generalization of Connon and Zhao, where vertex transitivity is replaced by irreducibly covariant, expansion by spectral expansion, and uniformity for channels. We also show that this is actually a necessary condition, or actually this, we show that there are quantum channels which are not irreducible covariant for which the equivalence fails. We actually use the same examples as Connon and Zhao by finding a suitable embedding of graphs into quantum channels. And for randomizing channels, this is a notion introduced by Abraham. We show that expansion and uniformity are equivalent. And this should be really seen as a generalization of the dense case for graphs. So the first bullet point really is the sparse case, or the Connon-Zhao generalization. And this is the generalization for Chung and Graham Wilson that showed equivalence for dense graphs. And this should be seen as that, for which we also give arguments why this is the case. And also for the Connon and Zhao theorem, we show that their constant is optimal. So the Grothendieck constant is not there for the show. To state our results, it isn't necessary to go through some technical definitions. So let phi be a superoperator. This is a linear map from the n by n complex matrices to n by n complex matrices. And for P and Q in 1 to infinity, the P to SQ norm is defined to be the following expression. We maximize over all non-zero matrices for where we look at the fraction of phi of x, the Schatten Q norm of phi of x divided by the Schatten P norm of x. And this Schatten P norms for matrices are simply the LP norms of the singular values, or if X is diagonalizable, the LP norms of the eigenvalues. Maybe a more convenient way of writing this Schatten P to Q norms for us later is using duality. We can write this also as the supremum over all trace inner product between y and phi of x of where we maximize over all matrices such that Schatten P norm is at most 1 of x and Schatten Q prime of y is at most 1. Here Q prime is the dual to Q. And also a small remark is that we use a normalized trace inner product. So the inner product between y and phi x is really 1 over n, the dimension, times the trace of y star phi x. And now let me go through the definitions of expansion and uniformity. So expansion so this is definition by Ben Oroy, Tashma, and Schwartz. So a unit of quantum channel phi is lambda expanding if the S2 to S2 norm of phi minus pi is at most lambda. And here pi of x is the projector onto the identity. So how should we interpret this? So this, why are we subtracting this pi of x? This is because the channel is unital, so it has it sends identity to identity, which you could see as eigenvalue 1 vector. And we don't want that eigenvalue 1. So just like in the graph case, we only looked at the second largest absolute value. This is in this way measured that. You could also think about the Choi matrix of phi minus pi. This is simply the operator norm of this Choi matrix. Uniformity is this is our new definition. We say that superoperator phi is epsilon uniform if the cut norm of phi minus pi is at most epsilon. And what is this cut norm? The cut norm of a superoperator is simply the supremum over all trace inner product y phi x, such that x and y are projectors onto subspaces. This might seem weird, but there is a reason why we do this. Actually, this is very closely related to how Hastings defined edge expansions for superoperators. The idea is that, so he used, so in expansion, you look at subsets of the vertices and you look at the outgoing edges. And Hastings used as a generalization of vertex subsets, subspaces, projectors onto subspaces. And this is exactly what we also do. We look at, so uniformity was defined by looking at the edges between subsets of vertices. But now we are looking at subsets, subspaces of complex vector space, and look how much it correlates this phi with phi of x with y. So there is a good reason why we are doing this. And then the generalization of Vertex sensitivity. We think it's irreducible covariance. Irreducible covariance for superoperator is defined as follows. So we have a group G and two unitary irreducible representations, U and V, such that for any group element and any matrix X, we have that if we evaluate phi at X conjugated with U of G, this is equal to phi of X conjugated by V of G. So it's like almost commuting with phi, but we must change the, or we should change the representations here. Of course, you could also be covariant with the same representations, but this is more general. And of course, this covariance is a very important property, playing a key role in additivity conjectures of quantum channels. So why is this the right generalization? So we have given an embedding in our paper as follows. So you should view this matrix A as the adjacency matrix of a graph. And we map this graph into a quantum channel, the quantum channel that sends X, a matrix X, to this expression where we sum over Ij, Aij, and we only look at the diagonal of X, and we only the output is also only on the diagonal of the matrix. So intuitively, what happens here is you grab a matrix X, you simply look at the diagonal, which is a vector, and you apply your adjacency matrix on that diagonal, and you output the you put this vector back on the diagonal, and that's your output. And under this embedding, all these shuttle norms are preserved, which is very convenient. And yeah, so not all these norms are preserved. And then we can also show that Farrokh's transitivity is equivalent with irreducible covariance for graphs. So if you have a graph that is Farrokh's transitive, then its embedding is also irreducible covariant. And vice versa. If you have a graph that for which the embedding is irreducible covariant, then the graph must have been Farrokh's transitive. And in fact, we also recover Connon and Zhou's result, except that our constant is a little bit larger. So let me go through one of the proofs. I will go through the proof of the equivalence between spectral expansion and uniformity for superoperators, for quantum channels, sorry, for irreducible covariant quantum channels. For this, we have this technical lemma, which is the following inequalities. So phi is a superoperator that's irreducibly covariant. Then we have the inequalities that the infinity to 1 norm of phi is at most the 2 to 2 norm of phi. This is actually, so this first inequality is actually again a simple, easy inequality. It's just writing definitions out for these norms. It is really the second inequality that is non-trivial. And we show that this 2 appearing here in inequality is optimal. So this the first inequality holds for any superoperator. So this is our main technical lemma. So let me prove how we can get our result. So phi is a unital quantum channel that is irreducibly covariant. Then if phi is epsilon uniform, then its lambda expanding for lambda is at most 2 pi squared times epsilon. Again, the other direction that if it's lambda expanding, it's epsilon uniform is the easy part. So how do we do this? Phi is epsilon uniform means by definition that the cut norm of phi minus pi is at most epsilon. And then we use this fact that the cut norm and infinity to 1 norm are equivalent, meaning that the cut norm is at most this infinity to 1 norm, and this is at most pi squared times the infinity to 1 norm. And this pi squared is also optimal. So how do we prove this corollary? So the S2 to S2 norm, which is really this expansion parameter, this is at most 2 times the infinity to 1 norm of phi minus pi. This is the inequality here. And then we use the equivalence of the norms of the cut norm and the infinity to 1 norm. And then we simply use our assumption. So we see here, phi's epsilon uniform implies lambda expanding with lambda is at most 2 pi squared epsilon. And I should note that here, this constant 2 pi squared, we don't know if this is optimal. So we know that pi squared is optimal. So in this inequality, the pi squared is optimal. In this inequality, the 2 is optimal. But strangely enough, we couldn't figure out if this is optimal in this case. We tried some straightforward techniques, but didn't really work. So for proving the technical lemma, let me give you some ingredients to how to prove this. So this theorem is due to H group, the non-commutative Grothendieck's inequality. It says that if phi is a superoperator, then there exists density matrices ρ1, ρ2, sigma 1, sigma 2, such that for all matrices x and y, we have that the trace inner product between y and phi x is at most the infinity to 1 norm of phi times this complicated expression. And then we also need a representation theoretic lemma, which is the following. If G is a group and U is a unitary representation, then U is irreducible if and only if, for all matrices n by n matrices, we have that the expectation over all G, and where we conjugate X with a U of G, this is equal to the trace of X divided by n times identity. So it's like the projector onto the identity. And this, this expectation here is simply 1 over the size of G, if G is finite, times the sum over all elements, or you can use some higher measure if it's a compact Lie group or something. And this simply flows from Schur's lemma. So now let's go through the proof of this lemma. So we're only going to look at the second inequality. Okay. So phi is irreducibly covariant. So we have these two representations, U and V, irreducible representations for which phi is covariant. So it commutes with these representations. And then we use a simple trick that by covariance, we have that the tracing product between y and phi x is the expectation over all group elements, tracing product between yg and phi xg. Here, xg is x conjugated with ug, and yg is y conjugated with v of g. And you can show that by irreducible covariance, every term in the sum is actually equal to this. So this is, we're really doing nothing here. But then we can apply non-commutative Grothendieck inequality on each term and the AMGM inequality. So what do we get? This was at most this expectation, and each term is at most. So this one is from the non-commutative Grothendieck inequality. The 2 comes from the AMGM because there was a square root over these terms. And then you can look at the expectation over all G of this complicated expression. And here the density matrices are from this theorem. How do we continue? We are going to use the representation theoretic lemma, which says, which does allow us to compute each of these terms. So the expectation over all G of trace of rho 1 x g star xg, we can show we can show that it is equal to the trace of x star x. This follows from irreducible covariance, from irreducibility, and this simply is the Schatten-2 norm squared for x. And we can do this trick for all the other 4 terms. So what happens is we get twice the Schatten-2 norm of x squared and twice the Schatten-y norm of y squared. So then the 2 disappears and we get this. The tracing product between y and phi of x is at most infinity to 1 over phi times the sum of the Schatten squares of Schatten norms of x and y squared. And then we remember how was the Schatten-2 to 2 norm defined. It was simply this tracing product y and phi x, where we maximize over all x and y such that the Schatten-2 norm of x is the Schatten-2 norm of y is 1, or at most 1. This means that if we plug this in, we get indeed the S2 to S2 norm of phi is at most 2 times the infinity to 1 norm of phi. We then go on to the optimality. how do we prove the optimality of the constant 2? We only proved, we only showed the inequality, but there's still work to be done. So in the non-commutative Grothendieck inequality, H-group and Ito showed constructed a family of superoperators for which they were able to show the tightness of the non-commutative Grothendieck inequality. If you're familiar with these terms, this family was constructed using creation and annihilation operators. You could look at the survey of PCA on Grothendieck's inequality for a nice proof of this. And how do we use this? We can actually show that for this family of superoperators, that they are actually covariant with respect to some to the special real orthogonal groups S, O, and R, acting on vector products of complex vector spaces. And a key fact here is that this N appearing here is actually odd in this case, in the construction of a group in Ito. We get that N is odd, and from the literature, it's well known that these representations are irreducible. So what happens here, we show that this family of superoperators is covariant with respect to the group SON, a real SON, and then we know that's irreducible. So this means that actually this family is actually irreducible covariant. And then in the same way as they showed tightness of the non-commutative Grothendieck inequality, we could also show tightness of our inequality. And this ends the proof of our technical lemma. So let me conclude, start with the conclusion. So we have shown equivalence between quasi-random properties, expansion and uniformity for irreducible covariant channels. And why are these, maybe I haven't mentioned this, but these are quasi-random properties because channels, so Hastings actually showed that when you pick random unitaries, they give us with high probability quantum expanders. And likewise, we can show this for uniformity. And for, so this is why it's called quasi-random. And we showed that it is, these two properties are equivalent for the subset of quantum channels that are irreducible covariant. We have done this through our main technical lemma, that the S2 to S2 norm of phi, or the operator norm of the Choi matrix of phi, is at most 2 times the infinity to 1 norm of phi, and shown that this inequality is in fact optimal. But what we weren't able to show, and this we leave as an open problem, is that if phi is epsilon uniform, then phi is lambda expanding with lambda at most 2 pi squared epsilon, and this 2 pi squared, we don't know if this is optimal. We know that the individual inequalities are optimal, the 2 and the pi squared, but the combined constant we couldn't resolve. So this we leave as an open problem. And also it might be interesting to look at more quasi-random properties from Chang, Graham, and Wilson's work. For example, they had 7 properties, but let's look at one of these. They showed that if the count of 4 cycles in a dense graph is right, then you're equivalent with the spectral expansion and uniformity. And one could be interested in how could you generalize this 4-cycle property. This 4-cycle property is really this combinatorial property of a graph. And this could be interesting research directions. And with that, I would like to conclude my talk. Thanks a lot.
Thank you very much, Farrokh, for this very nice talk. So we have 5 minutes for questions. So I see there are already 2 in the chat. Can you see them, or like do you want?
Oh yeah,
okay, I see you can see them. So yeah, maybe the first one slightly off topic, but if you have anything to say about it.
Yeah, I would really refer to this excellent survey by Lineal, Houri, and Wigdersen. I think I have written it. Let me go back to the, so you can grab the reference. It's really a very good survey. It's this one by Houri, Lineal, and Wigdersen. And then there they talk about many of these things, about the applications and many references in there. So my suggestion is to really look at their paper and find references in there.
Okay, and then so there is also another question going maybe also a bit beyond the scope of your talk, but if again if you have anything to say about it.
No, we haven't looked at a diamond norm actually, no. But yeah, not sure what to think of.
Okay, thanks. Maybe want to let a bit of time for people to potentially ask more questions. I will ask a question of my own.
Okay.
So one thing you said at the beginning, and that maybe you didn't talk afterwards in your talk, is that you prove a similar result of like equivalence between expansion and uniformity for like randomizing channels. That would be the equivalent of dense graphs, if I understood well. And the techniques there, are they like based on this like non-commutative growth-indic inequality or not at all? Is it?
No, this one. So for a randomizing channel, it's a little bit simpler. You could so for us, so randomizing channels are channels for which this 1 to infinity norm is small, and this corresponds to also to the dense graphs, where also you can show that dense graphs have the property that their adjacent matrix have that the 1 to infinity norm is small, and then you can simply use the proof of Chang-Graham using this observation about 1 to infinity norm, and simply generalize their idea to get the statement for randomizing channels.
I see. And then, well, if I may, since I still have 2 minutes, I will ask another question.
Sure.
Like, so what's interesting, like, is that, so you showed this equivalence between these two concepts. So is it the case that uniformity would be somehow an easier condition to check, and would it? I mean, does your result imply that we would get like new constructions of like quantum expanders? Because I mean, as far as I know, like the example that we have are basically random graphs that are good quantum random channels that are good quantum expanders, and like would this allow? Like showing that uniformity is equivalent to expansion to have new constructions of good quantum expanders?
Yeah, so this equivalence is really for irreducible covariant channels. So we should look at the subset of irreducible covariant channels and checking that they are epsilon uniform from an algorithmic point of view. I haven't thought about that.
Yeah, maybe one condition is not really easier to check than the other one. I don't know. I was just
exactly yeah, maybe it's interesting to think about that. Yeah.
Okay. So I don't see any further questions. So I mean, I redirect everyone who'd have like later thoughts to the Slack channel. Thank you again, Farrokh, for this great talk.
No problem.
And we will move to the next talk. So by Ludovico Lami. If you can please share your screen. Okay, perfect. So the next talk will be given by Ludovico Lami on convergence rates for the quantum central limit theorem. Please go ahead.
Okay, thanks, Srijita, for the introduction, and well, thanks everyone for tuning in. Okay, so right, so the topic today is this quantum central limit theorem, which I'm going to define, of course. And so the first ingredient to define it is this, is to define what we mean by convolution of quantum states, right? In particular, of continuous variable quantum states. This will be an important ingredient in translating, if you want, the classical central limit theorem to its quantum version, because convolution of quantum random variable is really at the base of the central limit theorem. Okay, so then I will present basically one of the first quantum central limit theorems that have been found. This was by Cushion and Hudson in 1971. And so then I will move on to discussing extensions and refinements of those, of the theorem. And so in order to do that, I will define moments of quantum states. And then this will allow us to state our main result, which tells you how fast the convergence in the quantum central limit theorem is. Okay, so this is a quantum equivalent of the Barry-Azine theorem. And then we will look into some applications to what we call cascade channels, the type of quantum channels that we'll define later. Okay. Okay, so a bit of let's brush up on continuous variable quantum systems. They're just finite systems of harmonic oscillators, quantum harmonic oscillators. So you know the Hilbert space is just a space of square integrable functions over a Euclidean space. There are this creation and annihilation operators that satisfy the canonical commutation relations that you all know very well, I guess. So, and an important operator is the total photon number operator, which gives you exactly the total number of excitations or photons, right? If you quantum optics language in your system. So the total energy of the system. So, and using this creation and annihilation operators, you can also construct a very special family of unitary operators called displacement operators. They are just, if you want, unitary evolutions generated by Hamiltonian zeta linear in the creation and annihilation operators. Okay, so it's a unitary operator, and indeed it performs a displacement in phase space, if you know what I mean. If not, don't worry. So once you have this displacement operators, you can define a characteristic function in pretty much the same way as you do in classical probability theory, right? In classical probability theory, if you have a random variable, you define a characteristic function as the expectation value of e to the I t transpose x. Okay, so this would be just the Fourier transform of the probability distribution. And so in the quantum case, we define a characteristic function as the trace of your state rho against the displacement operator. Okay. And so what happens in the classical probability theory is that if your random variable has finite first and second moments, this is equivalent to the characteristic function being twice differentiable at 0. Okay, and so that means that you have can Taylor expand the characteristic function at 0, like 1, which is the value at 0, plus a linear term in t, plus a quadratic term in t, plus a remainder. Okay, so in quantum theory, it turns out everything still holds, like the whole thing carries over to quantum theory. So if your rho has finite total number, this is equivalent to the characteristic function of rho being twice differentiable at 0, and so having an expansion with a linear term, quadratic term, and a remainder. Okay. Right, so the simplest form of the classical central limit theorem, if you want, is this, that you have a bunch of IID random variables that are actually random vectors in a Euclidean space with 0 mean and a finite variance, so a certain covariance matrix. And then you define this kind of normalized mean. It's not exactly the mean because there is a 1 over square root n instead of a 1 over n. So it's the normalized mean, if you want. And so this converges in distribution to a multivariate normal random variable. Okay, this I guess you all know. Right, so I mean, we know what replaces random variables in the quantum setting. It's just you have a IAD M mode quantum state, right? So since it's IAD, it will be just a tensor product, rho tensor n copies of rho. First and second moments are finite. That amounts to having the trace of rho against the displacement, against the creation and annihilation operators being 0, and then the total photon number being finite. Okay, this is just second moments are finite. And indeed, up to linear transformations, you can bring them. So in the classical setting, you can bring the characteristic function to this very special form that's very well known. And so in the same way, up to symplectic unitary transformations, if you don't know what symplectic means, don't worry. And there is a special unitary transformation, the quantum setting, that allows you to bring the characteristic function to this special form, okay? And you will see that this is slightly more complicated because you have this new J factors, coefficients there that cannot all be supposed to be 1, and this is because the value of h bar has to be the same for all modes, so that you can redefine h bar separately for each mode. That's at the basically at the root of this of the fact that you have this new J coefficients. Okay, so now we want to translate the concept of normalized sum into the quantum setting, and this is not clear how to do, right? Not yet. Okay, so let's move on to discussing this. So right, so suppose you take a number between 0 and 1, and you want to define a normalized sum of variables, of random variables, right? Independent random variables like this. So then what happens is that the probability distribution will be just a convolution of the two probability distributions, and the characteristic function then, since it's the Fourier transform of the probability density function, will be just the product, the normalized product of the two characteristic functions. Okay, so that's very important. So, and the way to generalize this to quantum states has been found by Koenig and Smith, actually relatively recently. So, and it turns out to involve a quantum optical element known as a beam splitter. So what happens is I mean, there's a very well-known object in the lab, actually. So what happens is that you feed in your two input arms of the beam splitter, your states rho and sigma. This beam splitter will have a certain transmissivity, lambda, between 0 and 1. So you trace out one of the two output arms, right? This gray thing is just a trace out, just like trash the state. And so you keep the state in the other output arm, and that will be your convoluted state, okay? So, I mean, so the unitary operator that implements the beam splitter can be written explicitly. And what it does is that it transforms the creation and annihilation operators by taking exactly the scaled sum of them, scaled sum of the input creation and annihilation operator. So that's already a hint that what we are doing is, well, what Koenig and Smith were doing is the right thing to look at in the quantum setting. So, and indeed, what happens is that if you look at the characteristic function of the convoluted state, it has exactly the same form as in the classical setting, precisely the same form. Okay, so it's just the product of the two characteristic functions of rho and sigma rescaled with this square root lambda, square root 1 minus lambda. Okay, so great. We are doing kind of the right thing. So if you want the most immediate translation of the classical central limit theorem to classical convolution to the quantum setting. Okay, so that's the table. We now know what takes the place of the normalized sum. That would be, so since we have n variables, and I discussed just the convolution for 2 of them, we want to actually do a symmetric convolution. So you just take the rule that I gave before for the characteristic function, and you just generalize it. So you just take n times the characteristic function of rho rescaled. Okay, that's pretty much it. So what is that takes the place of a normal random variable? Well, I mean, normal random variable can be defined as something whose characteristic function is like a Gaussian. And so a Gaussian quantum state can be defined in exactly the same way. Something whose characteristic function is a Gaussian, okay? Here I wrote just with no linear term because this is the case we care about. Great, so now we're ready to discuss Cushion and Hudson original quantum central limit theorem. So that tells you that if you have an M-mod state with vanishing first moments, that means exactly that the trace of rho against the creation and annihilation operators is 0, and finite second moments. Yeah, I forgot. Second moments means exactly that the total photon number is finite. Yeah, that just should be minus less than infinity, right? So then the symmetrically convoluted state converges in trace norm to the Gaussian state, okay, that I wrote before, the one with this characteristic function. So what we call also the Gaussification of rho. Okay, so just take the Taylor expansion of the Gaussian state whose Taylor expansion of the characteristic function is the same as the one of rho up to second order. Right. So I mean, actually, in the original theorem by Cushion and Hudson, they didn't state it like this with a trace norm. They stated with a slightly weaker form of convergence, but it's actually relatively easy to show that the two are equivalent. Okay, so I will skip the proof since, okay, we don't need it, but it's fairly easy. It's not a particularly cumbersome proof. And just goes in analogy with the classical case. Okay, so but this is a stronger case, a stronger statement than the classical one, because we have a stronger notion of convergence, right? So convergence in distributions for classical random variable is relatively weak with respect to, say, convergence in total variation norm. And here we have the, if you want, the quantum analog of the total variation norm, I mean the trace norm. So this is, it's actually stronger. And so, I mean, you can also show that this assumption of finiteness of second moments cannot be weakened to finiteness of some moment of order less than 2. Okay, and it turns out to be a counterexample. So, and now our goal from now on is to bound the speed of convergence of this object to of the difference between the symmetrically convoluted state and the Gaussian state to 0. Right. So, I mean, in the classical setting, that turns out to be a Bézier theorem that provides some information on this. So I stated this just for a real case, so a dimension 1. So, and then the main assumption there is that you assume to have finite absolute moments of order 3. So, and then provided that this holds, you have a bound on the speed of convergence, okay, with respect to some distance that I'm not going to discuss. And the speed of convergence is 1 over square root n. Right. And so in the quantum setting, we hope to do better, to say something about maybe the trace norm, a trace norm difference. And this will turn out to be not so easy. So what we will do first is to give a bound on the 2 norm difference. Okay, so first of all, we need to define moments of quantum states, higher moments of quantum states. Well, so the way to do it is, and there are several ways to do this, and we discuss at least 2 in the paper, but let's stick to 1, the simplest for now. Let's say that a state, an M-mod state rho, has finite moments of order up to k if the trace of rho against the total photon number raised to the power of k over 2 is finite. Okay, so that means exactly that the total photon number probability distribution has a well-defined moment of order k over 2. So this k over 2 is because the total photon number is already a quadratic object, if you want, the creation and annihilation operator. So you need to incorporate this this 1/2 fraction. So okay, so one of the main technical lemmas that we prove, not one of the main ones, but a challenging one, at least to me, is the fact that if a state has finite moments over the k, then it turns out that also the characteristic function is k-fold differentiable at 0 and also everywhere, it turns out. So this is in total analogy with the classical case, but here non-commutativity really makes your life significantly harder. And you can also extend this and include a case of a non-integer k, so in which case you have integer part of k derivatives, plus you also have some regularity conditions for the fractional part of k. It's very useful. And yeah, I mean, the only way we found to prove this is through this. I mean, you have to go through some operator inequality. So like this example, and it's not particularly easy to prove actually. So you have to bound the sum of the kth power, absolute power of x and b, the coordinate and the momentum, in terms of the total photon number. Yeah, it's not particularly immediate, but okay, it turns out to hold. So so far so good. Right. So now we are ready to state the quantum Bézier theorem, which is the main theorem that we give. I mean, we give several, but that's a simple form of one of them. Okay, so we have an M-mod state with vanishing first moments and finite moments of order up to 2 plus alpha. Okay, so again, we cannot go below 2, we will go above 2. Okay, and alpha would be a positive number between 0 and 1. So to fix ideas, you can also assume it's 1. So you have finite third moments. So then what it turns out is that you have a finite convergence rate of order 1 over n to the alpha divided by 2 in the 2 norm. And then to go to the 1 norm, you pay a price, which is increasingly high when you go to a high number of modes. Okay, so you get a significantly lower speed of convergence, but still a power law. So what we can prove is that the 2 norm, and prove, I mean, you can give numerical examples that are pretty compelling that show that the 2 norm estimate is tight, and we don't know about the 1 norm estimate actually. We suspect it's not tight in general, but we don't know that for sure. And so sometimes one can do better. It's not that this is always the optimal result for every state. For instance, if the third derivatives of the characteristic function of your state vanish at 0, which, for example, happens for Fock diagonal states that are pretty common in the lab, and the fourth moments are finite, you actually can double the speed of convergence. Say the 2 norm, you get a 1/n convergence rate. That's very good. But in general, this is the 1/√n, say for alpha equal 1, is tight. Okay, so let's discuss last 5 minutes. Let's discuss some applications to what we call cascade channels. Okay, so this application will show that this kind of nice setting, if you want, of the quantum central limit theorem is not useless. So suppose you want to model an optical fiber with that experiences, whose signal experiences a sequence of losses. So each loss would be modeled by an elementary attenuator, where you plug in your signal state and mix it with an environment state, which would be your noise rho in a beam splitter of transmissivity lambda to the 1/n. So this exponent is there because you have n elementary attenuators. So your global signal will experience a total transmissivity of lambda, okay? Or if you want a total attenuation of 1 minus lambda. Right, so the widely studied case here is when rho is a thermal state. Okay, so when rho is a thermal state, it turns out you can make the whole, or even the vacuum, which is even more studied. It turns out you can make the whole sequence of attenuators to collapse into a single effective one. And so in this case, when the noise state is thermal state or the vacuum is very well studied, we know a lot about the capacities of the resulting channels, both classical and quantum, but we know actually how to compute the classical capacity for the thermal attenuator. So that's it's very good, right? So we know a lot of things about this. So we want to study the model where rho is a generic state, not just a thermal state. Okay, so if you write the action of this, you will see that an elementary block will act like this, so like with an elementary attenuator. So then if you iterate n of those, you will have this nested sequence of attenuations, which looks pretty nasty, until you realize that you can actually write this as a single attenuation of your signal with total transmissivity, which is the product of the elementary transmissivities, and this rho bar effective environment state. If you want to write down this characteristic function of this effective environment state, it turns out to be a product, a kind of scale product of the elementary functions. Right. Oh gosh, what happened? Right. So it turns out to be an elementary product of the elementary functions. So if you go to the classical analog of this, you will see that you get basically a geometrically weighted average of your classical random variables. Okay, so that's kind of the quantum equivalent of this with this weight operation. So what we want to do is we want to study the properties of this cascade channel in terms of the properties of the Gaussian attenuator for large but finite n. Okay, right. So I mean, there is an extension of Cushion-Hudson that is well, I mean, it's very kind of straightforward that we also prove. I mean, it's very easy that this effective state converges to the Gaussian state again, to the Gaussification of rho. And so if you can establish like rigorously some rate of convergence, you can compare the channels, the cascade channel with its limit, which is the Gaussian attenuator for large n, right? So this will tell you something about the cascade channel for large n. So indeed, so let us state the theorem, the single mode case. You have a state with vanishing first moments and finite third moments. Then you can say something about the convergence rate of your cascade channel to the Gaussian attenuator in terms of the diamond norm distance. Okay, so the diamond norm distance, don't worry, it's just a distance measure between channels, and then you get a square root 1 over n to the power of 1 over 4, 1/4, right? Convergence to the Gaussian attenuator, and you can use this to bound the classical and quantum capacity of the cascade channel in terms of those of the Gaussian attenuator, right? You will have a fixed input energy E, and for a fixed input energy E, you will also have a convergence of those capacities to the capacities of the Gaussian attenuator. Okay, so that's important. If you don't know what the classical and quantum capacity are, it's just a way to measure how much classical and quantum information you can send through the channel. So these are important concepts, yeah, experimentally and theoretically also. Okay, so summary. This is just a table we tested you with, right? So now we know how to fill in the last entry that I presented. So one possible generalization is the result I presented. And also we discussed this application to cascade channels on how to approximate a cascade channel made of many elementary beam splitters with a Gaussian attenuator. Right, with that I thank you. And I will take questions if there are.
Okay, thank you very much, Ludovico, for this very nice talk. So, okay, for now, I don't see any questions yet on the chat, so maybe I will start by asking one until people have time to write some if they want. Okay, so maybe one technical question. So you said, like, at the beginning, maybe you were aiming at like measuring distance like in one norm, and in the end you get you could only get a nice result in two norm. So just to understand a bit better, so for the one norm result that you showed, you get a parameter that depends on the number of m of modes, right? And do you know if this is like just an artifact, like just because you just bounded things in a very rough way, or is this appearance of this M really needed, or are there cases where you cannot do better than this?
Yeah, thanks, Srijita, for the question. Actually, we don't know. We don't know. I mean, we know that, as I said, that two norm convergence rate is kind of tight, but the one norm, we don't know. So it may well be that this is just an artifact of the fact that we go through the two norm to bound the one norm. And that's, I mean, it's the only way we found, because right, I mean, with the two norm, you can actually apply Plancherel identity and go to the characteristic functions. And there we have a lot of tools to analyze those. But yeah, with one norm, we don't know. Short answer. It would be very interesting to know, of course.
Would it imply some more results, like some more applications than the one you mentioned?
Right. I mean, there you will have a stronger convergence rate there. I mean, which would perhaps be important experimentally, right? So, but I mean, formally, you still get a convergence even between trace norm, and you can even say something quantitatively. It's just the rate will be better. So
I see. Okay, so actually there's a question that appeared, so I guess you can see it, but let me read it loud. So by Masaito Hayashi, maybe I overlooked an important point. The original quantum central limit theorem addresses rho tensor n. However, you address a rho to the power square n, so this convolution. I would like to know the relation between these two quantities.
Right. So I mean, so yeah, I mean, the symmetric convolution is it's a state in the same system, if you want, as rho. So it's not a tensor product. It will be. So you can obtain it from the tensor product of rho n times by applying an n splitter and tracing away all but one output system. Okay. So indeed, it's a more specialized scenario, if you want. I mean, you don't address rho tensor n, but you address one of these partial reductions upon applying an n splitter. So, and yeah, but really in this case, it's not that easy to give convergence rates. So it's in a way, it's the simplest setting, if you want. But there, you have to struggle a bit.
Okay, maybe a related question, and then we will wrap up. So second, you discussed the one norm distance between rho convoluted n times and rho g, where this rho g is a state on a Fock space. I could not find how this rho square n can be considered as a state on Fock space.
Right, exactly. I mean, I didn't prove this very well. Good point. So, so yeah, I mean, I just gave the characteristic function, and then I asked you to trust that this is actually a quantum state. Okay, and I didn't prove this. Turns out it's not difficult, and and this is what I was saying before. So you just have to take rho tensor n, apply a unitary operator, which is an n splitter, if you know what I mean, and then trace out all but one systems. And that shows you that you get actually a quantum system, a quantum state. So and another way is to iterate kind of the elementary convolutions that I gave you. Those I proved that kind of prove that you get a quantum state. So if you iterate those, you get a state with this characteristic function. So that also shows that this is a valid quantum state. But you're totally right, I didn't prove this. That's not difficult actually. Anyway.
Okay, thanks a lot. So I suggest we move all further questions to the Slack channel. So thanks again, Ludovico, for this night.
Thanks a lot.
And let's move on to the last talk of this session that will be given by Gerardo Adesso on extendibility of bosonic Gaussian states. Please, Gerardo.
Okay. Let's see if you can actually... Do you see my screen? No.
Yeah, it looks perfect.
With the presentation. Okay, perfect. Okay, good morning, everyone. Thanks a lot. Thanks so much for accepting my contribution to TQC. Actually, this was submitted by Ludovico, but because he was already giving this other talk, then eventually I stepped in. So this work was done in collaboration with him when he was my postdoc in Nottingham last year, and then Mark Wilde and Sumeet Khatri at Louisiana State University. So the topic of the talk is about extendibility in continuous variable systems. And more generally, we can start by looking at the following question. Is entanglement monogamous? That's the title of a paper by Barbara Terrell from 2003. And this notion of monogamy of entanglement has been studied a lot in various forms over the years. Now, in a very strong form, entanglement is clearly monogamous, and we can express it like this. So if Alice and Bob share a maximally entangled state, then there's no chance they can have a polyamorous relationship with anybody else. So they cannot share any entanglement with a third party, Charlie. But what happens in the case in which they only share some partial entanglement to each other? So suppose we have this interesting situation where there's Alice and then there are lots of Bobs around, let's say. And if Alice and each of the Bobs share some partial entanglement, is it possible that this entanglement is repeated between Alice and all of those Bobs? So if Bob is not just to one, can Alice be related to all of them? So this seems like a sociological question, but actually this question can be formulated mathematically in a clear way. And this is the problem of K-extendibility. So it is formulated as follows. If we start with the bipartite state, rho AB of Alice and Bob, does there exist a bigger state of Alice and K subsystem Bobs, such that the marginal of this larger state that we would call rho tilde between Alice and each of the Bobs is equal to the original state rho AB? That is the K-extendibility question. So if this question has an affirmative answer, then we would say that the original state is K-extendible, and this larger state rho tilde is its K-extension. Oh, sorry about this now. I think there was some delivery possibly. Okay, why is this related to the monogamy of entanglement? Well, because we can classify all quantum states in terms of their K-extendibility property. So of course, if a state is K-extendible, then it's also K-1 extendible, but it might not be K+1 extendible. And so you have this nested structure where you have all states, including those which are not extendible at all, and then 2 extendible, 3 extendible, and so on, until you reach states, the smallest set is states that are extendible for all values of K. So they're infinitely extendable. And what was characterized about 20 years ago in some pioneering work was the following result. A bipartite state rho AB is separable if and only if it is K extendable for all values of K larger than 2. So in this very precise sense, entanglement is monogamous because separable states are the only ones that can be infinitely shared on one side. Any other state, as long as it has some entanglement, then it might be extended, but not for all values of K. So it is interesting then to characterize the middle ground of these k extendable states, because they form iterative approximations to the set of separable states, and they might give information about quantitatively how much a state differs from a separable state. So they might be related to the amount of entanglement and not just the structure of entanglement in a given quantum state. Now, this problem is also interesting for quantum information perspective more generally, because it's a particular case of the so-called quantum marginal problem, which is the problem where you give a set of marginals and then you ask whether there exists a big density matrix that is compatible with all those marginals. But that problem is hard. It's known to be QMA complete, and it's also being considered in quantum chemistry under the name of n-representability problem. Of course, the specific K extendibility problem is a special case because there's a lot of symmetry. So the K extension has to have permutation invariance between all those bobs. So those marginals, they have a high degree of symmetry. And for this reason, the problem is simpler to characterize. So it's not QMA complete, but actually can be solved in terms of a semi-definite problems, an SDP. So for a given state and a given K, you just need to find this K extension density matrix such that the marginals obey the required property. So being an SDP, this problem is at least numerically solvable, but still it becomes not so efficient when you have large dimensions for the subsystems and also when you have large values of K. So it would be nice to have close analytical solutions, but these are only available for some particular classes of states or some values of K. For instance, to give you an example, for 2 qubits, you have a complete characterization of 2 extendibility. A 2-qubit state is 2 extendable if and only if this relationship between the global and the marginal purities and the determinant of the density matrix is satisfied. So the problem becomes more intractable with increasing dimension. What do? We just take it to the extreme, and we want to study this problem in infinite dimension. So the previous talk already introduced you some notions of continuous variable systems, and what we will do in this talk, we will tackle as much as possible the K extendibility problem for infinite dimensional states, and in particular for the subset of Gaussian states. So we do not do exactly only results for Gaussian states. So if I have to anticipate a bit more of what I will present in this talk, we will derive some analytic necessary condition for K extendibility of any continuous variable state, Gaussian or non-Gaussian. These conditions become necessary and sufficient in the case of Gaussian states and take the form of a very simple SDP. We get a closed analytical criterion in the specific case in which the mode, the subsystem on which you extend, so Bob subsystem, is made of only one single mode. This condition allows us to characterize K extendibility also for channels, not necessarily only for states. And so we have a nice representation of all K extendable Gaussian channels, in particular in the one-to-one mode case. And then, as I said in the beginning, this allows us to give some quantitative estimate on the entanglement of K extendable states in the form of some definite type bounds. All right, so let me start. Luckily, you already got a little bit of introduction to continuous variable systems in the previous talk. Let me just set the notation that we will use in this talk. So a continuous variable system is a chain of n harmonic oscillators, the modes of a quantized field. And we can represent the field quadrature operators like position and momentum for each of those modes and arrange them into a vector where you have the 2 operators for mode 1, then for mode 2 up to mode n. And they obey the canonical commutation relations that you can compactly write in matrix form, introducing this block diagonal symplectic matrix omega. Right, so it is convenient to introduce quadratic Hamiltonians, which are those Hamiltonians that are indeed quadratic in terms of the field quadrature operators. These are, for instance, the Hamiltonians that describe a beam splitter and all the other linear optical elements that you can implement in the lab. So given this definition, then you can define the subset of Gaussian states as the states which are ground and Gibbs thermal states of all quadratic Hamiltonians. And you can describe them in the phase space in terms of quasi-probability distributions such as the Wigner distribution. And of course, by definition, these distributions take a multivariate Gaussian form in phase space. And so, as such, they are completely specified by the first and the second moments of the canonical operators. So the first moments, they just contain the means of these position momentum-like operators. Now, in this talk, we will assume that we have implemented local displacement so as to set these first moments to 0, because they're completely irrelevant for the purpose of characterizing K extendibility and entanglement of continuous variable states. So the only information that we will care about will be contained in the second moments that are collected in this covariance matrix. Now, the covariance matrix will correspond to a physical state in Hilbert space, provided this matrix inequality is satisfied. V minus I omega, where omega is the symplectic matrix, is a semi-definite positive matrix. Now, this is sometimes referred as bona fide criterion, and it comes from a combination of canonical commutation relations and Robertson-Schrödinger uncertainty principle. Very well. Gaussian states, I like them well. I've been working with them for 15 years. And so they are treatable theoretically, of course, because they are specified by a small subset of parameters as opposed to infinitely many for a general continuous variable state. But they also correspond to what many laboratories can easily implement in quantum optics, optomechanics, called gases, vibrational modes of trapped ions, and so on. Right, so let's look at this problem of K extendibility for continuous variable states. If we have a bipartite state of NA modes on the A side and NB modes on the B side, its covariance matrix this state might be Gaussian or non-Gaussian, but we will just look at the second moments for now. So its covariance matrix can be written in this block form, where VA is the reduced covariance matrix for the subsystem A, VB is the reduced covariance matrix for subsystem B, and this X is a matrix of correlations between the two parts. Now, if this system, if this state is K extendable, then its K extension, rho tilde, will have a covariance matrix that we can write in this form, where, of course, this is the original state, and then you can see that all of the bobs need to have the same reduced covariance matrix. All the correlation matrix XX transpose needs to be the same, but crucially, all the correlation matrices between the different bobs on the extension side, they have to be the same and specified by a matrix Y, which has to be symmetric. You can show this. So if there is such a K extension, its covariance matrix has to describe a physical state. So it has to satisfy this bona fide condition here. And so one of the first crucial results that we find is that, and that's a consequence of the quantum central limit theorem that we have seen in the previous talk, a Gaussian state is K extendable if and only if it has a Gaussian K extension. So for Gaussian state, the necessary condition on the previous slide becomes sufficient as well, because it fully specifies the K extendibility, because it's only described at the level of covariance matrices. But more generally, then we have that condition is necessary for any continuous variable state, but can be checked just by checking the second moments. And so this problem can be described as an STP, which scales linearly with the number of modes on the extended system. It's a feasibility problem, whether you have to check whether there exists a matrix Y such that this enlarged covariance matrix that is constructed as a function of Y is a physical covariance matrix. Now, this expression already defines the problem, but it can be massaged a little bit in order to get something a bit more easier to handle, and that will be our first main result. So given a bipartite state, which is Gaussian or non-Gaussian, if it is K extendable, then there exists some matrix whose dimension is 2NB by 2NB, where NB is the number of modes of the B system, such that it is a physical covariance matrix itself, and it enters in this matrix inequality. So the original covariance matrix of the state satisfies this inequality, where on the A side is just physicality, and on the B side there is some combination involving this matrix delta and the symplectic form. This condition is necessary for any continuous variable state, but it is necessary and sufficient for Gaussian states. In the specific case in which number of modes for B is 1, then you can get a closed analytical expression for this criterion, and it is given as follows. So bipartite Gaussian state with one mode on the p side is k extendable if and only if its covariance matrix satisfies this matrix inequality. So you don't have to find the existence of another matrix, you just have to check this straight away. So it is comparable to the 2-qubit case that I described at the beginning. It's a closed analytical solution. Very well, so what can we do with it? I don't have time to prove it, but just want to say that one of the main ingredients that we use in this proof is the Schur complement, which is something that particularly the previous speaker likes a lot and has been using with me a lot in the study of Gaussian states. So we want to see whether there exists, if it's k extendable, then there exists this matrix Y such that this big covariance matrix is physical. So this difference of matrices is semi-definite positive. Now, the Schur complement theorem says that matrix is semi-definite positive if, say, the top left block is semi-definite positive, which is true by construction because VA is physical, and the Schur complement with respect to this block is semi-definite positive. And this will be constructed by taking the red bit minus this bottom left times inverse of the green times this top right. That's the Schur complement. You write it, you play with it, you do some other things that the previous speaker can explain better than me, and then you get to the final result. Well, we have defined this delta B as the difference VB minus the matrix Y. So let's get back to the results. The Gaussian state is k extendable if and only if there exists delta such that this is satisfied. And in this way, we have the complete characterization of all the layers of extendibility within, let me see what's going on, 5 minutes, okay, within Gaussian states. So in particular, if we take the limit k going to infinity, then you recover a known result, which is a necessary and sufficient condition for separability of Gaussian states, given in terms of this matrix inequality, which was obtained recently in a paper again by Ludovico, myself, and Alessio Serafini, simplifying some known criterion by Werner and Wolf. Great, so what can we do now? We want to obtain some quantitative bounds on the entanglement. So intuitively, if a state is k extendable with increasing k, then it should be closer to being a separable state. This can be quantified exactly. So in the paper, we obtain bounds on various distance measures between k extendable states and separable states. One of them is very simple, is this one. So in trace norm, any k extendable Gaussian state, its distance from the set of separable states is bounded by a function which scales linearly with the total number of modes and is inversely proportional to k. There exist similar results for qdits, where this bound scales with the square of the dimension and then again inversely proportional to k. And we have other results for relative entropy that contain lots of logarithms, so I'm not going to write them here. But we can also obtain bounds on entanglement measures that are not defined through distances. For instance, one of the nicest results is in terms of the entanglement of formation. So for any k extendable Gaussian state, we know that its entanglement of formation is bounded from above by a function that depends on the number of modes and depends on the purity of the state. So this determinant of VA is related to the purity and is bounded by the mean energy of the state. So the previous bound didn't depend on it, but this one, yes. So the entanglement of formation is bounded from above by a function that is inversely proportional to k, as we intuitively expect, but depends on the purity of the state. Very good. Let me just, because my time is almost up, let me just go through some, quickly, some other applications of this result. One application concerns not entanglement, but something stronger than entanglement, which is EPR steering. Interestingly, there is a relation between 2 extendibility and steerability from Bob to Alice by use of Gaussian measurements. And the result is as follows. If a bipartite Gaussian state is 2 extendable, its entanglement basically is not strong enough to allow for steering. Indeed, it's not steerable from B to A by using Gaussian measurements. And if NB has one mode only, then this is actually necessary and sufficient. So there's an equivalence between unsteerability by Gaussian measurements and 2 extendibility when the Bob system is one mode only. And another application is we can use our criterion to test some states for which we know other interesting properties, like a bound entangled Gaussian state of 2 modes versus 2 modes. Interestingly enough, you sometimes think the bound entanglement is weak, but this example that was studied by Werner and Wolf in 2001 actually is not even too extendable. So its entanglement this state is quite far from the set of separable states. It cannot be extended. And another application concerns channels. So we can study Gaussian channels, which are channels that map Gaussian states into Gaussian states. And at the level of covariance matrices, they are specified by two matrices, one acted by congruence, X, and then an additive noise matrix, Y. And they have to satisfy certain conditions to make sure that the map is completely positive and trace preserving. And of course, you can think of a channel in terms of K extendibility. A channel is K extendable if there exists another channel from the sender to lots of receivers, such that the reduced channel from the sender to each of the receiver is the same as the original channel. And you can relate this problem to the extendibility of states by studying the choice state of the channel. So we have done this, and so we get from the previous theorem, we get a characterization of K extendibility of all Gaussian channels. And in particular, it takes a very nice form when you have channels from one mode to one mode, because we had a closed analytical solution in that case. The K extendibility is specified just by a balance between determinant of X and determinant of Y, the matrices that specify the channel, and is better visualized graphically. So this is a representation of all single mode Gaussian channel in the space of these two parameters. And what was known was that above this red line here, you have the region of entanglement breaking channels. And now we have lines parallel to this, which specify all the layers of K extendibility for the channel. So channels here are not K extendable, channels here are 2 extendable, then 3 extendable, then there are lots of lines until you reach, in the limit of infinite K, you reach the entanglement breaking boundary. And this is a nice characterization which mimics the similar nested one that we've done for states. Right, so I think it's time to sum up. In this brief talk, I provide necessary and sufficient conditions for K extendibility of all bosonic Gaussian states of an arbitrary number of modes. These conditions are necessary for states which are non-Gaussian, general continuous variable states. Our study leads to some bounds on entanglement measures for K extendable states that take the form of definite type bounds. And I think would be nice to have a closed solution rather than just an STP, even for a larger number of modes, not only when NB is equal to 1, and then investigate more applications, for instance, to bounding capacities of Gaussian channels. And I leave you with this. I'm not going to read it because I think there's no time. So that's a poem about the K extendibility problem. Given that we are romanticizing entanglement, you can read it yourself. Thank you.
Thanks a lot, Gerardo, for this very clear, interesting talk. So while I had a bit of time for people to write down the question, maybe I'd ask one. So when you showed this result, like about like the kind of definite type result that you have, so I mean, I don't know anything about continuous variable systems, so it might be very naive. This is derived from the characterization that you get at the level of covariance matrices. Like you have a way to relate what you know on covariance matrices to a distance between your, like the one norm distance between your state and the closest separable state?
Yes.
Okay. Okay, good. And well, maybe I will continue while I still let time for people to ask for the question. So about the channel application, maybe you went a bit fast on this. Maybe I missed something. So on this graph that you have, so if I understood well, so the graph for like the case K equals 2 then would be like characterizing like maybe the channels that would be kind of like degradable or anti-degradable or something like this, and then you have like this whole hierarchy up to entanglement breaking, right?
Yes, you're right. Yeah,
okay,
correct. Yes.
Okay, thanks.
Yeah.
Okay, so I see there's now one question in the chat, so let me read it loud. So it's from Hayata Yamazaki, asking, is there a simple example of non-Gaussian states for which your condition of K extendability is not sufficient?
I think I can construct some, but because it would be some state that maybe at the level of covariance matrix is product state. Its entanglement can only be detected by higher order moments. And these states are well known. So for instance, you can, even more generally, if a continuous variable state has second moments which correspond to an entangled Gaussian state, then the original state is entangled as well. But there are lots of states which are non-Gaussian whose covariance matrix maybe describes a product Gaussian state, but the original state is entangled. So all of those examples will not be detected by our criterion, because from the second moments you don't see anything. You will just see a separable state, but the original state is entangled and possibly K-extendable, but you can only detect it by checking higher order moments.
Okay, so I don't see any further questions for now, and actually our time is kind of over. So like again, I will redirect people to the Slack channel to ask all the question that they might come up with during the lunch break or whatever break it is for you in your time zone. So thanks a lot to all speakers of this session, and we reconvene in 1 hour 45 for the last afternoon of TQC 2020. Bye.
Thank you.
As it's almost 3 o'clock Riga time, we'll be starting soon. So this is a 1-minute warning for the start of the next session. Thanks. Okay, so hello everyone. It's 3 o'clock Riga time now, so let's get started with the next session of TQC. So in this session, we have 2 talks, both on the general sort of topic of algorithms. And the first talk is by Daniel Stilck França, who's going to tell us about faster quantum and classical SDP approximations for quadratic binary optimization. So Daniel, if maybe you could get going and maybe think about sharing your screen. Perfect. So great. Whenever you're ready, take it away.
Thank you, Ashley, and thank you for the organizers for organizing this great online conference. I'm also looking forward to maybe attending the conference next year in Riga. So as Ashley mentioned, I'm going to talk about faster quantum and classical STB approximations for quadratic binary optimization. And this is joint work with the great Fernando Brandão and great Richard Kueng. So let me start by giving you some context. So by now, there are already quite a few papers out there that discuss quantum speedups for STPs. So there are speedups for linear programming, shadow tomography. However, the scaling and the error of these algorithms prevented, and some problem-specific parameters prevented them from obtaining speedups for some practically relevant classes of STPs. And here in this talk, we want to address this gap and talk about quantum speedups for a very specific class of, and very important class of STPs, namely those arising from relaxations of binary quadratic optimization problems. So this class includes problems like computing the cut norm of a matrix, which is closely related to computing the max cut of a graph, and it has applications to machine learning and community detection and binary matrix factorization. And STPs with a similar flavor also appear in quantum information theory, for instance, when doing low-rank quantum state tomography. And as in other works in this area of quantum speedups for STPs, the main idea will be to develop convex optimization solvers based on preparing quantum Gibbs states. And then we use a quantum computer to prepare these quantum Gibbs states and obtain a speedup. So if convex optimization is, of course, a huge area of research, and there are polynomial time general purpose solvers for convex optimization problems, but these are slow. For instance, like the ellipsoid method runs in polynomial time, but is often too slow to actually run it in practice. So it is also necessary to develop more tailored solvers for convex optimization problems, which run faster. And in this talk, we're going to talk about the binary quadratic optimization and the convex STP relaxation thereof. So this problem consists of optimizing XAX for A, let's say a symmetric matrix, and X a vector of sign. So this is just plus minus 1 entries in this vector X. And of course, we can rewrite this as trace A X X star. And this problem captures many widely studied problems. For instance, computing the ground state energy of a classical spin system can be cast as a quadratic binary optimization problem. Community detection, max cut, many very widely studied problems can be cast as a binary quadratic optimization problem. And of course, these problems are NP hard to solve, even to a constant multiplicative error. So you can see this by noting, for instance, that max cut is contained in this class. Okay, and what is the standard STP relaxation of this problem? Well, as mentioned before, we can, instead of write this problem as maximizing trace A X X star. Instead of writing it this way, you can also write it as it on the right of the slide. You can write it as maximizing trace AX, such that X is a positive semi-definite matrix. Its diagonal has to have 1 entries, and the rank of X has to be 1. So this is just rewriting what is on the left. And on the right, we see that we have 3 constraints. The first 2 ones are actually convex constraints, linear, actually, so they are easy to deal with. The last one is the nasty one, is the rank constraint. So we obtain the STP relaxation of these quadratic binary optimization problems by just dropping this last constraint. Of course, whatever we obtain by solving this optimization problem will give us an upper bound on the original problem as we dropped 1 constraint. And a very nice aspect of these relaxations is that there are randomized rounding techniques that tell us that the value of this relaxation also will give us a multiplicative lower bound the optimal value of this problem. And in some instances, you can even prove that this ratio is close to being optimal. So in some sense, this is a very good relaxation, which can be solved in polynomial time from the problem on the left. Okay, now so far things do not look very quantum. So let's make this problem look a bit more quantum. So the first step is to realize that we can just normalize our state, our set of feasible states. So instead of requiring that the diagonal is equal to 1, we just require it to be 1 over n, where n is the dimension. So we now see we are optimizing over the set of quantum states, which look like the maximally mixed state when measured in the computational basis. And moreover, we normalize this operator H, have operator norm 1, so that it looks more like an observable. And what will be really fundamental to obtain the speedups we mentioned here is that we further relax this diagonal constraint. So again, by taking, let's say, a quantum point of view, a very natural relaxation of this diagonal constraint would be to relax to states that look like the maximally mixed state when measured in the computational basis up to some error in total variation distance. So whenever we measure the states in the computational basis, we see something which looks like the maximally mixed state up to some error epsilon and total variation distance. And by doing this further relaxation of the problem, we now have, instead of having n constraints, we have one constraint instead, which is this total variation distance you see here. You can check this constraint much easier than the one we had before, and also to a higher degree of precision in some sense. So further relaxing the problem in this way is actually key to obtain the speedups we're going to discuss later. Okay, now let us just discuss the general strategy we're going to follow now to obtain speedups. First, we're going to do some very standard reduction from solving an optimization problem to a feasibility problem. And then we're gonna just talk about a quantum-inspired meta algorithm to solve the aforementioned feasibility problem, which will be based on preparing quantum Gibbs states. And then we're gonna use a quantum computer to do that last step more efficiently. And these algorithms are inspired by the matrix multiplicative weight methods, or more precisely, the mirror descent algorithm, which allows us to solve these optimization problems also without having to talk about the dual SDP. So we're only, using mirror descent allows us to only focus on the primal problem. Okay, so I'll just note that you can actually reduce the problem of solving the optimization problem we mentioned before to solving a feasibility problem instead, which just asks, is there a quantum state such that trace A tilde, where A tilde is just a normalized matrix A, is smaller or equal to lambda, and then you just solve this problem for a couple of values of lambda. And this allows you to also solve the binary, the original optimization problem. So this is a standard reduction from optimization to feasibility. And well, let's maybe get some intuition why writing everything in terms of Gibbs states could actually be a good idea. If you look at the constraints we have, the diagonal constraint and the trace A tilde x smaller or equal than lambda, these are linear. These are very easy to check and enforce somehow. The only annoying constraint is somehow that x is positive semi-definite. And one way of making sure that this is the case is by just writing x as the exponential of some Hermitian h or minus h. Because in this way, I mean, first of all, any positive semi-definite matrix can be approximated arbitrarily well by such Gibbs states, and by writing it this way, positivity follows immediately. So instead of optimizing over the matrices X, we're actually going to optimize over these matrices H, which can be naturally interpreted as Hamiltonians. So what is then the general idea. At each step, we're going to check, we're going to start at infinite temperature. So we set our initial guess for the Hamiltonian to be 0, which gives us the maximally mixed state, right? And then we check if the constraints are satisfied or not. So we look at this is going to be an iterative procedure. So we start with, we have some guess at some iteration t. We just check if the constraints are met or not. Namely, we just look at what is the expectation value of a tilde, and we check if the diagonal constraint is approximately satisfied. And if they are approximately satisfied, then we just stop. We found a feasible state. If not, we're going to find a separating hyperplane that allows us then to separate the current guess from the set of states that actually satisfies our constraints. And the separating hyperplane will then be used to update the Hamiltonian we are optimizing over. And we are guaranteed to converge in a number of steps that is logarithmic in the dimension and in inverse quadratic in the error of the approximation. And I'm going to tell you in a second why that is. So just some illustration, as usual in these convex optimization problems, we just find separating hyperplanes, we update our guesses, and then at some point we reach the feasible set. Okay, and how do we show that if there is a feasible point, we're going to find it in log n epsilon minus 2 steps? Well, this immediately follows from one of the properties of mirror descent, which is an optimization algorithm. If you use the von Neumann entropy as its potential, you show that from one of the basic properties of this algorithm, one can show that the relative entropy between any feasible point and your current guess will decrease by a constant factor at each iteration. And as we started with the maximally mixed state, our initial relative entropy between the feasible point and the initial state was maximally log n. So after log n epsilon minus 2 iterations, we are guaranteed to reach a feasible point if such point exists. So we're going to be able to decide whether we're going to either find a feasible point after this many iterations, or we run the program for this many iterations, don't find anything, and then we know that no feasible point exists. Okay, now let us check how we actually find these separating hyperplanes for the problem at hand and how much this costs. So let's first just talk about a classical implementation. Let's suppose you want to run this algorithm classically. The first thing you have to do at each iteration is just to compute this Gibbs state and check then if the constraints are satisfied or not. And this both can be done, computing the Gibbs state can be done in n to the matrix multiplication constant time. So roughly, let's say realistically n cubed. And the other steps can be computed in n times s, where s is the row sparsity of our matrix A. The third one can be computed in linear time. And note that the separating hyperplane for the diagonal constraint is just a projection that allows you to distinguish the current state from all those states that look like the maximally mixed state on the diagonal. So this would give us a total runtime of n to the matrix multiplication exponent, which is still not very impressive. However, by using one of the oldest tricks in the book, we are actually able to reduce this runtime to n squared s by just doing a Taylor expansion. So we use the fact that we can do a Taylor expansion and only prepare this, compute this Gibbs state approximately. And we then get a runtime which scales like n squared s, where s is again the sparsity of the matrix. And this already beats the best existing classical algorithm. So a classical implementation of our algorithm already beats the best existing implementations by Aurora and Kale, which run like n to the 2.5. However, I must say that there's an an important subtlety in here. The way we measure the error is different than what they do. So we get an error which scales like epsilon times n times the operator norm of the matrix, and they get an error which scales like the L1 norm of the matrix, and this is just the sum of the absolute values of the matrix. And these, for some instances, our way of measuring the error is the right one. For some instances, their error is the right one. However, we show also that for generic instances, our error gives the right scaling. But anyways, this makes the direct comparison of the algorithms a bit difficult. Moreover, we see there's no speed up for the very important subclass of maxcut. So if the matrix A is the adjacency matrix of a graph, then we don't see any speedups. Moreover, we also see that the error dependency is quite high, and this is maybe one of the most important open question left by this work, namely how to improve the scaling and the error. Okay. Now, how do we actually do this on a quantum computer to also obtain speedups? Again, we just need to prepare Gibbs states for every iteration and just check how they look in the diagonal in the computational basis and check what is the expectation value of A. This is all we need to do to run an iteration. And if you can prepare a Gibbs state on a quantum computer, then it's straightforward how you should actually implement each step. You just measure it in the computational basis often enough for you to have to know how the Gibbs state looks like up to an error epsilon in total variation distance. And you also measure the expectation value of A tilde. So to estimate the diagonal, you need n copies. To estimate the expectation value of A tilde, you need 1 over epsilon squared. So you need n copies of the Gibbs state to run each iteration. And it turns out that by using some recent Hamiltonian simulation techniques, we can then obtain 1 copy of the quantum Gibbs state in times square root of ns, roughly speaking, which gives us a total runtime of n to the 1.5 times square root of the sparsity. And this, again, beats also our classical implementation of this algorithm and the best classical algorithm previously known, again, with the caveat of the different way of measuring the error. And the nice thing is that this quantum algorithm also gives you access to a classical description of the optimal Hamiltonian. So you can then directly use this classical description to perform the randomized routing. So maybe I'll skip how you actually implement the quantum Gibbs states, as this essentially boils down to importing results from the literature. And just mention that one of the main technical issues here is to make sure that the fact that we don't enforce the diagonal constraint exactly, but rather only approximately, doesn't change the value of the problem significantly. So from the technical point of view, this is maybe the main challenge, because of course this is a further relaxation of the problem, and it could maybe be the case that this further relaxation makes the problem artificially easy. This is not the case. So this further relaxation, if you pick epsilon small enough, so epsilon 1 to the 4th, this is enough to still give you a good solution. And maybe I'll also skip how to actually prove this, and just mention that also with the output of this approximate and further relaxed STP, you can also perform this randomized rounding. So in this, usually classically, you obtain the randomized rounding by multiplying your solution or the square root of a solution with a standard Gaussian vector, and then looking at the signs of the entries. And I just want to mention that with our approximate solution you obtain from the quantum algorithm, you can also do this on a classical computer. So you can also get use our algorithm to do randomized routing, even the quantum one. And with that, I would like to finish and make some last comments, namely one thing I already mentioned, namely that one of the main questions I think which is still open is how to improve the scaling and the approximation accuracy epsilon, because this is epsilon to the -9 or -12 in the quantum and classical respectively, which of course leaves a lot of room for improvement. I would also like to mention that I think these sorts of algorithms might be an interesting candidate for near-term applications, because at each step we only need to implement to prepare a quantum Gibbs state up to constant precision. So as we only need constant precision, this might be an interesting algorithm to implement in the near term. And just like to mention that we are applying similar ideas to solve other relevant STPs, for instance, quantum state tomography for low rank quantum states. So yeah, this is something we're working on right now using similar ideas. And with that, I would like to thank you for your attention.
Brilliant. So thanks very much indeed, Daniel, for a very nice, very clear talk. If you have any questions, you can ask them on Slack or via the Zoom Q&A feature, and I'll try to monitor those. But perhaps while people are typing, I can start by asking a question. So you already mentioned at the end about the runtime scaling in terms of epsilon. I guess in your algorithm, like let's say the classical one, for example, you know, this is 1 over epsilon to the 12th. And I was just wondering if you can say sort of where that 12th power comes from, like what it's built up from.
Sure. So, I mean, you already see an inverse polynomial dependency on the error and for the number of iterations. This you cannot get away with. And the problem is that in order to, it's the stability theorem we show. So we have this further relaxation where we say that we just want to enforce a diagonal constraint up to an error epsilon in total variation distance. And we then show that this gives you a multiplicative error with respect to the problem where we enforce the diagonal constraint exactly of order epsilon to the 1/4. And this is where this gives you an extra huge dependency on epsilon. So by using these mirror descent or matrix multiplicative weight methods, in general, you already get a quite high dependency. But as we have to rescale epsilon by 1/4, this then blows up to 12. So I would say that even if we improve the stability theorem, you would still get a dependency like epsilon to the 4 or something like this. You probably cannot improve much on that, but I think that should be doable.
Okay, thank you. Okay, so now some questions have started to come in. So first one is by Karen Morens, who asks, what makes this class of SDPs important relative to others that have been looked at in the past?
Well, I wouldn't say, I mean, it's difficult to say that it is more important than some other problem. I mean, that depends, of course, what you're interested in. But I would say first, it's very widely studied. There's a lot of literature on that, and it encompasses many extremely important problems, both in practice and in theory, right? So computing the cut norm of a matrix is a very fundamental problem in computer science. Or as I mentioned in the beginning, you can also see this problem as trying to approximate the ground state of a classical spin system. This is also a very fundamental problem in physics or computer science. So I think these are some of the reasons why this particular class of problems is very interesting and important.
Thank you. So there are a couple of more questions that have been asked, and maybe in the interest of time, I'll pass those ones on, and then we can save other questions for Slack. So question by Changpeng Xiao. He asks, in the classical algorithm, there's a step where we update H. So how do you update the Gibbs state on a quantum computer?
Of course, yeah, that's a very good point. I mean, we unfortunately skipped the Gibbs preparation step. So, well, you assume you have A in a QRAM. So all the steps, you will either add you a diagonal projection to your Gibbs state, or you will add some value you will add epsilon times A to your Hamiltonian. So it suffices to have A stored in some QRAM, and then you have some other QRAM where, so all the Hamiltonians you're going to be optimizing over will have the form of some linear combination of A and some diagonal matrix. So it suffices to update some QRAM for this diagonal part, and then you can use it to implement to prepare the Gibbs state. So we assume access to a QRAM. Yes.
Okay, cool. Thank you. And final question for now, which is an anonymous question. Someone who says this is amazing work, and they're curious if there are any existing implementations in this algorithm on quantum devices.
Not as far as I know, but of course it would be extremely nice if someone actually did this. But I must mention that, of course, if you were going to implement this on near-term devices, you wouldn't use these very fancy Hamiltonian simulation techniques, but maybe you could use some variational method to try to prepare the underlying quantum Gibbs states. I don't know. So I think this is a very interesting research question.
Brilliant. Well, maybe that's a nice point to stop. So thanks very much again, Daniel, for a great talk, and thanks for the questions as well from the audience. So perhaps we can now move on to the next talk, which is by Frédéric Magnier, I think. And this is a talk about quantum distributed algorithms for triangle finding in the congest model. So, so fantastic. I can see your slides are up already. So maybe you could make those full screen, I don't know. Brilliant. Okay, so Fred, then whenever you're ready, please feel free to get started.
Okay, thank you. Okay, so I'm going to start. So yeah, so this is a joint
work. We can't see
work.
your slides anymore, by the way. I don't know if you were expecting to show your slides now, but we can't.
Okay, so you don't see my slides.
We can see you, but not your slides.
I don't know why. Give me a second then.
A second ago we could, but it was not full screen.
I see. So maybe I have to choose. Let me try again.
Perfect. Now we can see.
Sorry for this delay. Okay, so it's a joint work with Taisuke and François from Japan about a quantum distributed algorithm. So let me first define the model. So it's, I guess, not so common model in quantum computing, but it's quite well studied in classical computing. So we are given a network, so let's say a graph, and on every vertex there is a processors, and the edge represent the communication between the processors. So at the beginning of the protocol, of the algorithm, each processor knows just the neighborhood. For instance, 4 knows that is connected to 1, 3, and 6. So there is a different label, let's say, to every vertices. And as a first round, the vertices, so the processor, can exchange a message without interacting. So just one message. So for instance, 1 can send a message to 4, and 4 can send a message to 1. So because we are in the so-called the congest model, this message is a quite short message of size basically logarithmic in the size of the network. At the end of this exchange of message, there is a local computations on the vertices. And here there is no restriction on time, space, or whatever. So this is the end of round 1. At the end, processors are ready to exchange again the message. And we continue like that. And the complexity is the number of rounds. So of course, we can put everything quantum here. And then it's called quantum distributed computing with congestions. So now at every round, processor can exchange a logarithmic number of qubits, logarithmic in the size of the network. On top of that, of course, the processors in each vertices are quantum. So the question that can we compute something faster quantumly than classically? So in fact, this problem was studied a long time ago, but basically with So essentially a negative result. So the one I would like to mention is the one in the in 2009, 2014. So they show that basically any task that has most studied classically, meaning finding a shortest path on the network or finding a minimum spanning trees, there is no speed-up quantum. So here, remember, we are the data is a network and is only known locally by each vertex. And globally, let's say, so all the processors would like to find, for instance, the shortest path. So at that time, there was basically no speed-up quantum. So here I'm going to mention two specific problems for which we know some speed-up. So the first one is a diameter. So we would like to compute the diameter of the network while minimizing the number of rounds of computations. So classically, this can be done in n rounds. This is not so good, but still not so easy because of the congestions. N is a number of vertices. The other problem is to decide or find all triangles in the networks. A priori, it may look easy because a triangle is a very local problem. And if you look, for instance, of this picture, so U, V, W, U know is connected to V and is connected to W, but it doesn't know if V and W are connected. So it looks simple, but we see it's not so simple. And in fact, there is a sublinear algorithm for this problem. So it's possible to find all triangles in a number of rounds, which is a qubit root of n, and I will come back to this later. Classically, those two problems are optimal. Those two algorithms are optimal, meaning we cannot do better. So let's come back to the first problem. So there is a result by myself and François 2 years ago, where we show that it's possible, in fact, to compute the diameter much faster quantumly. So on this picture, you can see that if the diameter you want to compute is d, so we don't know d, of course, but let's say it's d, then we have a complexity which depends on this diameter, which is square root of nd. So when d is sublinear, this is sublinear. We don't know if it is optimal. It's in fact quite hard question. And I make progress on that with Ashwin Nayak this year, but you see the lower bound doesn't match the upper bound. So the question today, can we make a progress to another problem? So this problem is finding a triangle. So let's now be more explicit about this problem. So we have a network, the graph, and we want to decide if there is a triangle. What does it mean in a distributed way? So for triangle finding, there is at least one node that should, so one vertex that should say, oh, I know a triangle. And this is a triangle. Triangle listing, meaning all together, all the nodes together have to output some triangle. And if you take the union of all those triangles, then we find all triangles of the network. So for the two problems, it's not so difficult to come with an n-round algorithm classically. And we will see that we can put Grover on the top of it and get a quantum algorithm, quantum discrete algorithm that choose only square root of n rounds, but just to find one triangle, not all of them. And we will see why. So here is the algorithm. So I think everyone can understand this algorithm. So let's first describe the classical algorithms that can find all triangles of the graph. So remember, every vertex is a processor, and it knows its neighborhood. So every pair of vertices that are connected with an edge are going to communicate through this edge. So here is U and V, in order to decide if UV makes a triangle with another vertex. So U has utmost n neighbors because there is n vertices in the graph. V is the same. And in fact, they want to output all the vertices they have in common is a neighborhood. If you think about it, it's something called set disjointness in communication complexity. In fact, this is a communication complexity problem because U is going to communicate to V, and U knows all its neighborhoods and the same V, and they want to find the intersection. So classically, we can do that by communicating UV n times, and this is optimal. So this approach is optimal classically. Now, set disjointness, you can speed up by Grover search. And we know that set disjointness can be done with communication complexity square root of n, which here means with square root of n rounds, it's possible for an edge UV to detect if there is at least one vertices in common in the neighborhood. Now it's a distributed algorithm, so all pair of vertices can play this game together at the same time. And since every edge is only, every pair of vertices UV is only using the edge UV, there is no congestion. So this can be done using square root of n quantum rounds. Now, if I look at the lower bound for finding all triangles, here there is an argument. I'm not going to details, but this is the full proof, so you can see it's short, saying that there is no way we can do that with a number of rounds smaller than the qubit root of n. If I want to find all triangles, and in fact, this algorithm, argument is information theoretical, and it is also valid quantum. So where are we now? We have a lower bound, which is for finding all triangle, qubit root of n. There is an upper bound, which is n, for finding all triangle. And there's a quantum algorithm in square root of n for finding at least one triangle if there is any. So quite recently, in fact, classically, the deterministic upper bound were improved by Taisuke and François, and they provide a sublinear algorithm. Later on, there was so past year, two amazing results. And the conclusion of this line of work is that finding all triangle classically can be done by a randomized distributed algorithm with a number of rounds, which is qubit root of n. And so this is optimal up to a factor of n. So can we do better quantumly? No, for triangle listing, because the lower bound is also through quantum. But maybe we can do better for just finding a triangle, and this is what we are doing in this work. So we provide a fourth root of n round distributed quantum algorithm for deciding if there is a triangle. So realize here that we are modifying we relax the problem in two ways. We consider quantum distributed algorithm, and we just want to find one triangle, not all of them. So it's still possible, in fact, that we don't need to go to quantum algorithm. Maybe there is a classical algorithm that also find a triangle in a number of rounds smaller than qubit root of n, but we don't know. And I have no lower bound quantumly for this problem, for just find one. So this might be not the final answer. So I'm going to describe the strategy now. So there are two steps, in fact. The first step is to find a triangle, detect if there is a triangle with one vertices of very high degree. So what does it mean? It means that degree, that is m, the number of edges, divided by square root of n, the number of vertices. Here, I'm assuming those parameters are known. This is just technical details. In that case, we can just speed up the previous algorithm I mentioned for set disjointness. Because let's say every edge UV now is looking for a common vertices with high degree. And there cannot be so many vertices with high degree. In fact, there is only square root of n with those constraints. So I'm going to solve a set disjointness, knowing that the set of candidates is just square root of n. And then if we do Grover search on that, we go to the fourth root of n. So this is very easy. The second part, this is a much difficult part, is, okay, can we find how to find a triangle where all the vertices of that triangle have low degree? And for that, we need two ingredients. The first one is classical, so it comes from the previous line of work, and the second one is a framework I developed 2 years ago with François. So here is the first ingredient. So this is quite a fantastic decomposition of the graph that can be done very efficiently, meaning with polylog number of rounds. So this is completely classical. So remember at the beginning, every vertices just know their neighbors. So what they showed is that it's possible to decompose the graph. So meaning that every vertices know in which part of the graph they are. So it's possible to decompose the graph very quickly in polylog number of rounds, such that so the vertices are in different parts, and within each part the graph is an expander. And there are few edges that we don't know what to do with them, but it's just a small fraction of the initial edge. So using this decomposition, in fact, we show in the paper that it's possible to assume that our graph is an expander. So now our graph is an expander. So there are some technical details because of the remaining edges, but this is not too difficult. The second thing that now we assume that our graph is an expander is that in such a graph, they showed that it's possible to route easily from one vertex to the other, just like it was a click, just like if everyone is connected, in fact. So this is amazing. Remember, there is some conjections on the graph. And the only constraint is that, of course, every vertice should not send and receive too many messages. So the number of messages should be basically the degree of that vertices. Otherwise, there's obviously a conjecture. So the strategy, assuming that the graph is an expander, will be to delegate some verification of the triangle to some vertices. So this is the first ingredient, and this is very nice. The second ingredient that we'd like you to know is this framework of basically, how can I do a Grover search on a distributed framework? So we developed this framework with François 2 years ago. It says the following: imagine we have a network and some function, and we want to find a solution of that function, meaning some input where it takes the value 1. And it's a distributed problem, so of course, computing this function is going to use the networks, and it is going to use some number of rounds t. So here it's very abstract. F can be anything. But I know, of course, it's going to be related to the graph, and I know it's going to use t rounds. Then we show that if I want to find x such that f of x is 1, then basically I can do a Grover search. So it can be done in square root on the domain size times the cost of the function, which is t rounds, plus a parameter, which is a diameter. And this, we can forget it in our setting because we are dealing, I said, with expanders. So I don't have so much time left, but I think I can give you the idea now. How do I combine those two tools? So the first thing is to partition the vertices. So we are going to do just a random partition of the vertices in square root of n parts. Each part is going to have square root of n vertices. And I'm going to assume that the graph has a small degree. I told you I'm looking for a triangle with only low degree vertices. So here I just assume that the maximal degree is in fact that quantity. And then it's possible to show that if I take any triple of these subparts, the number of edges is very small, m over n. And this is nice because m over n is the average degree. So most probably, I can just send all the edge between one selected triple of parts to a single vertex, which have degree, let's say m over n, which happen a lot of time, in a polylog number of rounds. And this vertices is going to check if there is a triangle here. That's fantastic, except that if I look at the number of triples, I have n3½ of them. But I have only n vertices, so I have too much. In one round, I'm able to deal with n triples. So what I'm going to do is I'm going to put my n triples in square root of n buckets, and each bucket have n triples. Now I'm going to look for one good bucket, and this is a distributed search. And I'm almost done. So my goal is to find a bucket of n triples with a triangle. Checking if a bucket has a triangle can be done in polylog n round. This is just classical. On top of that, I'm going to do a distributed Grover search. I have square root of n buckets, so I can do that in n to 1/4 times the cost of checking the bucket, which is polylog n rounds. And I'm done. So this is my conclusion. So the problem of finding a triangle is much easier than just finding all triangle quantumly. We don't know if we can do better, even deterministically, for this problem of finding just one triangle. And it would be nice, of course, to get a lower bound, maybe to improve that and to find other application of quantum distributed computing, maybe using other tools than basically Grover search. And I'm done. Thank you very much.
Brilliant. Thank you very much for that very nice talk. So as before, please ask questions on Slack or on the Q&A feature on Zoom. So I guess I'll ask the first question. So I was wondering whether in this model, there's anything known about the structure of which problems have efficient algorithms and which ones do not. Like, do we have any intuition for which problems we should expect to be easy, which problems we should expect to be hard?
I guess up to 2-3 years, we thought that they could not have any speed up. So I guess we have quite a few intuition for now. It's important to, okay, first of all, for some problems, the diameter is a barrier, and then we cannot do more. And looks like the problem for which we can have a speed up are essentially a decision finding problem. Most probably for minimum spanning tree, for instance, I cannot do better.
Interesting. Okay, questions have started coming in. So there's a question from Andrew Sambinus who asks, what's the best classical lower bound for triangle listing?
N to 1/3, this is what I tried to say, is N to 1/3. So for listing, classical and quantumly is N to 1/3, and this is optimal, up to log n factors. And now for finding, there is just no lower bound, classically and quantumly.
Okay, fantastic. Okay, so I can't see any more questions. So I think we could bring this session to a close unless anyone has any last minute things they would like to ask. So if not, then we have a coffee break now for, I guess, half an hour. And then after that, the next session will be starting. So wonderful. Thank you all very much for your questions. And thanks again to the speakers for some great talks. Thank you.
Thanks.
Okay, can you hear me? Great. Thank you. Okay, almost.
Should I share my screen already?
Okay, welcome everybody to the Friday afternoon session on focused on computational complexity theory. We have 3 talks in this session. The first one is entitled Approximate Tensor Decompositions, Disappearance of All Separations by Andreas Klingler, Gemma de las Cuevas, and Tim Netzer. And Andreas will be giving the talk.
Yeah, thank you for your introduction. Can you see my screen?
Yes.
Perfect. Yeah, I will be talking today about an approximate notion of tensor decompositions, which is a joint work together with Gemma de las Cuevas and Tim Netzer. And before starting, I would like to tell you the main message of this talk. So the main message of this talk is the following. On the one hand, there are many different decompositions of tensors, but on the other hand, there was shown in recent years that there also appear many separations between these decompositions. So one rank can be much larger than the other rank. And this has a lot of applications. For example, you can show with this tool that, for example, different communication protocols have separations. On the other hand, we have studied in this work an approximate notion of tensor decompositions. And with this notion of approximate tensor decompositions, we have shown that these separations, or many of these separations, disappear in the approximate case. So let me start at the very beginning with the very basics, namely tensors in general, tensor decompositions in general. So tensors, as an element of a tensor product space, have the property that they can be decomposed into a sum of elementary tensors. I guess that's not a surprising property for most of you. So for example, we could write it down in that way. So where every elementary tensors consists of local elements in the local vector spaces. And the maximal index here, this R, has a particular name. It's called the tensor rank. And the tensor rank is quite an important parameter for a given tensor because it somehow is connected with the efficiency of the representation of a tensor. But in fact, this is not the only possibility to decompose a tensor. There are many possibilities to define a tensor decomposition and its rank. So for example, we could arrange the indices in quite different way. So for example, we could arrange the indices in a circular way, where every local vector consists of 2 indices and each index is joined with its neighbor. And each such a decomposition, for example, this circular decomposition here, can be associated with a graph, like we see it here. This idea representing a decomposition with a graph comes from tensor networks. And every vertex is associated with a local vector, and every edge corresponds to a joint index. But if we go back to our very initial example, there you would observe that we cannot associate it with a tensor. So we have to generalize the idea of tensors to Simplici complexes, which are generalizations of tensors in a way that this also allows simultaneous connections between more than two vertices, called facets. Another way of studying tensor decompositions is to introduce invariant decompositions. So a global element, this V, could be, for example, invariant with respect to some permutations of the local vector spaces. But this invariance is usually not incorporated in the local elementary tensors or in the elementary tensors here. So we have to define that as an explicit invariant decomposition. And this has an influence on the rank. Another thing we could consider is positivity. So in a lot of applications, we don't have only given a tensor product space, we also have given some notion of positivity. So think about, for example, describing a quantum many-body system with mixed states. We use density matrices to describe mixed states, and these density matrices are positive semi-definite. And this is one notion of positivity. And this positivity is usually also not incorporated in the local elements here. Yeah, I will come to that later a little bit more in detail. So I've defined that tensor decompositions now quite abstractly. Now let me go first into two. Let me mention two examples. So one example is, for instance, in the context of machine learning, probabilistic modeling. So if we have given an explicit tensor product space consisting of column vector spaces, C to the D, we could define a notion of positivity, namely we call a tensor non-negative if all the entries of this tensor are non-negative. And with this definition of non-negativeness, we could associate every probability distribution with a non-negative tensor up to a normalization. And it was recently shown that in this context, different tensor decompositions with respect to arrangement of indices and local certificates of probability, the positivity correspond to different probabilistic models. For example, hidden Markov model or a Born machine, and different ranks corresponding to the tensor decomposition corresponds to the expressive power of this probabilistic model. Another example, which is quite well studied, and is the field of tensor networks. And I already mentioned that. So in the field of tensor networks, people are studying different types of decompositions with respect, for example, with respect to different arrangement of indices. So for example, the well-known matrix product state is nothing else than a decomposition where the indices are arranged in this circular-like structure, what I've mentioned at the beginning already. And there are also other decompositions, just mentioned the PEP state, for example, which is another arrangement of indices. But such decompositions in the context of tensor networks cannot only be defined for pure states, they can also be defined for mixed states. And for mixed states, as I already mentioned, we also have given some notion of positivity, namely positive semi-definiteness of the density matrix. Okay, and I want to point out that in my talk, I will stick exactly on this example, namely I will define different tensor decompositions of mixed states with this arrangement of indices here in this circular-like structure. And this different tensor decompositions differ in the fact that they have given different local certificates of positivity. So I will define three different exact tensor decompositions, and in this context we will explicitly see that there will appear separations. And after that we will go to our actual work, namely an approximate notion of these tensor decompositions, where we will show that these separations disappear. Okay, so let me recap the notion of this matrix product state like decomposition, but now for mixed states. This had a particular name in the tensor networks field. It's called the matrix product density operator form. and it's a decomposition of a density matrix in this circular-like structure. And we don't claim any properties for the local matrices. So the local matrices here doesn't have to be positive semi-definite. This can be arbitrary Hermitian matrices. And the minimal R, which is necessary to decompose a given density matrix in this structure, has the name operator Schmidt rank. And so I've already said that the local matrices don't have to be positive semi-definite. It could be arbitrary Hermitian matrices. So we could ask somehow a weaker question. So does there exist a local certificate which is somehow uniform in the system size to decide whether the global element is positive semi-definite or not? And the answer to this question is negative. So in general, as it was shown in this paper, a local certificate of positivity would be undecidable if it is uniform in the system size. But we don't have only negative news, there are also positive news. It will restrict our space of consideration to separable states only. Then we get decomposition with a local certificate of positivity. And that's because by the very definition of separable states, there exists decomposition, which is a convex combination of product states. And so we could get a matrix product density operator form of separable states where all the local matrices are positive semi-definite. And for this decomposition, we call the rank the separable rank. The separable rank can be larger than the operator Schmidt rank indeed. But let us go back to arbitrary density matrices and decomposition with a local certificate of positivity for arbitrary density matrices. And this can be done with the so-called local purification form, where the main idea is that we can characterize positive semi-definiteness of the density matrix by the fact that we can factorize it with a Hermitian matrix sigma. This matrix sigma is called a purification. And since it's a matrix like rho, it doesn't have to be positive semi-definite, but it's an arbitrary Hermitian matrix on the tensor product space. It can be like the density matrix rho can be decomposed into a matrix product operator form. And so we could define the local purification form with this purification. And the corresponding rank, the purification rank, is called the purification rank, and it's simply the operator Schmidt rank of the purification sigma. So we have seen now these three different types of decompositions, and as I already mentioned in the beginning, the different ranks correspond to the efficiency of the description. So it would be interesting to relate these three different notions of ranks. And one relation which can be obtained is that the operator Schmidt rank can be upper bounded by the purification rank squared. And that's not so unreasonable because a purification contains somehow more information than the operator Schmidt decomposition because it has a local certificate of positivity. So we can reconstruct from a given purification a matrix product density operator form. So in fact, it would be more interesting to go into the other direction. So can we find an upper bound of the purification rank only depending on the operator Schmidt rank? And this question we again have to answer with no. So there doesn't exist a function such that we can upper bound the purification rank by the operator Schmidt rank for arbitrary density matrices. So considering density matrices of arbitrary dimension. And this fact is called a separation. So we have seen now that we have given a separation between operator Schmidt rank and purification rank in general. But there is also another example. There is a separation, for example, between purification rank and separable rank. So to summarize now the case of exact decompositions, so we have seen now these three different types of decompositions, where the first one, the operator Schmidt decomposition, matrix Farrokh density operated form, contains no local certificate of positivity, but is the most efficient one. And on the other hand, we have two decompositions which contain a local certificate of positivity, but they are arbitrarily much larger than the first. So now let's consider the approximate case, and that's our actual work. And the main idea of the approximate case is the following. So we consider a fixed approximation error, call it epsilon, and then we do not define directly, we do not define an approximate decomposition, we define it directly with the given rank. And the idea is that we define an approximate operator Schmidt rank for a given element row as the minimal operator Schmidt rank, which can be obtained in the epsilon ball with respect to a given norm. And the given norm in our work is the Schotten P norm, which is in fact the P norm over all singular values of the matrix, or if we restrict to Hermitian matrices, it's just the P norm over all eigenvalues. And of course, the unit ball, or the epsilon ball, could look quite differently for different values of P. So for P equal to infinity, it's the outer square. For P equal to 2, it's the circle. For P equal to 1, it's the inner square. And similarly, we could define the approximate separable rank and the approximate purification rank. And with this definition of approximate decomposition, we now have shown the following. Let me state the theorem first in an informal way. So we have shown that the separable rank can be, in the approximate case, so for a fixed value of epsilon and fixed value of P, can be upper bounded independently of the system dimension of rho. Yeah? And this directly implies that the separation between operator Schmidt rank, purification rank, and the largest rank, namely the separable rank, disappears because we don't have any dependence on the system dimension. So a little bit more in detail, we have shown that for various values of P, namely for P strictly greater than 1, so we have to exclude P equal to 1, and 2 for third, and P equal to 2, and P greater equal to 4, we can in fact upper bound the separable rank by some function which only depends on P and epsilon. And the main tool how we have shown this is an approximate version of Gerardo's theorem, which was recently shown in 2019. And Gerardo's theorem is a theorem which gives upper bound for general convex combinations. And usually in the exact case, the upper bounds for the ranks of convex combinations are dimension dependent. But there is a lot of research going on in these approximate versions of Gerardo's theorem. And in fact, it was shown that these upper bounds are dimension independent. But we didn't only, so here we have to restrict only to the case of separable states. But we have also shown a similar result for a huge class of arbitrary density matrices. And there we have shown that for, again, a fixed approximation error epsilon and the P in the same interval, the separations between purification rank and operator Schmidt rank disappears in the approximate case. Okay, so now we have only considered a special arrangement of indices, namely this circular type of decomposition, and we haven't talked about symmetries yet. And in fact, we have shown this result, what I talked about in the last slides. We have shown this in a more generalized way. So up to now, we only talked about this circular type decompositions, but in fact, we have also shown it for arbitrary geometries based on simple complexes. as I defined it at the beginning, where every phase set coincides to a joint index. So for example, for the very first example, what I've shown at the beginning, so where we only have one index, also the notions of ranks, purification rank and separable rank for this special geometry of a simplicial complex, there the separation disappear in the approximate case for the same assumptions what I've already talked about. But that's not enough. We have also shown it for not only for decomposition in simplicial complexes, we also included symmetries. So in fact, we have shown that for a given density matrix, if this density matrix respects the symmetry, so it is symmetric with respect to a given group, a given subgroup of the permutation group, then we can also show that the separations between the symmetric rank, purification rank, and separable rank disappears in the approximate case. Okay, so to summarize everything, so first of all, we have seen the first part that in general, for a given, we have seen it in the special case of a circular decomposition, but in general, for a given simplicial complex omega and a given group action G on this simplicial complex omega, in general, the exact notions of decompositions separate. Yeah. But our goal, what we have shown in our work was that if we fix some approximation error epsilon and some values for some special values of P, we can show that the same notions of ranks, but now in the approximate case, disappear. And we think that, so let's do an outlook. So as I already mentioned, these separations have a lot of different applications, different fields. I mentioned machine learning and quantum many-body systems, but also quantum communication complexity. So there the separations are used to show that that different communication protocols have separations. So we think that this result has a lot of applications in different fields. And what would be also interesting to consider, what we have done yet, is to consider other norms, especially local approximations, because up to now we only have considered this global approximation with respect to the Schatten P norm. But it would be interesting to also go into local approximations to approximate the local matrices. So that's everything from my side. Thank you for your attention, and now open for questions.
Thank you very much, Andreas. That was very very interesting. I don't see any questions at the moment, and we're close to the time for the next talk. Am I missing something for where the questions are? Okay, thank you again for a very interesting and clear talk, and maybe we'll set up with the next speaker.
Okay.
And may I ask that so Joao, please set up, and Andreas, yeah, okay, you turned off, and
yeah, I'm here.
9:43, so let's wait till 9:44. Okay, there we go.
Can you see my screen and hear me?
It's very clear.
Great, perfect.
Yeah. Okay, so the next talk is entitled exponential quantum communication reductions from generalizations of the Boolean hidden matching problem by João Fernando Doriguelo and Ashley Montanaro. And João is going to give the talk. Please go ahead.
Great, thanks for the introduction, Richard. And I'd like to thank the organizers for putting up the setting the conference. So yeah, as Richard mentioned, I'm going to talk about a generalization of the Boolean hidden matching problem, joint work with my supervisor Ashley Montanaro. So let me give a brief overview of the talk. So I'll briefly introduce the field of communication complexity. Then I'll explain the Boolean hidden matching problem. I'll give then our generalization and then characterize the problem by giving upper bounds and lower bounds, and then conclusions. So, okay, so a very gentle introduction on communication complexity. So in this field, we have normally two parties called Alice and Bob, and each holds a data, normally bit string, and they are required to compute a joint function of their data. So in order to do so, they have to communicate some data between themselves. So Alice will send some data to Bob, and Bob will send some data back to Alice, and so on, until they have enough information to compute the function. So, and what we are interested in here is the minimum amount of exchange information that is needed to calculate the function. So what I mean is the minimum number of bits in the classical setting, and where we are normally interested is in the quantum counterpart of this problem, which is like, what is the minimum number of qubits that we need to allow exchange in order to solve the problem. So we're interested in problems that we can allow an exponential reduction of this amount of information. Okay, so there are many different communication models. So you may consider a communication model where Alice communicates to Bob and vice versa. You can have more restricted models where Alice, for example, only communicates to Bob, or even more restricted where they only allow to communicate to a third party called referee, and the referee needs to send the output answer. So here in this talk, we're gonna focus on the one-way model where Alice can only communicate to Bob. Okay, so now I'm gonna introduce this Boolean hidden matching problem. What it is. So in this problem, you have Alice, and again, you have Bob, and Alice holds a bit string, and Bob holds a permutation of Alice's bit string. So whenever Alice sends a bit of her data, Bob's gonna like rearrange this bit according to a permutation he holds to get a final bit string, and then he's gonna separate this final bit string in blocks. So at the end of the day, what he does is like rematch the bits of Alice, and he's gonna compress this bit string using parity to get a final bit string. So for each block of 2 bits, he's gonna output the parity of these 2 bits. And then they are interested in some property of this final bit string. So in more mathematical terms, Alice holds a bit string X, and Bob holds an alpha matching M, characterized by disjoint blocks. So this X plus this matching gets a final bit string such that each bit of this bit string is just a parity of 2 bits of the original string X, which this thing is basically what I just showed in the picture. So one question you may ask is like, they want to output a block and the corresponding bit of this block. So this characterized what you call hidden matching problem, was introduced by Briët, Ernest, and Ernest in 2004, and is a relational problem. So there's many outputs, but you can turn this into a Boolean problem, which was also, so now in this problem, Bob has another bit string called W, and his problem is that the final bit string and the compressed final string is either equal to W or the complement. So you want to find out which case is the correct one. So this problem was also introduced by Briët, Ernest, and Ernest, but Gavinsky, Kemp, Ernest, Raz, and Rowe, and Van der Wolf, they gave lower bounds for this problem. So what's interesting about this problem is that this was the first relational problem and partial Boolean function to exhibit exponential classical quantum communication gap. What I mean exactly by this is the following. So it was proven that this problem can be solved using sharing this logarithm many qubits. So we say like is an easy problem to solve. But classically, you can see that Alice can solve this. Alice and Bob can solve this problem by having Alice sending random bits, and by birthday paradox, you can solve the problem. Like you can have a clash of 2 bits in one block after you send like order of n, square root of n. And the paper from Rona and the others, they proved a lower bound of square root of n using Fourier analysis and KKLR inequality. Okay, so this is the problem. There is no problem. So we generalized this, and it was a very like straightforward generalization. Is that why use parity for compressing your rearranged bit string? Why not use any Boolean function f? And in this way, you might get like many new exponential separations. So that's exactly what it did. So if we go back to our problem, so Alice is going to send random bits of her bit string. Bob's going to rearrange according to some permutation, and it's going to now separate into larger blocks and into t bits, and it's going to use another function, a Boolean function, to compress the rearranged string. So now we can phrase the same problem again. So Alice has a bit string x, Bob holds a permutation, and now given this Boolean function that is already known, and the j block of the primitive string, we can have the final string compressed by applying the function f to each j block, to each block. So these 2 lines here is basically the picture I just showed. So again, we can formulate the same problem, which we call f Boolean hidden partition problem, which now that Bob has a bit string w, and again, its problem is that the final rearranged and compressed string is either equal to w or is complement. So now we want to know which case is the correct one. So the case when f is parity on 2 or more bits was already studied before. So in the case on t bits, it was proven by Verbe and Yu back in 2011. They proved a classical lower bound of this form. So if you insert t equals 2, you recover the normal square root of n lower bound. And again, the quantum lower bound was given by Shi, Yu, and Yu in 2012. This form. So I guess if you put t equals 2, you don't get any meaningful lower bound, because we know there's a efficient protocol that solves the problem with logarithm log n qubits. Okay. But then one might ask, why generalize? Why in the first place? So I guess in the literature, there are not many, but a few exponential quantum classical separations. So we know go back into Rouzé in 1999, he gave a exponential separation for a geometric problem in a 2-way model, and then all the later Berman, Clave, Walters, DeWolf, they gave exponential separation for the equality problem in the simultaneous message passing model using this idea of quantum fingerprinting. In the way model, of course, you have the Boolean hidden match problem I'm just talking about. And again, you have all the separations between 2 and 1 models and 2 and the SMP models. But still, Ash and I, we felt in the beginning of this project that there are many separations when you compare to the Curie complexity model, where the Shor's algorithm acts. So we think we should expand this. This generalization could help expanding this class of problems using having exponential separation. And of course, this broad class of problems can be useful in the future for reductions, for reducing other problems to it. Okay, so now we're gonna characterize a problem. So we think, and this will be clear at the end of the talk why I'm stating this as a conjecture. But we think that the whole problem can characterize by the term in terms of the sign degree of the Boolean function. So what is the sign degree? So given a Boolean function f, we say that a polynomial p over the bit strings on t bits over to the reals, its signs represent f if it takes negative values for the bit strings whose value of f is 0, and it takes positive values when f equals 1. So I guess what you're doing is like relaxing the codomain of f. Instead of being 0, 1, you're allowing any real number. So of course, and we define the sign degree of f by the minimum degree of such polynomial that signs represent f. So we think that this quantity alone can characterize the whole problem. And now I'm gonna like give our results like starting with upper bounds. So what we first proved, well, we can give efficient classical lower bounds if the sign degree is less or equal to 1. And so efficient, so the complexity here is logarithm of n. By R1, I mean the randomized complexity in the one-way model. So I'm gonna briefly explain how the protocol works. Is quite simple. So if the sign degree of f is 1 or less, so you can sign represented by a polynomial of this form. So the idea of the protocol is that Alice is gonna send different like bits at random, uniformly at random to Bob, and Bob is gonna get each bit string, it bits the Alice sends, and gonna match to the corresponding bit inside the block. So for example, Alice sends a bit, and Bob checks that this bit, for example, is the 3rd bit in a block. So he's going to assign the corresponding weight of the polynomial that size represent this bit, the f, according to this random variable. So you can prove the expectation value of this random variable is positive if the final compressed string equals w, and is negative if it equals the complement of w. So again, so after logarithm log n bits, like you can decrease your error probability as much as you want to epsilon. Okay, so that was the classical protocol, very simple. So now I'm gonna state so we have a similar result for quantum protocols. So again, it's the same result if basically the same result, the same complexity, but now the sign degree of f can be 2 or less. So it allows more functions. And the idea of the protocol borrows these block multilinear polynomials that we use from paper from Harrison and Bannink and others. So what we say, what is a block multilinear polynomial? So it's a polynomial which you can separate the input into blocks, and each monomial of the polynomial has exactly one variable for each block. So for example, giving an example for a block multilinear polynomial of degree 2, you can separate the inputs in 2 blocks, so the x block and the y blocks, and each monomial here, this aij, xi, yj, so each monomial has just one, maximum one input variable for each block, so one x and one y. So in this paper from Harrison and the others, they proved they show that if the sign degree of f is 2, so there exists a block multilinear polynomial of degree 2 of this form. The signs represent f. So using this result, we can prove our upper bound by the following. So the idea is that Alice is going to send us this following quantum state to Bob, which is basically a superposition of her bits. This extra term here, this second summation is a technical, is for technicality to make the results of Harrison to work. So Alice is going to send this quantum state. Bob then is going to project the state into one block. So for example, he has a block that is like the first, the third, and the fifth bit. So he's gonna like measure his state and get like one of this block. So a superposition of bits of this block. He then attach a plus state to this state he just measured to get this final state, the psi b. So now, if you will let A be the matrix of P tilde, the signs represent F, that I showed in the last slide. In the paper of Harrison, they show the following: that there is a unitary U, such that you can, when you apply the unitary U to a state psi, is basically equivalent to applying the matrix to psi plus some orthogonal junk. So the idea is that Bob's going to apply a control U to the state he has, to this plus and this psi j. So he's going to get this final state, and then he's going to perform the Hadamard gate on plus, the final qubit, and measures it. And the claim is that he's going to get a probability of 1 with, he's going to measure 1 with this probability. And this basically is the Hadamard test. So, and then if you plug the results of U applied to psi from the last slide, from here to that state, we're going to get this. So what's happening, like this sandwich of U is basically reproducing the block multilinear polynomial. And then if F, because this block multilinear polynomial signs represent F, if F equals 1, then the probability of measuring 1 is going to be greater than half. But if F of X is 0, then the probability of measuring 0 is going to be greater than half. So I guess you can see that by repeating this many times, you can obtain decrease the error probability by as much as you want. So this, with this, we get our lower bound, our upper bound of log n qubits. Great. So these were our lower bounds, upper bounds. So now I'm going to talk about our lower bounds. Cool. So our first lower bound is a symmetric function. So we proved that if f is a symmetric function of degree of sign degree greater or equal to 2, so we have this the lower bound of order of square root of n, and this comes from a lower bound reduction. So it comes from a reduction from the usual Boolean hidden matching problem. The problem is that this reduction doesn't work if f is the not all equal function that I'm stating here, unfortunately. But you can see the paper to see why it doesn't work. So we can see we get a large exponential classical quantum separation for sign degree equals to 2. Another general lower bounds we got is the following in terms of not the sign degree, but the pure high degree of f. And the pure high degree I'm stating here. So we say the pure high degree of f is d if the Fourier coefficients of order less than d are 0. So if you change the domain from 0 to 1 to -1 to and 1, this has this like nice statement here that I put in the footnote. So we got this lower bound. So we proved that the randomized complexity, class complexity, is the following: is n to 1 over d, 1 over -1 over d. If the pure high degree is greater than 2 or equal, and we have a similar one for quantum. So now the pure high degree has to be greater and equal to 3. And this were obtained using the Kirk-Hallel and hypercontractivity inequalities. We don't need to. I want, in the interest of time, I want to explain what they are because they are high technical. Okay, so with this, I would like to conclude. I think I'm running out of time. So we got like upper bounds for quantum and quantum classical upper bounds for our problem. We got a lower classical bound specific for symmetric functions, and we got a general lower bounds for classical and quantum for our problem. So in this way, you get a large family of exponential quantum class separations. But unfortunately, you know that the pure high degree is always less than or equal than psi degree. So in this case, our lower bounds that we're having here, they are not general in this case, in the sense that they are functions with like large sign degree, but maybe with like low pure high degree, for which our lower bounds don't apply. So we have like a gray area where we think the problem is hard, but we couldn't prove that they are hard. It's hard. So another thing people normally ask when I give this talk is that to give a concrete example of functions where we have separation. So of course, Peryton to be a trivial example. Any symmetric functions or function of this form, which go up and down once, is have an exponential separation. And functions of this form, so a product of two linear threshold functions, and these include like majority and dictator functions. We also get exponential separation for this. And finally, we of course conjectured our lower bounds can be expanded for instead of pure high degree here, it's going to be the sign degree. But in order to do this, you're gonna have to use a non-uniform hard distribution on inputs for the proof. I didn't say, but it's possible. We proved in the paper. If you wanna see that under the input is uniform distribution for Alice and Bob inputs. If the pure high degree is less or equal to 1, we can come up with efficient classical protocols. It's only when we allow a non-uniform distribution on the inputs that the problem might become harder. Okay, and this I would like to finish right on time, I guess.
Thank you very much. That was a very nice talk. There is a Q&A window on which people can post questions, I believe. And
yeah, I'm looking at it, but
oh, I see.
Yeah, no
right.
question. So I guess
Okay.
everyone understood the talk.
Here we go. Changpeng Xiao asks, is it easy to compute the sign degree?
You can state the problem as a linear program. So I guess in the sense, yes, but if your function is very complicated and a lot of inputs, it might be not. But I don't see why no.
Okay. Okay. Thank you very much again. I'll just remind people that there is a Slack group that on which you can we can continue conversations or questions about the talks. And I may have overlooked something for the questions for the first speaker. I apologize for that. I'm not sure whether there were questions. I didn't open the correct window. Anyway, thank you again, Joao. And now we'll prepare for our next speaker. And the next talk is entitled On the Complexity of Zero Gap MIP Star. And the authors are Harmoon Musabi, Sajjad Nezadi, and Henry Ewan. And Sajjad is going to be giving the talk. So please go ahead whenever you're ready, Sajjad.
Thank you. So yeah, my talk is going to be on the complexity of zero gap MIP star. And this is joint work with Harmoon Musabi and Henry Ewan. So the main result of this paper is this equality between two complexity classes, that is MIP star 0 and pi 2. So MIP star 0 is the class of multi-prover interactive proofs with entangled provers, but the zero gap variant of it. And pi 2 is a computability class that lives in the second level of something called the arithmetical hierarchy, which I'll talk about later. So this is investigating the zero gap variant of the MIP star complexity class, which was recently shown to be equal to RE in a very important result. So this is showing that there's a separation really between the zero gap variant and the constant gap variant of MIP star. So In particular, in order to prove this equality, we show a reduction between languages of the compatibility class pi2 to 3 prover zero gap MIP star protocols. And some consequences of this reduction is, first of all, it shows that the problem of exactly computing the value of an entangled non-local game is strictly harder than the halting problem. So this was already known to be undecidable, but it wasn't characterized how complex it is. And another consequence, for example, is that this refutes the 3-player version of Cyrilson's problem. And in fact, if this reduction can be improved to 2-prover MIP star 0 protocols, then this would also refute Kahn's embedding problem. In fact, the MIP star equals RE result of a couple of months ago also refutes Kahn's embedding problem, but I just wanted to put this out there so that it's evident that this type of reduction requires some non-trivial tools to be done because it has major consequences. And so I'm going to start with some definitions. So first of all, a non-local game is a game G that's played between a verifier and multiple entangled cooperating provers. And these provers are not allowed to communicate once the game starts, but before the game starts, they're allowed to agree upon a strategy that may use the entanglement that they share so that they can maximize the chance that they win the game that the verifier is playing with them. And so given a game and a strategy, the winning probability of that strategy for the game is denoted omega star GS. And really what we care about is to know what the maximum winning probability of a game is over all strategies. So the value of a game, which is the value that we care about, is denoted as omega star of G. And this is defined to be the supremum over all possible strategies of the maximum of the winning probability of those strategies for a given game. So this is really the value that we care about. And the fact that we define it using a supremum here is kind of important because just because a game has a value of 1, so a perfect value, that does not necessarily mean that there exists a single strategy that wins the game perfectly. So it might just be that there exists a sequence of strategies whose probability of winning approach 1. And in fact, because it was shown by William Slofster in 2017 that the set of quantum correlations is not closed, there are such examples of games with perfect values but no perfect single strategy. So that's a non-local game. Now that we have the notion of a non-local game, we can define complexity classes based on them. In particular, MIP star K is a class that consists of all languages for which there exists K prover, a uniform family of games, so non-local games that decide them. How do they decide these languages? It's that if X is in the language, then the game associated to it within the family should have a perfect value. And if X is not in the language, then its associated game in the family should have a value that's upper bounded by a half or any constant that's less than 1, really. That could be the case. And so then the complexity class MIP star, constant gap version, is defined to be the union over these MIP star Ks for K greater or equal to 2. So that is languages that can be decided in this way using non-local games of 2 or more entangled provers. And what we care about in this result is MIP star 0 gap. So MIP star 0 gap is similarly defined. The only difference is that here we require the games to have a 0 gap requirement. That means if X is in the language, again, we want this associated game to be perfect. But if X is not in the language, then what we require is that it's not perfect. So it's kind of relaxing that requirement, which makes it more powerful. And in fact, the problem of deciding whether or not a given non-local game has a perfect value or not is a problem that is complete for MIP star 0. So if you would like, you can just think of MIP star 0 as exactly that, as the difficulty of deciding whether or not a given non-local game is perfect or not. So that's on the non-local side of things. now we can talk about the computability side of the equation. So there's something called the arithmetical hierarchy, which is a hierarchy of computability classes, where the bottom of the hierarchy is all decidable languages. That means languages that you can potentially write an algorithm to solve for. And all these computability classes within the arithmetical hierarchy are strictly separated from each other. So in particular, the class pi2 that we care about in this result strictly contains both RE and co-RE. And so RE that I just talked about, what is it? So it's the class of recursively enumerable languages. That means languages for which there exists a Turing machine M. If X is in the language, then we want the Turing machine on that input to accept. And if X is not in the language, then we just have that the Turing machine runs forever. So it's semi-decidable. It only decides if whether or not the input X is in the language. And you probably know about the halting problem, which is a famous problem. And the halting problem is complete for this class RE. And in fact, there is a different way of also characterizing RE, which is simpler for many of our proofs. And that is that RE consists of all languages that can be defined in this form. That means can be defined using formulas that have this structure, that is existential quantifier followed by a decidable predicate. So any language that can be defined using a formula of this type, which we'll call an RE type formula, then that language will be in the class RE. And similarly, the class pi2, which we care about, consists of all languages L for which there exists a Turing machine. If X is not in the language now, we want that MX, the Turing machine on this input X accepts, given the power to access an oracle for the halting problem. And if X is in the language, then we just want the Turing machine to run forever. So this is really like a meta type of computability language. It's kind of esoteric. It's saying that it's kind of the difficult languages that are so difficult that they can only be, the non-membership in the language can only be decided by Turing machine, even if it has access to solve the halting problem for free. And so it's kind of difficult to deal with it in this form. But again, there's an equivalent way of defining pi2, which is simpler to deal with. And that's all languages, L, for which you can define them using formulas of this type here. So it's similar to RE, but here the formulas consist of a for all quantifier, followed by an existential quantifier, followed by some decidable predicate P. And in fact, the number of alternating quantifiers here is exactly what characterizes the level of the arithmetical hierarchy, which these computability classes come from. So RE is from the first level, so it had only an existential quantifier. Pi2 is the second level, so there's two quantifiers and so on. And the order of these quantifiers defines whether or not it's pi or sigma in the arithmetical hierarchy that I showed. And so that was some definitions for our result. And in order to prove this equality, there's two directions of inclusion. And the easier direction is to show that MIP star 0 is contained in pi2. And to, as a reminder, the language that is complete for MIP star 0 is to decide whether or not a given non-local game has perfect value, that means value 1. And so all we do is we just have to show that this problem of deciding that omega star of g is equal to 1 can be equivalently written in the form of a pi2 formula. That means a formula which starts with a for all quantifier, then an existential quantifier, then some decidable statement. And I claim that omega star g equal to 1 can be rewritten in this form, which is exactly the form of a pi2 formula. And that would show the inclusion of MIP star in pi2. So what is this saying? This is, of course, this is not rigorous, but it's for the purposes of the presentation. It's saying that for any constant gap epsilon, there exists some protocol or some strategy that can win the game with probability greater than 1 minus epsilon. And if that's the case, that means as you shrink the gap that you want to win by, you have a strategy that can win it always. And that means that really the value of the game must be approaching 1, which is exactly what we want. And therefore, there's an inclusion of MIP star 0 in pi2. And the more difficult and interesting inclusion is to show a reduction from pi2 specifically to 3 prover MIP star 0 protocols. And in order to do this, we use two tools from previous recent results. The first is a zero gap protocol compression scheme that comes from a work from 2019 by Fitzsimmons et al. In that work, they actually show the inclusion of co-RE. They show a reduction from languages from co-RE to MIP star 0 with 3 provers. And this is going to be basically the heart of our argument as well. But in order to increase the power of this compression protocol and to be able to capture pi2 with it, we bootstrap this using something called a halting game or a halting protocol, which is something that pops out as a consequence of the MIP star equals RE result that was recently proven in a couple months ago. And so I'm going to talk about these two important tools. So the first thing is the halting game or halting protocol. And this says that if you have a Turing machine M, then there exists efficiently computable non-local game GM, which is associated to it. And the properties of this game are that if M halts, if you run M and it eventually will halt, then the property of this game is that it will have a perfect value. That means omega star of GM will be equal to 1. And on the other hand, if M is a Turing machine that will run forever and will never halt, then the value of its associated game should be less than 1. And this is the game associated to any Turing machine that kind of decides whether or not it's halting based on the value of the game, based on whether or not it's winnable, basically. And so you can use this, for example, to show that RE is contained in MIP star 0. And the way you do that is you begin with a RE type formula, so an existential followed by a decidable predicate, and you want to decide whether or not this is true. So this is something that's that was complete for RE. And the way you do this is that you can translate this problem to an equivalent problem here. So you define a Turing machine M. What this Turing machine does is that it begins to loop over all possible values of n, and it only stops if the predicate P of n is ever satisfied. So if it's true that there exists an n for which P of n is true, then this Turing machine will eventually halt whenever it reaches that value of n. But if it's this statement here is false, then this Turing machine will run forever. Therefore, you can reduce the problem of deciding whether or not an RE formula is true to an equivalent problem, which is deciding whether or not this associated Turing machine halts or not. Then you can use this halting game construction that I showed in the previous slide to then further reduce this problem to just deciding whether or not the game GM associated to this new Turing machine that we constructed, whether or not it has a perfect value, which is exactly something, which is the problem, the complete problem for MIP star 0. So using that halting game construction, you can make a simple argument to show that RE is contained in MIP star 0. So that's the first tool that we need. The second tool is a tool called, a more fundamental tool called the compression, zero gap compression. So what does compression say? Compression says that if you're given a family of non-local games indexed by natural numbers, call them Gn, then there exists a way to efficiently compute another family of games, G sharp n, where G sharp n has a property that it's much more efficient. That means the verifier, the runtime of the verifiers for each of these games is polylogarithmic in the runtime of the verifiers of the original game, which is important. And also that the new family of games, even though it's much more efficient to run, the value of the game hasn't changed much. That means that it's kind of preserving the gap that was already there. In particular, you have these two requirements here, which say that if a given game in your original family was not perfect, that means it had a value less than 1, then you're guaranteed that its associated game, G sharp n in the new family, will also not be perfect. And also, you're guaranteed that your new game, G sharp n, will always be lower bounded by this formula here, half plus half times the value of the original game. So these are two properties that are important. And so we can run through a quick argument that shows the inclusion of co-RE in MIP star 0, which using just this compression. So similar to RE, co-RE formula is of the type of all quantifier followed by decidable predicate. So the problem here is to decide whether or not a formula of this form is true. And we want to reduce this to deciding whether or not some non-local game G is perfectly winnable, which is the MIP star 0 problem. The way we do this, and we try to kind of circumvent having to enumerate over all n in this formula, we first construct a family of games that we want to use compression on in order to get this property. And so we construct a family of games Gn, indexed by all these n's. And each of these games, what they do when you play them is first, the verifier checks if P of n is true. Because remember, this formula is true if P of n is true for every n. So it first checks if P of n is true. If it's not the case, that means if the game G3, for example, sees that P of 3 is not satisfied, then the verifier, without even using the provers, already rejects the game. That means already it decides that the provers have lost the game. But if P of n is true, then the verifier goes on to play G sharp n plus 1, where G sharp is the compressed family of games from Gn. And so this kind of seems recursive, but it's not. And some of the details I've, of course, left out here. But G sharp is really a different game that you're able to efficiently compute and play. So we kind of use this recursive, maybe pseudo-recursive property in its analysis, but it's not really doing recursion here. And I claim that once you go through this analysis, these family of games I've defined here, they have the property that if you played the first game, if the first game in this family is perfectly playable, then that's equivalent to having decided whether or not this co-RE formula is true. And so to go through a quick analysis of this, let's first consider the case where the formula is false. That means there exists some n for which the P of n is false. Let's say n is equal to 3 here. So let's say P of 3 is false. Then we know that the game G3 will have a value of 0. Why is that? Because the game G3 will first decide whether or not P of 3 is, the verifier will first decide whether or not P of 3 is true. And because it's false, he will reject it outright. And therefore, the value of that game we know is 0. And here the red and green lines are kind of relations between the values of the sharp games on the right side and the normal games on the left side. And we get this one, this equality, just from the construction of the family of games. So remember, the game Gn plays the game Gn plus 1 sharp. So this equality, if P of n is not rejected, this equality will always hold. And this pops out of the properties of the compression theorem. So if the game from the family was not perfect, then its associated compressed game should be less than 1. So here, in this kind of diagram, I've shown the connections. So we can just run through the analysis using these connections. So we know that the game G3 is equal to 0, the value, because P of 3 is not satisfied and the verifier outright rejects it. So therefore, we know that this value is less than 1, it's less than perfect. So by this, using this relation, we know that this associated game G sharp 3 will also have a value of less than 1, which means because of this relation here, that the game G2 will have a value less than 1. And using the same argument again, we get to the point that the game G1 will have the value less than 1. Therefore, if the formula is false, and at some point n, let's say n equals 3, the P of 3 fails, then we're guaranteed that if the game G1 will have a value less than 1, which is exactly what we want. On the other hand, if the formula is true, in fact, then we can do a similar argument. We know that the first part of the game will never fail for any of the games in the family because P of n is always true. So always the game Gn will just play the associated game G sharp n plus 1. So we have an infinite kind of like hierarchy of these relations now that hold. In particular, again, we have this red relation by construction. And then this is the second property that we get from the compression. That says that G sharp of n is always lower bounded by this value here. So we can run through this argument. We know that the value of G1 is equal to the value of G2 sharp. And we know that the value of G2 sharp is lower bounded by this guy here. So we can use that argument to see that omega star of G1 is lower bounded by this guy here. And then we can, again, recurse, because we know we can do the same argument here for G2, as saying that lower bounded by some value associated to G3. And so therefore, we can keep recursing this argument. And we get that if the formula is true, then the value of the game G1 will be lower bounded by this over here as the limit of k goes to infinity, where this limit approaches 1. So again, if the formula, the co-RE formula was false, then we know that the value of the game G1 is less than 1. But if it's true, then we know that by this argument that the value of the game G1 should be exactly 1, which is exactly what we want. And that concludes the inclusion of co-RE in MIP star 0. So I'm kind of running out of time, but I'm almost done. And so I'm not going to get into the details of exactly how to prove the reduction from pi 2 to MIP star 0. But really, it's the main core argument is those two tools. So you begin with a pi 2 formula. That means a for all followed by an existential followed from a decidable predicate. You want to decide whether or not this is true. Well, first of all, you see that there is an RE formula embedded within. So you use this kind of halting trick that we showed before. You instead of doing this, you're kind of you change this to some Turing machine that you want to decide whether or not it halts, and then you get the associated halting game. And then so using this halting game, you can convert doing this decision to deciding whether or not for all n, the associated halting games, which are associated to this RE formula, have perfect value or not. And then we have a for all n here. So even though this is not a core RE formula, you can still use compression here. The math works out. And you can use compression to, again, circumvent doing this for all n, doing this enumeration over all n. And then you get, in a similar way that I showed for the co-RE inclusion in the previous slide, you're able to reduce this to this, playing a single game called G pi 2. So really, you go from the pi 2 formula, you use the halting game to reduce it to a for all and something that you want to decide. And then you're able to use compression to reduce that to just playing a single game. And that's exactly what we want. So in this way, you're able to take a pi 2 formula and reduce deciding whether or not it's true to playing a corresponding game and deciding whether or not that's perfect, a perfect game, which is shows that pi 2 is an MIP star 0. So just some open questions. So this reduction reduces pi 2 to languages to MIP star protocols with 3 provers, and that just has to do with the details of the compression theorem that have to use at least 3 provers. So it's interesting to see whether or not this can be improved and reduce it to just 2 prover MIP star 0 protocols. And the final open question, and I'll end on this, is to show whether or not, is to basically finish this quest of understanding entangled multi-prover interactive proof systems. And the last complexity class that needs to be characterized in this work is MIP co, which is similar to MIP star, but you're allowed infinite entanglement. And so it's conjectured that this is equal to co-RE, but this is a big open problem. And here on the right, I have kind of an image of the landscape of entangled multi-prover interactive proofs. And you can see MIP star 0 is the largest of all of these. And that'll be all. Thank you. And I'll take any questions now.
Thank you very much, Sajjad. That was very interesting. And are there any questions? Okay. Anurag Ashu asks, he says he says great talk. And why do you believe MIP co-RE equals MIP CO equals co-RE?
Yeah, so I guess it could be that MIP co is actually decidable, but we know that MIP co 0 gap is equal to co-RE. and MIP co is contained in MIP co 0. So it's either equal to co-RE or it's decidable, and probably I'm actually don't have a great argument for why it should be one or the other. Maybe others might. But also it would have a pretty nice symmetry to it because there's co on both sides of the equation, though the co's mean different things. Co on the right side means complement, co on the left side means commuting operator strategy, so infinite entanglement. But you know, that's still waiting to be seen.
Okay. Gilles Bassard asks the question about the CO meaning different things. I think you just answered that.
Yeah, so the CO for MIP co is just a commuting operator strategies. That means strategies that can use infinite entanglement instead of finite strategy.
Okay. Okay. So I believe that you can continue questions and discussions on the Slack group, and but let's end the session now. So thank you very much, Sajjad, again, and also to the other speakers of the session. And that ends this this session. And there's a 30-minute break, and at 5:35, well, 30 minutes from now, whatever time zone you're in, the next session begins. So thank you again, and this is the conclusion of the session.
Hi everyone. Let's start our quantum circuit section. First, we will have Jonas Haverkamp talking about efficient unitary designs with a system size independent number of non-Clifford gates. Jonas, go ahead.
Thanks. Give me just a second, then I will share my screen. So there we go. And you should see it full screen now. Does that work?
Yeah, it works.
Ah, wonderful. Okay, then thanks a lot for the introduction. Also, thanks to the organizers for making this happen, despite all of the difficulties. So I'm very happy to talk about a piece of research that we did on random unitaries and how to generate good random unitaries, or what we believe to be good random unitaries, using only few non-Clifford resources. So the talk is based on a paper that we put on the archive in February. And so you can find it under this link, and you can also obviously find it just by Googling buzzwords. Before I start with the talk, I should say that I was very lucky that I got to collaborate with these wonderful people, and that this is really joint work. So all of these people contributed a lot to this work. So this is Felipe, Marcos, and David from the University of Cologne, and Jens and Ingo, who are also at Freie University Berlin. So without further ado, let's get straight to the result. What do we prove in this paper? What we do is we show that you can generate good random unitaries or pseudo-random unitaries using a number of non-Clifford unitaries, as for example the T-gate, that is completely independent of the system size and only polynomial in T, at least if T, where T somehow measures how good the randomness is, at least if T is not too large compared to the system size. So we called this phenomenon quantum homeopathy, which was obviously meant as a joke, but it is actually a surprisingly accurate description of this phenomenon. So in a sense, the magic ingredient, which is the non-Clifford gates, or the T-gate in particular, the density of these is allowed to go to 0 for large system sizes. So the rest of the talk will be just me explaining all of the words I just said. What is a good random unitary, what's applying a Clifford unitary, what's non-Clifford unitary, and so on, and hopefully motivating why this is an interesting result, or why we believe that this is an interesting result, and maybe give an idea how to attack the proof of this. So let's get straight to random unitaries. Random unitaries, I mean, for many people, these probably don't need motivation. They are a ubiquitous concept in quantum information theory. Many quantum information processing tasks use random unitaries as a resource. For example, quantum system identification methods usually rely on random unitaries, as for example randomized benchmarking and certain tomography protocols, but also encoding and decoding information for quantum channels. Some more exotic applications also involve models of quantum information scrambling on the surface of black holes. And much more generally, it is possible to capture generic features of complex quantum systems by studying random dynamics or random states. There's one caveat though, I mean there always is one, and in this case the caveat is full Haar randomness is ridiculously expensive, at least for large Hilbert spaces. So a simple counting argument, just counting the degrees of freedom in the unitary group, shows that if you want full Haar randomness, if you want to implement this on the Hilbert space, on the unitary group that acts on n qubits, then you will need 4 to the n, I think it's 4 to the n approximately, or round about 4 to the n local gates. So this is completely unfeasible for most applications, but fortunately there's a way out of this. So for most applications, it actually completely suffices to have a probability distribution that just has similar properties as the Haar measure for a certain function. And when I say a certain function, I mean a certain function in the entries of the unitary random variable. And usually this function is actually a polynomial. So one way of saying that something is a good pseudo-random unitary is to say that the expectation values of polynomial functions, or of balanced polynomials in particular, are the same as the ones that you would get for the Haar measure. So an arbitrary balanced polynomial can be written like this in the entries of u and u bar up to degree t. So the polynomial is supposed to have degree t in the entries of the unitary matrix. So if we take the average over these or integrate over the Haar measure, then this will give us a new matrix, a new operator. And the super operator that acts on matrices and does that, this is something that we call the moment operator, corresponding to this probability measure. And saying that the Haar measure, or the probability, that the probability distribution that we are interested in produces the same moments as the Haar measure up to tth moments, can also be expressed as saying that these moment operators are the same. So this is just a fancy version of that. And if that is the case, we call the probability distribution an exact unitary T-design. Because it's a very well-behaved case, and also because we will need it later, this time is as good as any time to introduce the following case. If nu is actually the Haar measure on a subgroup, then this introduces a probability distribution on the unitary group. In this special case, we have actually a very nice description of the moment operator. In that case, it is just an orthogonal projector onto the commutant of the T diagonal action. So orthogonal here means with respect to the Hilbert-Schmidt product. One particular case of that is captured by the so-called Chauval duality. So if we consider G to be the full unitary group, in that case, we just get the plain moment operator of the Haar measure. And what this tells us now is that the moment operator that corresponds to this is really just the projector onto the commutant of the T diagonal action. And the Chauval duality, or I should say one of the phases of the Chauval duality, it tells us that this space is completely spanned by the permutations of these tensor factors. So you can easily see that this commutes with this action, because if you commute two tensor factors and the unitaries in these tensor factors are the same, then the permutation doesn't change the action. But the non-trivial part of the Chauval duality is to say that, okay, this is really the full commutant. So we should progress to the protagonist in the story, really, which is the Clifford group. And the Clifford group actually does exactly that. It tells us, okay, for at least for small t, in particular for t equals 3, there is actually an efficient implementation of these unitary designs. So the Clifford group is this beast here. It is generated by the phase gate, the Hadamard gate, and the controlled Z gate applied to arbitrary qubits. And if you consider the full group, or if you take the Haar measure on the full group, then this will give you a unitary 3 design. And for many applications, this is actually enough. For randomized benchmarking, for example, you usually only need a unitary 2 design, and this is the reason why people like the Clifford group so much. The other one is really that it's easily implementable, at least compared to non-Clifford gates. And the dynamics consisting of Clifford gates can be classically simulated by the Gottesman little algorithm. So it is not a unitary 4 design, however, but in a representation theoretical sense, it's quite close, actually. So now the hope would be that if we require for some application higher moments, then an obvious hope now would be that we might be able to construct similar groups, similar to the Clifford group, maybe extend the Clifford group somehow, or take something completely different that generates simple, exact, higher designs. And this hope is crushed immediately, unfortunately, and quite spectacularly, because it can in fact be shown that there is no such thing as a 4 group, at least as a subgroup of the unitary group. So this simply doesn't exist. This is, I think many people probably knew this before, but I didn't until I was made aware of this paper here in 2018, who showed this. But they use an older result by Guralnik and Teep, who basically show that 4 groups don't exist. And I should say finite 4 groups, because the infinite dimensional case is independently solved, was independently solved by Savitsky and Karnas. So they don't exactly write it down like this, but essentially they show that if you have unitary 2 design and it's finitely generated and infinite, then this is the full unitary group. So there seems to be a brick wall, and all hope is lost, essentially. But that is fortunately not the case, because it just seems like asking a probability distribution to be an exact unitary design seems to be too much to ask for. And in fact, for most applications, it actually suffices for the probability distribution to be an approximate design. So one notion of approximate design is if we consider, or one sensible notion is if we consider these moment operators, these super operators, then we say it is an epsilon approximate design. So the probability measure nu is supposed to be an epsilon approximate design if the channel distinguishability between the moment operator corresponding to nu and the one corresponding to the Haar measure is smaller than epsilon. So the channel distinguishability it gives you a bound on the probability of distinguishing these channels, even if they are allowed to act on arbitrarily entangled inputs. So there's a seminal result that now shows that if you only require epsilon approximate designs, and they actually show this for an even stronger notion of approximation, then you can get away with polynomial resources. And in fact, they show that this is not only true for polynomial in N, but even the dependence on T is polynomial. So you get this with really polynomial depth circuits, you get polynomial designs, approximate polynomial designs. So this is a powerful result, and it has many implications. But if we only view this now as a protocol to generate designs, then, so if we only concentrate really on this aspect, then it has some caveats, in particular for small t. So basically, even for t equals 2, if we want to generate a unitary design using this, we get polynomially deep circuits, and these will not be classically simulable, and also it will be difficult to implement them, at least using near-term devices, because essentially what you require is a fault-tolerant quantum computer. So on the other hand, we know that just implementing a uniform Clifford unitary gives you a unitary 2 design, an exact unitary 2 design even. So it seems like this, just viewed as a protocol to generate unitary designs for very small t at least, is overkill, actually. And we can somehow capture this intuition in our result by showing that if t is not too large, at least in this regime, then we can actually greatly reduce the necessary resources to generate higher designs. So this is the result that you have seen on the first slide. What we do here is we draw a uniform Clifford unitary, multi-qubit Clifford unitary, and then we implement a single qubit non-Clifford unitary that we denote by k. I'm actually simplifying here a bit. There's a little bit of fine print that you can look up in the paper. But basically, this is the model. And what we show is that if the depth of this iteration, this k interleaved Clifford circuits, we call it, then there's some constant that just depends on k, such that if the depth is larger than the constant times t to the 4 plus just the logarithm of 1 over epsilon, then this is an epsilon approximate unitary design, provided, again, that t is not too large compared to n. So this has many consequences, especially for small t. It's really nice that we get now efficiently simulable families. So if there's an application, if there's something that you want to know about generic properties of, or Haar random properties of, for example, many-body systems, and this only depends on the 4 design property, then now we have families of 4 designs that can be efficiently simulated on a classical computer. So it might be possible to do this completely numerically without actually implementing this fault tolerantly. And overall, we also get an improved gate count, at least in the regime that I was talking about, because the Ernst-Gottesman protocol allows us to decompose an arbitrary Clifford gate into n squared over log n many gates. So it was proven to be optimal, that the n squared dependence was proven to be optimal, I think, at least up to logarithmic factors, and we can show that in some cases you can actually save this logarithmic factor. And also in the simulability result, we even allow for t to scale slightly with the system size, which is perhaps surprising. So how do we prove this now? We prove this using the so-called Schur-Weyl duality, or a variant of the Schur-Weyl duality for the Clifford group. So this is really the key tool that we apply to get this result. And it was obtained, like, I think 2 years earlier by David Grosse, Per Nizami, and Michael Walter. And what they do is they describe the commutant of the T-diagonal action of the Clifford group in terms of a generalization of permutations. And I don't want to get into what these Lagrangian subspaces are, but let's just say it's a completely geometrical notion. It's actually a notion from symplectic geometry. And here it's precisely this notion, but for finite fields. So it's completely defined in terms of the discrete phase space of the system. And what they can show is that there's actually a canonical basis, similar to the permutations being a canonical basis for the commutant of the unitary group, or the T-diagonal action of the unitary group. And that these actually span the commutant and that they are linearly independent. So what we can do now, so this is actually a notation that I didn't introduce here. The sigma is the probability distribution on the unitary group that corresponds to these circuits. So if we consider now the moment operator, and if we really want to bound the difference between this one and the Haar measure one in the diamond norm, then there's a trick using the properties of this projector. We can actually rewrite this difference as an iteration or k-fold iteration over the interaction of the action of k and a different projector. And this projector is actually the projector onto the autocomplement of the unitary commutant in the Clifford commutant. So we take all of the elements in the Clifford commutant that are orthogonal to those that are spanned by permutations. And the most natural way to really describe or to work with this, or to get any handle on working with these projectors, it would be good to describe them in terms of an orthonormal basis. And this is also what we do effectively. We rewrite this as a sum over ket bras in an orthonormal basis that form an orthonormal basis. But unfortunately, the Lagrangian subspaces or the operators that you can construct out of these, they actually form a basis, but it's not orthogonal. Not pairwise orthogonal. And what we can do, however, we can show that if n is large enough, and this is basically where this n needs to be larger than t squared condition comes from, in that special case, we can bound the coefficients that come from the Gram-Schmidt orthogonalization. And then applying a rather longish combinatorial argument, we get in the end this bound. And it contains all of this really in the end contains all of the information that you need. So it has this 2 to the t to the 4 dependence, and then something that's luckily logarithmic in the depth. And then we have a factor that shows that n really needs to be large compared to t squared, because this here would scale exponentially if the argument of the racket wouldn't be close to 1. And the last one, it kind of looks innocent here, but it's actually the most important part. This is eta, and it's the maximum of the overlaps of these Lagrangian subspaces that don't correspond to permutations with the action of the non-Clifford gate. So this somehow measures how a non-permutation Lagrangian subspace interacts with K. So let's talk about this for a second in more detail. If we have some Lagrangian subspace, this is actually bad notation. Okay, forget this one here. This is supposed to be T is supposed to be a subset of Z, sorry. So if we consider these normalized representations of these Lagrangian subspaces, then we can show that the interaction between the action of K and any T that is not a permutation is actually bounded away from 1 by a function that grows or that decays very slowly in T. And we used 2 results for this. One is a geometrically proven lemma that bounds the difference between the Haar symmetrizer and these non-permutation Lagrangian subspaces. And I really like it because it kind of captures the essence of the interaction between the unitary commutant and the Clifford commutant. And the second one is a deep result from harmonic analysis by Peter Variou, who bounded spectral gaps of averaging operators acting on irreducible representations. So these averaging operators are a generalization of the moment operators that we study in this talk. So let's end the talk with some open problems. The most obvious open problem, to me at least, is that the question whether this condition that T can't be too large compared to N, whether this can be lifted. Then there is a stronger notion of approximation. And we prove this for additive errors, but it would be interesting to see whether this also holds for relative errors, the system size independence, I mean. The scaling in T, we have a T to the 4 in the scaling. I believe that this can be improved, and we actually have an idea how to get down to T to the 3, but right now it's not completely working out, so there's much more work to do. And then we are right now also interested in applications of higher designs, and last but not least, we strongly expect that this can also be proven for qubits. There are some technicalities, some parts of the proof need to be generalized, but I think this can be done. So with that, I want to thank you for your attention, and if there's still some time, I would like to answer some questions.
Thank you, Jonas, for a great talk. Is there any questions from the audience? You could type them in the Q&A session.
Sorry.
We still have 3 minutes left until the next talk. So if you have any questions, please speak up and we could answer.
Sorry, I actually do have a question, but maybe as a panelist, I can't figure out how to enter it into the Q&A, so I'll just ask. Jonas, can you explain a little bit more how this this condition that the design order needs to be less than square root n appears?
Yes. So this basically stems from the fact that we have this Gram-Schmidt orthogonalization, right? And we will usually have factors that we can only bound by the triangle inequality, where we have a sum over all Lagrangian subspaces. And in fact, the number of Lagrangian subspaces is bounded by 2 to the t squared. So for example, the number of permutation grows like t faculty, right? But the Clifford commutant is much larger because it is the commutant that corresponds to a subgroup of the unitary group. And it's really this 2 to the t squared that gives us the t squared condition, because usually we can show that luckily these terms are also suppressed exponentially in n, and then you get something that's 2 to the then constant t squared minus n. And if these contributions are not small or are not actually exponentially small, then it's very difficult to say anything, because we can't we don't know anything about the Gram-Schmidt orthogonalization. We don't know whether this is actually close to the Lagrangian subspace basis that we have.
So I guess technically speaking, how much of a roadblock is it? Like, do you just have to use something different than Gram-Schmidt?
Actually, I have no idea how to surpass this. So I have a feeling that it's very difficult to write down. I think you probably know this this obstruction when you are dealing with the commutant of the unitary group, right? So there seems to be this threshold where you can approximately diagonalize this, which is if the local dimension or the dimension of the space you consider is larger than t squared. This is the analog thing for the unitary group. If this is the case, then suddenly you can prove all kinds of things. And everything turns out to be well behaved. But below this threshold, it's very difficult to say anything. And you basically run into the same problem with the Clifford group here, just that now the overlaps don't cancel such that it's not suddenly exponential, the dependence in T anymore. Right? So for the unitary group, you have this overlap of all permutations, and then you can show that this is smaller than T squared at some point, even though the number of permutations is T faculty, and you just don't get that for the Clifford group, unfortunately. And I think our bounds is basically sharp, so it really just doesn't.
Thank you.
So I think also, yeah, thanks for the question. Super cool.
Okay, thank you, Jonas, for the nice talk. Can you unshare the screen, and we could have our next speaker, Nick Hunter-Jones. He will actually have 2 talks. The first one is about unitary designs from statistical mechanics in random quantum circuit.
All right, so everyone can see my screen?
Yes.
All right, you can hear me, I guess. Okay, great. First, I'd like to thank the organizers for putting on a fantastic conference and for doing a phenomenal job organizing and hosting the conference virtually. And I really hope to visit Latvia sometime in the future, and hope that everyone listening is doing well despite the circumstances. So today I'm going to be talking about random quantum circuits and their pseudo-randomness properties. And I'm going to be talking about some nice techniques to do computations for random circuits using a mapping to the statistical mechanics of a lattice model. And this is based on a paper from mid last year. Okay, so I'll get started. So random circuits are very nice because they're a rare instance of a solvable model of local chaotic dynamics, as well as efficient implementations of randomness. So in quantum information, random circuits are very fast quantum information scramblers, essentially optimal decouplers. They're low depth implementations of unitary designs, approximating approximating the moments of the unitary group with relatively low depth. And as we've heard about recently, they're also, the hardness of sampling the output distribution of random circuits means they're good candidates for demonstrating quantum advantage, for instance, in the Google supremacy experiments. In quantum many-body physics, random circuits are, as I said, a rare instance of a solvable model of strongly interacting dynamics, and we can use them to extract universal features of many-body systems and study things like thermalization, the onset of things like chaos and scrambling, and out of equilibrium properties. Okay. So the specific random circuit model I'm going to be considering are local random circuits on n qubits of local dimension q. So their total dimension is q to the n. And the evolution I'm going to be considering is this evolution by staggered layers of 2-site unitaries. So acting on even links at even time steps and odd links at odd time steps. And where evolution to time t is a depth t circuit given by the product of t layers. Okay. Yeah, I'm actually going to be, in this talk, I'm going to be focusing on circuits with this fixed geometry and where each gate is chosen independently from this 2-site unitary group. And each gate is chosen randomly in space and time. And our goal is going to be to study the convergence of these local random circuits to unitary K designs, as we heard about in the last talk. So this is the circuit, this is some ensemble of depth T circuits, and we're interested in the circuit depth at which we start approximating moments of the unitary group. And I should apologize for changing notation from the previous talk, but in my talk, K is going to be the design order, and T is going to be the circuit depth. I think this is actually reverse from the previous talk, but I'll just emphasize that. So T here is like time, okay? Good, so we're interested in studying the pseudo-randomness properties of these random circuits, okay? And as Jonas mentioned, designs are incredibly, well, random unitaries, but especially designs are incredibly useful. And they kind of pop up in all sorts of different subfields in quantum information, including tomography, state distinguishability, randomized benchmarking, as well as in studying kind of physics and the onset of things like thermalization, generation of entanglement, and fast information scrambling. And a lot of these results only require maybe approximate 2 or 4 designs, but high degree designs are often essential for showing things like concentration and proving large deviation bounds, and are also essential in proving long-time growth of complexity, as we'll see in the next talk. Okay. So I'll just review again the definition of a design. So remember that the Haar measure is the unique left and right invariant measure on the unitary group, UD. And if we consider some subset of the unitary group, so some subset of unitaries equipped with some probability measure, we're often interested in averages over that, that set of unitaries. So if we consider an operator acting on the k-fold Hilbert space, we say that the k-fold channel of that operator with respect to this ensemble is given by this average over the ensemble. Okay. And one might ask when averages over this ensemble of unitaries look like averages over the entire unitary group. So we say that an ensemble of unitaries is an exact K design if the K-fold channels are equal for all operators O. Okay, so we have some big space, right, like the unitary group, and we're asking when some subset or maybe some set of points, right, equals the average over the whole space up to the kth moment. So for K equals 1, Pauli operators and any basis of operators actually forms an exact 1 design, but in general, very few exact constructions are known. So we can relax this this notion and ask, instead of when are the k-fold channels when is the ensemble kind of equal to the kth moment of the unitary group, we can ask when it's close. So we say that an ensemble of unitaries is an approximate K design if the k-fold channels are close in diamond norm. Okay, and designs are very useful, as I mentioned, because they kind of allow us to wield the full power of the unitary group with relatively low complexity. All right, so I'll just give some more intuition for designs. We can think about asking about how random the evolution of a system is. So if we consider some ensemble of time evolutions at a fixed time t, so these could be depth t random circuits or things like Brownian circuits, or these could also be unitary time evolutions generated by some ensemble of disordered Hamiltonians, say. So at time equals 0, this is just a bunch of points sitting at the identity. But chaotic time evolution is going to move us rapidly or ergodically over the unitary group. So we might ask, how random this time evolution is, and ask when this ensemble of unitaries starts approximating moments of the unitary group. Okay, so as I said, we're interested in random circuits and their design properties. So actually, a lot is already known. For instance, Harrow and Lowe studied the mixing time of non-local random quantum circuits, so with long-range gates, and found that they form approximate 2 designs with order n squared gates. And then Brandão, Harrow, Horodetsky studied the spectral gap of the moment operator and showed that local random circuits form approximate K designs in n times K to the 11th depth. Okay. Moreover, they showed that a lower bound on the K design depth is linear in n and K. So there's actually a significant improvement that you can get in K, and there's kind of some lore and speculation in the community that random circuits actually saturate this lower bound. So that random circuits, this dependence on K can actually be improved. And there are a lot of other very nice results for the design properties of random circuits. For instance, Harrow and Maribin extended these results to higher dimensional random circuits and showed that for a random circuit on a d-dimensional lattice, you form K designs, again with some high degree polynomial dependence on K. And as we heard about in the last talk, this very nice paper kind of took a different approach to efficiency, where they showed that n times poly K depth local random Clifford circuits are K designed with kind of only a polynomial number of expensive gates, of non-Clifford gates. And again, up to this square root n moment. And Nakata et al. Considered some time-dependent Hamiltonian construction and found that they form K designs linearly in K, but again, up to this kind of low moment order. So the quantity I'm actually going to be interested in this talk is a more tractable measure of Haar randomness, and it's something called the frame potential, where the kth frame potential for an ensemble of unitaries is defined as this double average over the ensemble. And this actually captures the 2 norm distance to Haar randomness. So for some ensemble of unitaries, this quantity actually turns out to be lower bounded by its Haar value, which is just k factorial, with equality if and only if the ensemble forms a k design. So given some ensemble of unitaries and some k, this is just some number we can compute. And how close that number is to k factorial tells you how close you are to forming a design. Okay. More precisely, the difference in frame potentials bounds the diamond distance between the channels up to this dimension factor. Okay. And the frame potential has kind of come up in the literature recently, in more of the many-body literature, and is kind of understood to be related to different notions of scrambling and chaos. So our approach in this talk is going to be to focus on this, this nice simple quantity, the frame potential, and try and analytically compute it for random quantum circuits. And we're going to make use of some ideas in these papers and write the frame potential exactly as a lattice partition function. And we're going to be able to compute this, this partition function exactly in the second moment case. But for very general k, we're going to have to sacrifice some precision and rely on a limit. But we'll see that the decay to Haar randomness has a nice interpretation in the lattice model in terms of domain walls. Okay, so as I said, the goal is to compute this frame potential. So if we just remember, it's just this double average over the ensemble. So if we just look at its 2k moments of this quantity here, this U dagger V quantity. So if we just look at one of them, we immediately see that we can kind of simplify this and combine by the invariance of the Haar measure. We can combine one of these layers here in the middle, and also combine one of these layers on the outside through the trace. So really what this, and because we're averaging over U and V separately and independently averaging over each local unitary, this is really just equal to the moment of traces of depth 2t-1 random circuits. Okay, so this is really the quantity we need to consider. Okay, so we have k moments of this depth 2t circuit. So this is k copies of the circuit and its conjugate. And recalling that Haar integration is really just a prescription for index contraction, where we kind of contract the ingoing legs and outgoing legs separately with respect to some permutation and weighted by some factor called the Weingarten function. Thinking about this a little bit allows us to reinterpret this quantity, and we can replace the average over the 2 set unitaries in terms of this effective kind of 4-leg vertex, where the diagonal legs here are just index contractions with respect to a permutation sigma and tau. So these are elements of the symmetric group SK. And the diagonal, the horizontal line here is just the weight determined by the Weingarten function. So doing this, it turns out we can write the frame potential exactly as the partition function on this hexagonal lattice model. So here time is running left to right, and these nodes here are identified with these nodes here. This is kind of the the trace. Gives us periodic boundary conditions in time. So and we sum over all spin configurations sigma and tau. And here the diagonal lines are inner products between permutations. So, I mean, this is nice, but a priori it's not super enlightening because we've, just kind of reduced one hard quantity to some horrible mess of tensor network contractions. But it turns out a very nice simplification occurs when we sum over some subset of the nodes. So summing over all of these blue nodes, we can define an effective interaction between 3 of these spins, 3 of these permutations. And I'm going to denote that as this triangular plaquette term. And then doing this, we can write the frame potential as the partition function on a triangular lattice model. So I'll just summarize, and I'm actually going to rotate time now. So time here is running left to right, but for the rest of the talk, it's going to be running up. It's just going to be a little bit more visually convenient. So the kth frame potential is given by the partition function on this triangular lattice model, where each local degree of freedom, these spins, are elements of the symmetric group SK. And the lattice has width n over 2 and depth 2t with periodic boundary conditions in time. So these spins are identified with these spins. And these plaquette terms are functions of three permutations, which can be written explicitly like this, but they're just some functions we can compute. And they turn out to have some very nice properties. Okay. So it turns out we can show that if you kind of plug in the same spin everywhere, you just get a weight 1. So the entire spin configuration has weight 1 if you plug in the same spin. So we already see where this minimal Haar value is coming from. Remember that this frame potential is lower bounded by k factorial. So we see that, as there are k factorial elements of the symmetric group, that means there are k factorial ways of plugging the same spin everywhere. So k factorial ground states of this lattice model. So the decay to Haar randomness is really going to be just the decaying contribution of the excited states in this partition function. And for k equals 1, there's only one local degree of freedom, so only one weight 1 configuration. So the frame potential equals 1, and random circuits form exact 1 designs. But the second moment actually turns out to be non-trivial. So this is where we have local degrees of freedom. They're Ising-like spins. So elements of S2, which is the identity and swap. So here we can just directly compute the plaquette terms, and we find that, again, plugging the same spin everywhere, we just have weight 1. But there are kind of more non-trivial rules when the neighboring spins differ. So remember here, time is running up. It turns out that the best way to think about these is in terms of domain walls separating regions of identity and swap operators. So if I just draw in domain walls separating the differing permutations, and again, remembering that time is running up, we see that these kind of tell us that the domain wall at a plaquette with no domain wall has weight 1, and a domain wall can move left or right at each plaquette term at the expense of this factor, and domain walls can't end. Right? So if a domain wall ends, the entire configuration has weight 0. So the only non-zero contributions to this partition function are domain walls which wrap the circuit. Right? And they need to start and end at the same place because we have periodic boundary conditions in time. So here's an example of a single domain wall configuration separating regions of identity and swap operators, and some double domain wall configuration. And we see that there's a nice interpretation of the decay to Haar randomness as domain walls stretching through the circuit. So as time evolves and the circuit becomes deeper, we have higher energy domain wall configurations which have decreasing contribution of the partition function. So to compute the 2 design time, we simply need to count all the domain wall configurations. So just count the number of single, double, triple domain wall configurations. And we know what the weights are because we computed these non-trivial plaquette terms. So we just need to compute these combinatorial factors for the number of single or double domain walls. And it turns out this quantity is actually very easy to bound. So we can just bound it like this. But these coefficients are actually, you can actually exactly compute them. So just by solving the problem of p non-intersecting random walkers in the presence of boundaries. And this makes use of some nice ideas from kind of statistical physics papers from the 80s. But to compute the approximate 2 design time, all we really need is this bound. So we have the, remembering how the frame potential relates to the diamond distance between the channels, this just directly gives us the epsilon approximate 2 design time, which we find to be linear in n plus log 1 over epsilon, where this linear in n factor has some constant which we can exactly compute, which is a function of the local dimension q, and is very small for q equals 2 as well as a large q. So this reproduces the known result that the approximate 2 design time is linear in n, albeit with an exact calculation and an exact determination of the constants. And it's also fun just to note that I took a 1D chain with open boundary conditions in space, but if we took periodic boundary conditions, so qubits on a, or qubits on a circle, this constant factor improves a bit because we're kind of only allowed to have even domain wall configurations. So we decay even faster. Okay, so that was the second moment, and we could do everything exactly, but for general k, we're going to need to sacrifice some precision. So remember, the kth frame potential was this lattice partition function where the local spins were elements of the symmetric group Sk with these plaquette terms. And before we had just one type of domain wall, which represented the kind transposition, which takes us from the identity to swap. But for general K, we have a separate domain wall for each type of transposition in the permutation group. So generically, we have K choose 2 domain walls in the kth frame potential. All right, so yeah, before kind of the combinatorics were fairly easy, and we could kind of directly count all the domain wall configurations. But for general K, it's kind of less amenable to an exact treatment. So we're going to need to, we're going to need to sacrifice some precision and do something to make the problem tractable. So for general K, these domain walls are now, turns out they're allowed to interact, pair, create, and annihilate, which they weren't allowed to do for K equals 2. And this means we can have closed loops in the circuit. So there's no longer this nice division into different kind of domain wall sectors. So the combinatorics definitely seem more ominous. But there are a few facts you can prove about these plaquette terms for any K, which kind of guarantee a nice sector of domain walls. So for any K, you can show that a plaquette term with no domain wall has weight 1. And anytime a single domain wall goes through a plaquette, you always pick up this factor. And moreover, any plaquette term with where a domain wall annihilates with no outgoing domain walls or 1 outgoing domain wall has weight 0. And what this means is that for general K, you always have this contribution from the ground states and from the single domain wall sector. So you can kind of compute the ground states and the first excited states. But you don't really have much control over the higher order excited states. But these rules kind of guarantee this nice simple sector of domain walls. And moreover, what you can show is that these plaquette terms are always are kind of heavily suppressed in Q, depending by the number of domain walls. So more visually, this proves that multi-domain wall terms are heavily suppressed. And are very subleading in 1 over Q. So roughly the number of domain walls that go through a plaquette term has contribution, which is like 1 over Q to the number of domain walls. So what this does is it shows that for some Q larger than a value, which is going to depend on the moment K, you can just extract the design time from the single domain wall sector. And what that actually gives you is the depth at which you form an approximate design is going to be roughly linear in N and K in this large Q limit. Okay, so I'll just wrap up. So what we've done is we've showed that that random circuits form approximate K designs in a depth which is linear in N and K. But we were only able to really kind of show this rigorously in a large Q limit. But there are kind of a number of reasons I believe that this limit is likely not necessary. The more complicated the interaction is, the higher the more severe the suppression is. And many of these interaction terms actually have negative weight. So if you're just trying to upper bound them, you can just drop them. So I left it as a conjecture that for any local dimension Q, these single domain wall terms kind of always bound these multiple domain wall terms. But at least in the large Q limit, as the lower bound on the design depth is linear in N and K, what we've then shown is that, in this limit, random circuits are optimal implementations of designs. So there are a number of things I'd like to understand. First is, can we rigorously bound the higher order terms in this partition function for any local dimension? It might also be worth revisiting different techniques to show, or different methods to show random circuits form designs, just bounds on spectral gaps, and revisit these at small q. And these StatMech methods for random circuits are very powerful. So we could imagine asking different questions about different random circuits in different geometries or with different kind of conservation laws, and ask questions about their correlation functions or their pseudo-randomness properties or their entanglement growth. And I think the StatMech methods might be a good approach to address some of these questions. And as we'll see in the next talk, a linear growth in design also has implications for the growth of complexity. So I'll end there, and thanks for listening.
Thank you, Nick, for the great talk. we actually have one question in the Q&A session from Felix Ludovico. He asked, can you say again what the constant Q is?
Oh, Q is just the local dimension. So yeah, here, well, I'm not going to go back, but yeah, Q here is just the local dimension. So I'm considering a system of n qubits with local dimension Q. And so for qubits, Q equals 2, but it turns out if you take the local dimension to be large, so if you take a large Q limit, you actually get a lot of, yeah, there's a lot of power in this limit, and you can control a lot of quantities, specifically these kind of higher order terms in this frame potential.
Thank you. Do we have any more questions? If not, let's go ahead with the next talk. So Nick is going to talk about models of quantum complexity growth. Thank you, Nick.
Okay, and we're running on time?
Yeah, I think we are good in time. Is okay. Great.
Right. So right, I'll just segue straight into the next talk. Actually, can you remind me when we're supposed to end? It's supposed to end at 20 past?
Yeah, I think it's 7:20. Yeah.
Okay. All right. So I'll start the second talk. I'd like to again thank I'll re-thank the organizers for putting on a really incredible conference and doing a great job hosting the conference virtually, or phenomenal job hosting the conference virtually. I'm going to be talking about a paper, which is joint work with Fernando Brandão, Wissam Chamasani, Richard Kueng, and John Preskill about complexity growth in random circuits. And many of the ideas and techniques in this work were due to Richard Kueng, pictured here. And kind of improving some of our main results, we relied on some results I talked about in the previous talk about design growth in random circuits. Okay, so I'll get started. So quantum complexity is a very important and a fundamental idea in quantum information, and it allows us to distinguish tasks, computational tasks, which are easy versus hard for a quantum computer. And we're used to thinking about the complexity of quantum circuits, but there's been a lot of recent interest in the circuit complexity of quantum states in quantum many-body physics. So by thinking about the complexity of the ground state wave functions allows you to distinguish topological phases of matter. And the complexity of a specific, in the context of the ADS-CFT correspondence, the complexity of a specific CFT state is conjectured to describe the region behind the horizon of an ADS black hole. And more generally, complexity growth is kind of one universal aspect of the real-time dynamics of strongly interacting many-body systems. So if you're interested in kind of understanding universal phenomena that arise from generic many-body systems and kind of are asking questions about real-time dynamics, complexity growth is kind of one underlying phenomena, along with things like thermalization, scrambling, entanglement growth, etc. Okay. So we're going to be talking about quantum complexity. And complexity is a fairly intuitive notion. And the traditional definition involves building a circuit with gates drawn from some universal gate set. So two local gates drawn from some universal gate set, which approximately prepares the state or unitary to within some tolerance. Right? So if we have some unitary, we're interested in some decomposition in terms of gates from some two local gate set, which prepares that unitary. And the complexity is then the minimal size of the circuit that does this. Okay. And just to set some notation, I'm going to be considering systems of n qubits, again with local dimension q, just as in the last talk, because as we saw, it's a nice parameter that we can play with sometimes, such that the total Hilbert space dimension is q to the n. Okay. So it's believed, maybe expected or conjectured, that the complexity of a simple low entangled initial state grows potentially linearly under time evolution by a chaotic Hamiltonian. Okay, and is believed to saturate after an exponential time. The same holds for the complexity of the unitary time evolution operator itself. So e to the iht, so that the complexity of this unitary grows, again, possibly linear in time, for a generic Hamiltonian, saturating after an exponential time. So exponential in the number of qubits. So something like e to the n. Okay. So this might sound reasonable, but computing the complexity of a specific state or unitary, especially with a fixed Hamiltonian, is very hard. And the reason is because, you know, if you, maybe you hand me something which approximately, you know, prepares that unitary, so some circuit composed of 2 local gates, which prepares that unitary, what you need to do is you need to prove it as the minimal one. You need to prove it as the smallest such circuit that prepares that unitary. So, you know, that seems like a very complicated task, and naively it seems like it amounts to enumerating all possible circuits to find the shortest depth one. So yeah, so kind of to lower bound the complexity, what you need to do is prove that there are no shortcuts, which sounds very hard. So why do we expect these features, like linear growth in this plateau? Well, as I said, kind of for a generic Hamiltonian, like the complexity should scale with the time we evolved for, and at least at early times, collision should be rare. So I shouldn't be able to prepare the unitary with a much shorter circuit. And moreover, there are some upper bounds on the growth of the complexity just from Hamiltonian simulation. So for instance, using methods like trotterizing the time evolution and decomposing into 2 local gates using Solvay-Kitaev and controlling the total error, or using many of the myriad of other Hamiltonian simulation methods, which work for very general, possibly time-dependent Hamiltonians. These give an upper bound on the complexity growth. So in a lot of these algorithms, the circuit size scales linearly or polynomially in T, right? So this is an upper bound on the growth. But as I said, the hard thing is proving lower bounds on the growth, on the complexity. So this is an argument for why we expect this kind of growth regime. And we also expect the complexity to saturate at an exponential time. And this just kind of comes from a simple counting argument. So in some sense, the volume of the unitary group is really doubly exponential in n. So more precisely, if we just count the number of balls in UD of size delta, right, what we do is we find that there are roughly e to the n distinct unitaries. So if we think about how many circuits of depth t there are, we realize that once the circuit depth is exponential in the number of qubits, so once the circuit depth is like 2 to the n or e to the n, we see that the number of possible depth t circuits becomes the same order as the number of unitaries in the unitary group. Okay, so what this means is that we can reach any unitary with a depth t equals like 2 to the 2n circuit. Okay. So this is the argument for why we expect the complexity should saturate. But these are just, again, some kind of more rough intuitive things. What we actually want to do is you know, kind of prove these features. And to make progress, there are kind of 2 different approaches we can take. We could imagine making some complexity theoretic assumptions to make statements about the complexity of a particular Hamiltonian evolution at exponentially long times. So, for example, in work by Aronson and Susskind, as well as Bogdanovich and Brandão, where they consider the complexity of a specific Hamiltonian at exponentially long times. And what they showed was that the complexity needs to be super polynomial, assuming some separation of complexity classes at these exponentially long times. So, you know, assuming something like P space doesn't equal BQP, I think, in this work. So this is kind of one approach you can take to make progress in understanding this regime. But if we want to make progress understanding this growth regime, another option is to, instead of focusing on a specific Hamiltonian or specific time evolutions, to focus on ensembles of time evolutions. So just as in the previous talk, I'm going to be considering ensembles of random quantum circuits. So these are local random circuits, kind of constructed from these nearest neighbor random gates, again on n qubits with local dimension q. So if you have qubits, this could be q equals 2. And again, we could imagine evolving with these staggered layers of two-site unitaries and drawing each gate in space and time randomly from some universal gate set G. And the goal is to prove complexity growth in this model. And actually, for the first part of this talk, this kind of brick layer, this layered or parallelized construction is not going to be super important. So we could also imagine a model of random circuits where at each time step we apply one nearest neighbor gate to a random pair of qubits. And I think, yeah, the results are essentially going to be the same in the first part of the talk for these different circuit models, but only in the last part of the talk, when I need to use the result from the previous talk, will I specify this circuit with a fixed geometry. Yeah, and kind of the only difference between these two models is really there's some difference in the scaling of the depth of the circuit with n, just because here I'm applying order n gates per time step, whereas here I'm applying 1. And I actually find it more convenient to talk about the depth of the circuit instead of the size, but it's not that important. Okay. So again, we want to try and prove something about the complexity growth for these random circuit models. And specifically, it's been conjectured by Susskind and Brown and Susskind that most of these local random quantum circuits of depth t have complexity which scales linearly in time for an exponentially long time. So again, this sounds totally reasonable, right? You hand me one of these circuits, and it's built from gates from this gate set, which might be the same as you use to define complexity. So it just sounds like this should be, just count the number of gates, and that should be the complexity. But again, as I emphasized before, this is very hard to prove because you need to prove that there was no shorter circuit. So you need to prove that there was no way you could have approximately prepared that circuit with a shorter circuit. So explicitly, you need to show that collisions between circuits of sub-exponential size are rare. And then again, as you kind of approach very late times, you expect that these kind of collisions should become more common. Okay, so first I'm going to define complexity. And then, I guess in the spirit of this session, I'm going to talk about the complexity of designs. So just, these abstract, nice ensembles. And then using the fact that random circuits form designs, we're going to be able to prove something about their complexity growth. And then I'm going to make progress on this conjecture, kind of using this linear design growth result from the previous talk. Okay. So as I said, the complexity of a unitary, and I'm actually just going to, for this talk, everything I say is going to apply to the complexity of unitaries as well as the complexity of states, but we're just going to focus on unitaries for now. So the complexity of a unitary is the minimal size of a circuit built from some set of elementary two local gates, some universal gate set G. The minimal size of a circuit which approximates the unitary. And I'm going to let G sub R denote the set of all size R circuits. So more precisely, we're going to say that a unitary has delta complexity of at most R if there exists a size R circuit V such that the corresponding channels are close in diamond distance. Right. So what this is just saying is that there's a size R circuit V, which is close to our target unitary. And we're going to denote this as the delta complexity of that unitary being less than R. And then what we're interested in is finding the minimal R for which this is true. Okay. We can also consider a stronger definition of complexity in terms of an optimal distinguishing measurement. And actually, in most of our work, we focus on the stronger definition, and actually a lot of the effort in our paper was devoted to proving our results, proving that our results hold under this strong definition of complexity, which Richard actually came up with. And roughly speaking, the strong complexity of a unitary is the minimal circuit required to implement an ancilla-assisted measurement capable of distinguishing the channel from the completely depolarizing channel. So the task is to distinguish these two channels with a two-outcome measurement with restricted state preparation and measurement. Okay. So again, the intuition here is that if you have a very simple unitary, right, you might be able to apply like a pretty simple measurement to distinguish these two channels. But if your unitary is very complicated, you might need to perform a large depth measurement to distinguish the two. Okay. So more precisely, we say that a unitary has strong delta unitary complexity if the optimal bias is greater than this quantity. Okay. And I'm actually not going to dwell on this strong notion. Oh, and I should say that it's strong in the sense that this implies the standard circuit circuit complexity, the standard notion of complexity, but the converse is not true, given some unitary. So I'm not going to dwell on this too much, and I'll just say that all of the results I'm going to talk about are going to hold for both definitions of complexity. Okay, so as I said, we're interested in the complexity of random quantum circuits. And to make progress, I'm going to derive some very general statements about the complexity of unitary designs. But first, I'll just remind you of the notion of a unitary design. So as we heard about in the previous two talks, we say that an ensemble of unitaries forms an approximate design if the average of that ensemble over that ensemble of the kth moment. So this could be some monomial expression of KUs and KU daggers. If the average over that subset of the unitary group is close to the average over the full unitary group. Okay. More precisely, we say that we have an exact design if the k-fold channels are equal for all operators O, and an approximate design if the k-fold channels are close in diamond norm. All right. And this is really just saying that the average of this quantity over the subset is close to the average over the full space. So that's a design. So if we consider, for instance, a discrete approximate unitary design, so this is some weighted subset, one might imagine asking if the structure of a design allows you to say anything about the complexity of the unitaries in that design. And it turns out the answer is yes. The structure of a design is actually it's pretty powerful. And you can just directly count the number of unitaries of a specific complexity. So we can actually prove the following two statements, which are just written informally. So with very high probability over the weights of your design, a unitary drawn from that approximate design has complexity linear in n and k. So it's complexity nk. And moreover, using a bound on the weights of a design, you can kind of directly count the number of unitaries with this complexity and show that there are an exponential number, so like something like e to the nk, distinct unitaries with this complexity. And the emphasis on distinct here is important because we might, we're trying to rule out shortcuts, right? So we're interested in when there are collisions between unitaries. So we want to, in the set, we want to really count the number of unique things of a given complexity. Right, so this is like the average complexity is like nk for an approximate k design, and there are an exponential number of distinct unitaries with that maximal complexity. More precisely, we say that for an epsilon approximate unitary k design, there are at least this many distinct unitaries with complexity greater than r, which is essentially exponential in n and k. And for strong complexity, so proving this is relatively straightforward in the normal circuit for standard circuit complexity, but proving this for this strong complexity in terms of an optimal distinguishing measurement was actually fairly difficult and required proving some very general bounds on Haar moments, and proving those bounds required using techniques like Schur-Wilde duality and Weingarten calculus, as well as additional arguments from tensor networks and convex optimization to kind of prove these very general bounds, which give this complexity result under the strong definition for measurements. Okay. Right, so we have this result for the complexity of designs. And as we've heard about, I guess now in the previous two talks, we know that there is a connection between designs and random circuits. So if we consider these G-local random circuits on n qubits with gates drawn from the gate set G, we can use this very powerful result from Brandão, Harrow, and Hordetsky, which says that for moments less than square root in the total Hilbert space dimension, the set of all G-local random circuits of depth T forms an approximate unitary design if the depth is roughly, if the depth is order n times k to the 11, with some constant that depends on your gate set. Okay. So, at depth T, if T is like n times k to the 11, you form K designs. And we can now combine these two results to say something about the complexity of these random circuits. So as I said before, at very early times, we expect the complexity just to be, the size of the circuit, which should be like, n times t. But we need to prove that there are no collisions. So we need to prove that, that two circuits, basically that a depth t circuit we couldn't prepare with some circuit of a much shorter depth. Okay, but the definition of an approximate design, and specifically a bound on the weights of a design, allows you to restrict the number of potential collisions and directly count the number of distinct circuits of a given complexity. So combining these two theorems allows us to say that with very high probability, a local random circuit of depth t has complexity which is t to the 1 over 11 with some factors of n. And the set of depth t local random circuits contains at least an exponential number in t to the 1 over 11 distinct unitaries with this complexity. So this establishes a polynomial relation between the growth of complexity and the depth of the circuit up to exponential times. So this is some growth which is like t to the 1 over 11, so some very slow growth. So this is definitely a very powerful statement, but what we really set out to prove was a linear growth. Kind of recapping, what we've shown is that complexity is linearly related to the design order k. And then we use this result by Brandão, Horohordetzky, which says that t, it goes like k to the 11, to prove a complexity growth, which is like complexity going like t to the 1 over 11, right? To prove this slow complexity growth. And this actually holds for both kind of these parallelized as well as kind of random local quantum circuits. But more generally, every time you have, if you have some model of time evolutions which is forming designs, you can use this complexity by design result to prove statements about their complexity growth. So for instance, in these Brownian circuits, a result due to Onorati et al. Showed that the design depth has this similar high polynomial dependence on k, which gives you this same slow complexity growth. And in this paper by Nakata et al. For kind of a time-dependent Hamiltonian construction, what they found was that you form k designs linearly in k. So that's, it's very nice. You get this linear growth in k, but only up to some kind of very low design order. So only up to square root n. So this kind of proves a linear complexity growth for very short times. And lastly, in higher dimensional random circuits, it's known that for random circuits on a d-dimensional lattice, form designs in n to 1 over d. D is the spatial dimension of your lattice, times polynomial in k with a high degree polynomial, which I think has a larger exponent than 11, which depends on your dimension. And this again proves some slow sublinear complexity growth in these models. But what we were really interested in was random circuits and a linear growth of complexity. So to get a linear growth of complexity, what you need is a linear growth in design, right? So we had this linear relation between complexity and the design order k. So what we really need is that the design growth in these random circuits is scaling linearly in k. So a linear relation between k and t. Right? And as I mentioned in the previous talk, Brandão, Horohordetzky gave a lower bound on the k design depth to be roughly linear in n and k. So, I guess we already know the answer if you were listening to the previous talk, but the question now is, can we prove that random circuits saturate this, or kind of come close to this lower bound and are optimal implementations of k designs? Because this will give us this linear growth in design we need to prove a linear growth in complexity. So I'll just review the result in the last talk. Using this exact statistical mechanical mapping, what we're able to do is show that random circuits form designs in a depth which is linear in n and k in the limit of large local dimension. Okay, and here this was specifically for the random circuits that were of the parallelized form. These kind of where I apply order n gates per time step. Right, so the result was that right for some q, which is for some large q, the design depth is linear in n and k. So using this result, we can just go back and plug this into our complexity by design result. And what this allows us to establish is the conjecture we originally set out to prove for local random circuits, at large local dimension Q. So the corollary we find, the corollary we've shown is that the set of all local random circuits of depth T contains at least an exponential number in T of distinct unitaries with complexity T. Okay. So what this is saying is that complexity is growing linearly in time for a long time. And the number of unitaries, the number of distinct unitaries in the set of random circuits of depth T with complexity T, so generated by time evolution to time T, scales exponentially in T. So there are like an exponential number in T, distinct unitaries with this complexity. Okay, so this is nice. What we've done is we've proved this conjecture for large Q, but there are a number of things we would like to, a number of very interesting future directions. So one could ask, can we prove anything about the complexity of a unitary time evolution e to the IHT for a fixed Hamiltonian? We can also ask if there's if we can prove this linear design growth at small local dimension Q. So this is also the an open problem in the previous talk. Is can we prove this linear design growth for, say, random circuits on qubits? And can we show that this design growth is linear for exponentially long time, so for exponentially large moments? There are also a number of confusing things about this late time regime. So the complexity saturating at exponential times. So when the design order is larger than the dimension. So there are a number of open questions there. And we introduced the strong notion of complexity in terms of an optimal distinguishing measurement. And I think there are a number of nice implications that in quantum information and for holography with the strong notion. But with that, I'll end, and thank you very much for listening.
Thank you, Nick, for the great talk. We have one question from Abhinav Deshpande. He asked about regarding the definition of strong complexity being stronger than the regular one. Do you mean the strong complexity is a lower bound for the regular one? And can you see that by simply undoing the unitary, which allow us to distinguish the two evolutions? So the strong complexity is almost equal to the gate complexity.
Yeah, that's right. Essentially, that sounds right. Yeah, basically for a strong complexity, if you have, if you know that some unitary has strong complexity R, this directly implies that that the circuit complexity is at least R, or sorry, is at most R, but the converse isn't true. So kind of one example which kind of highlights the difference is if I have some very complicated unitary and I add like one ancilla qubit, the normal circuit complexity doesn't change, right? Like it's the circuit depth that hasn't really changed. But in terms of measurements, right, I might imagine being able to like measure that single qubit to see that I'm not in the completely depolar, to see that this is not the completely depolarizing channel. So yeah, kind of by that's kind of one example which highlights the difference between the two. But yeah, in general, having strong complexity R implies that the standard complexity is at most R, but the converse is not true.
Okay, thank you. We have another question from Mike Vassmer. He asks, could you elaborate on the implications of strong complexity?
Yeah, maybe I won't. Because maybe I won't speculate too wildly, but yeah, I imagine there are a number of very interesting ways you can take this for quantum information. Kind of what I meant here is in holography. So yeah, I basically didn't talk about this much, but a lot of the papers on the archive now about complexity growth are actually in the HEP-TH section, and they're trying to understand complexity growth in these holographic systems, so in the context of the ADS-CFT correspondence. And basically what they're doing there is they're doing calculations in the bulk. So they're basically doing gravitational calculations for some quantity that they think is related to the complexity of a specific boundary state. So a specific quantum state in the CFT. And so they're computing gravitational path integrals or computing bulk actions on specific patches, and they and they're claiming this is equal to complexity. So basically, by doing these gravitational calculations, there are a number of features you can see that you might expect from complexity. And kind of one of the things they notice is something like this clean qubit example I was saying, where adding a clean qubit kind of resets your complexity. So that isn't the case for the standard definition of circuit complexity, but it is the case with the strong notion. So in that sense, this strong notion might capture something more relevant in holography. But probably more interest to this audience, I imagine there are implications of this kind of optimal measurement complexity for other areas of quantum information, but maybe I won't speculate too wildly, but yeah.
Okay, great, thank you. So is there any other questions? If not, I'm going to declare the end of this session, and I will hand it over to Andreas. He will say some concluding remarks from the local organizing community. Thank you for the nice talk.
Hello everyone, thanks for attending TQC. We had 830 participants from 57 countries, which is many more than what we expected. Online conference provides an opportunity for people to join just for a session or just for a few talks, and many people used that. And I hope that we continue to have some online conferences after this pandemic is over. And we also hope to see you in Riga at some point in future where traveling becomes possible again. Thanks to all the speakers for their great talks, to session chairs for chairing sessions, to program committee for all of their work in putting together the program, and to steering committee for providing guidance to the conference. Thanks to all the local organizers. We had more than 10 local organizers involved in organizing the TQC. Thanks to our Zoom team, consisting of Alexander Rivosh, Evgeny Svichros, Juris Smotros, Martin Škalis, and Martin Škokainis. Many of them also dealt with many other aspects of the conference, from creating the schedule to communicating with participants. Thanks to our communications person, Ilyana Polyakova, for setting up web page and dealing with all the other communications aspects. Thanks to Dace Shostaka for dealing with EasyChair. Thanks to the administrative director of our faculty, Kaspar Ščikste, for dealing with the budget and financial issues. Thanks to our Slack team consisting of Jānis Siraits, Andis Draguns, Mati Sapins, and Elise Gaile. And thanks again to all of us, all of you for coming here and listening to the talks. And we hope to see you in Riga at some point in the future. Thanks to everyone. Bye.